Can you hear me? Yeah. Okay, so welcome for today's session of ACT. The first talk of the morning will be given by Ryu Rodriguez Sakamoto, who will tell us about value iteration as optic composition.
Thank you very much. So I want to motivate this talk as given how you can make your best decisions. And I want to first introduce the topic with a very down-to-earth explanation, introduction, and then we're going to see how to apply the framework of optics in this sense. So if you're faced in the situation where you have to take an action out of n possible actions, you may wonder like which action to choose to get the best reward. So for each action, you may have a fixed distribution of rewards. And if you got a finite set of actions, you might always choose, well, the action that maximizes this reward. And this is called a greedy policy, where you just maximize this reward. But if you may think, well, my estimation of this reward might not be perfect, so I might try to choose a suboptimal action with a subprobability epsilon, and this is what is called an epsilon greedy policy. And this already introduces us with a dilemma between exploration of possible actions and exploitation of the best actions that you know so far. Now, considering now a second case where you've got, depending on your state, you've got different sets of actions that you can choose. In that case, you have to choose the best action depending on your state. But these actions are still giving an immediate reward. And this is what is called a contextual bandit problem. In the case that your actions then affect your future states, then you have to think about, well, what's my best action now, depending on the possible future rewards in the long run. And this is what's called the general reinforcement learning problem, where you have many states and your rewards may be delayed. And this is formalized as a decision process where you can think of a state space X and an action space A. Then you have transition functions and utility or reward functions. And again, your objective is to build a policy, which is a way of choosing, depending on where you are in the state, what actions to choose from the action space. The objective is then for this policy to optimize this long run reward, which we can think of summing all the possible utilities along the sequence of the states that we are going through, discounted by a factor beta, which serves a dual purpose, which is on one hand to have a finite value for an infinite horizon problem that is in the never-ending sequence of states, and on the other hand, also it allows you to leverage the importance of the utilities of the future states in the case of a beta close to 1, or giving importance only to the states that are the very next ones, if you in the case of a factor beta very close to 0. So there's two ways of getting an exact solution of this problem. So on one hand, you have linear programming methods. On the other hand, we have dynamic programming methods. And I'm going to focus on the second one. And the main idea is to assign value functions, again, to policies with the functions that we've seen before. And we start by having a rough estimate of this value function. We can think of starting with a value function that gives 0 reward for every state. And then you're updating this with what I call the Bellman update steps. You both update your value function or your policy. So the value improvement step allows you to update this value function. It's also called a policy evaluation in reinforcement learning, where you assign a new value to a given state X, depending on the utility that it gives the state and the action that you're going to take, depending on your policy, and the discounted value for a future state, with F being the transition function again. We can also think of updating our policy, where now for a given state, you have to choose the action that maximizes, again, this expression. Now, the fixed point of these two equations separately. On one hand, you have for the value improvement, you can update this until you get to the point where updating the value function doesn't change it at all. So we say that we reach this fixed point of the value improvement equation, and we can also think of a fixed point of the policy where the policy doesn't change anymore. So there are two classical dynamic programming algorithms where you interleave these two steps of value improvement and policy improvement in different ways. So in policy iteration, which is the first algorithm, you improve your value until you get to the fixed point, and then you update your policy. And then you start again by updating the values. In value iteration, however, you update your value function once, you update your policy once, and then this is the thing that is going to be repeated. In that case, we usually fuse these both steps into a single equation, which is usually written in this manner, where you update your value function already maximizing of the possible actions. Now, to see a very down-to-earth comparison, we can think of the situation where you are in a 2D grid world, and you want to get to a specific location where you have the maximum possible utility of 1, let's say. So you start with maybe a naive policy where you just go upwards regardless of which your state is. Then in policy iteration, which is this first row, you update your value function depending on the policy without changing it until you get to a fixed point where you then update your policy, and then these red arrows then point again to the position where you try to maximize your utility. On the other hand, in this value iteration algorithm, you update both your policy and your value in each step. And in both cases, you end up converging given some conditions. You end up converging to a optimal solution, which is an optimal policy that goes to the desired location in the shortest amount of steps. Now, this is also studied in a stochastic case. In the case of, for example, we have a non-deterministic transition function or a non-deterministic utility function, or your policy may be also non-deterministic. And we can think of these functions then being a morphism in a class morphism of some probability monad. One thing, for example, the same example as before, but where maybe your policy gives just a probability distribution over the possible neighborhoods where you want to go in a specific state. Now we can also think of continuous spaces or continuous action spaces or state spaces. We can give a very central example in economics, which is the savings model, where state space now consists of your assets, or you can think of your savings, and then in each step you decide how much you want to consume of these assets. Then this is again the policy that lets you choose for each state what amount what amount you want to consume, and the transition function gives you the next amount of savings. That is your current savings minus the things that you consume plus some interest, and then multiply plus times a gross rate of return. This is again formalized with a value iteration algorithm, which is given here down below. We can also think of other examples of a continuous space, for example, the control of an inverted pendulum. And also in the case of stochastic transition in continuous spaces, we can think of these maps living in some classical category of a Giri monad, for example, or some suitable subcategory. Now, I want to introduce the way we study these things using the framework of optics. So just to give a brief recap, we've seen already some great talks on Tuesday about optics and mixed optics, but I want to give a brief explanation. So let's consider a monoidal category M. Oh, sorry. And then another category C. We say that the monoidal category M acts on C by the functor from M times C to C, which is called the action. Given some coherence conditions, we then say that C is an M actagory. Given M monoidal category and two actagories, then we can build the category of mixed optics of CD, where objects are pairs, so X living in the category C, X prime living in the category D, and morphisms as well as cohens. You can think of this as an existential quantifier of M, where you give a morphism in the category C from X to M acting on Y, and in the backwards pass, you can think of a morphism of M acting on Y prime going to X prime. We can think the intuition is that the necessary data to define this morphism is an equivalence class of this residual M and this forwards map F, backwards map F prime. So in the case of we want to give a more specific example which are optics where we choose these categories to be this C category and the M category to be marked. That is the Kleisli category of a probability distribution monad, and the D category to be the Altenmüller category of the same monad. So these two categories are monoidal, and in particular, I want to emphasize that D is monoidal with respect to a tensor product, which is similar to the tensor product of modules over a ring, and it's moreover closed under this monoidal product, where the function set from X to Y has also a convex structure given pointwise. So to repeat, we can build a category of optics from mark to conv, where the forwards maps lives in mark. These are Kleisli morphisms, and the backwards map lives in conv. So this delta M is the embedding of an object in the Kleisli category to the Altenmüller category, and because of this closed structure, we can just basically move this delta M tensor Y prime, so Y prime to the other side. So we've got a function from delta M to functions from Y prime to X prime. So in the case of non-mixed optics, that is where both the category C and D are the same, we've got a formal string diagram syntax. In the case of mixed optics, this is not quite formal. So let's just take these images as some intuition. But again, the morphisms can be represented this way, where the forwards category has an input X and then output Y, and you save some M that you plug into the backwards map F prime with an element Y prime and outputting X prime. Now, co-states are special morphism where the right-hand boundary is the monoidal unit. So you can basically think of this as discarding this output and not giving anything as an input. And this is important because we want to. This is one of our building blocks. So what does this have to do with what we explained so far about value iteration? The idea is that this movement across states with the transition function and your policy is a way of simulating looking into the future. And then we want to, given the values of these future states, we want to update our priors or value functions and give an output of the value of our current state. Again, co-states also have a significance here, where they are interpreted as an initial estimation of our value function. So given that the optic goes to the monoidal unit, we can think of this just as function from X to R. And more closely, how does then this internal structure look like? Well, we can think of it as this way, where you've got the state that you're in, and then you choose with a certain policy the action that you're going to take. You then save the current state and the action, and you input it to the transition function to give you the next state. And you also save your action and your current state to calculate the utility on the backwards pass. On this hand, we can then plug in the value of our next state. You discount it and you sum it with the current utility, and you get back this the current value, the value of your current state. For convenience, we're going to separate this lens as two different lenses for convenience. So in this first one, we're just applying the policy, and on the next one, we are doing everything else. And just to note, the words lenses are just optics where every category are sets. So it's a very nice setting. So if you want to talk about these two maps that we've seen before in value iteration, that is the value improvement and the policy improvement, we can think of these as certain maps in our dynamical system. So the data that we have in each step is, well, our current policy, which is a function from X to A, and our current value function, which is an optic from XR to the monoidal unit. and that is this data. What does value improvement do? Well, value improvement doesn't change anything about the policy. The important thing is that the update of your value function is done by optic composition. So this is the main idea of this talk and the title, which is that this update step is done by updating the value function and precomposing it with the policy and the transition, let's say the transition optic. We can think of this more graphically, where we just plug in the string diagrams together, and we see that given our data, we have this initial value function, and the composition of these three different optics gives you the new value function. And this, from the implementation side, we can think of this as an act of memoization, that is, composing these three optics and forgetting the internal structure, and just looking at this whole construct as just a function that goes from X to R again, which is our updated value function. In our case of policy improvement, we also have a similar map that, again, doesn't change the value, but does update the policy by choosing the argument that maximizes, the action that maximizes this composition of, again, this transition and the current value function. So what is interesting is that we've introduced not only lenses, but optics for a reason. The thing is that if you look at this transition function in the category of optics over mark conv, we can get the same algorithms, but for Markov decision processes, where now the transition function, or the transition optic, let's call it, consists of a forwards map that applies. You can think of it as here. You can apply the transition function, which may be stochastic, so it may live in the classical category, and we save this distribution of actions and states, and we can apply this utility function, and moreover the expectation, so the expected utility function, because in this backward category we are living in the Allen-Bemol category, so we can have this expectation map as the algebra map of our category. In this sense, we then again we sum the discounted value, future value, and then we update our value, that is the output of this here. So we can also think again of continuous space Markov decision processes. In this case, for example, the savings model, where you have this equation that we've seen before, and we're going to decompose it as the value improvement step and the policy improvement step. This value improvement step can be really described in this diagram, and recall that again the different notions here of what the functions are doing in the savings problem. In the case of stochastic maps, we can also think of this inside some Markov category, but I won't get into this too much. So lastly, one of the outlooks, or one of our things that we want to do is how to extend these formalisms to algorithms that are close to reinforcement learning. So the first thing is that we can shift our attention from learning these state values, that is functions from X to R, to state action values, that is functions that learn the value of both your states and your actions together. Recall that in regular value iteration, again, we have these two maps that we've merged together. So this is the policy update, and this is the value update or value improvement. And we can do the same with state action value iteration. So in this case, our state space consists of our policy and then our Q function, which is what is called the state action value. That is a function that learns the the values of pairs of states and action, and this is usually denoted by Q. And then we just again apply the same trick, which is composition of these optics. Note that we are slightly altering the order because we are first applying the transition, then our policy, and then our Q function, and then again the same step of memoization outputs your new Q function. But you can think of algorithms which are, for example, Q learning, where the focus is a bit different, because now in Q learning, the update that you do to your Q function is a bit different. You don't use anymore your transition and your policies, because in this setting you don't know them. In Q learning, the agent interacts with an environment and updates its function based on the experiences that the agent has, in the sense that this new Q function now is not a composition anymore of the transitions, because you don't know them. You just get the new Q function of a new state Q x prime that you obtain based on what the environment gives you. So you treat this the composition of like this structure as a black box. Well, this structure as a black box, and then this x prime doesn't depend anymore on a known transition. So there's also some interesting related work, in particular open dynamical systems by Just Myers, where we've seen that our formulation of value iteration can be transformed to a specific case of his MDP lenses, which are functor lenses of this specific functor, which I won't get into. But the important intuition is that we can transform from one to the other, and it works. Amazing. So it's not so important how you do the transition. It's just more of an informal visual way of emerging from one to the other. The important thing is that our case of this structure is that has an interface where the interface of the optics come from value functions, that is XR, to value functions XR. On the other hand, if we move these boxes around, we can transform this as a specific case of Myers MDPs, where you've got first a rewrite function, you apply a certain policy by closing the dynamical system on the right, and then you put everything here on the transition function. So this transition function compromises the utility, the discount, this F, and we see everything inside here. So in that case, we've got a different interface where now the interface is from current states to future states and rewards to outputs and inputs of an agent. The important thing is that we were interested in having the first formulation, because if you have both inputs and outputs of an optic being the same, this is exactly what allows us to iterate this algorithm. So maybe some summary and some future work could be that we can say that optics can be tailored to study different Markov decision processes. We've seen some deterministic, some stochastic cases, also some discrete space, continuous space, etc. But still, the last point of Q learning still feels a bit ad hoc, in the sense that, well, we've built this compositional structure of updating a value function, but then we say, no, just forget about it, just treat it as a black box and interact it with the environment. So we're still trying to build a framework that tries to encompass this in the by using this category cybernetics, and we're trying to apply also this this argmax operation inside the framework of optics. Moreover, we've seen today that we've especially focused on this specific case where you have an agent and we want to learn a specific policy, and we have also many states. But our goal is to expand this to other scenarios. For example, we can think of the scenario of having only one state, which is similar to maybe the bandit problem. We have only we have to choose between different actions, but we always stay on the same policy. And we can think of this third column where you have imperfect states, that is, the agent only being able to observe a partial description of the state, not having a perfect information, and that allows us to tackle more problems. For example, what I call these partially observable MDPs, which are a whole another field. And also another interesting thing is this first column, where we've got no agency. That is, or we can think of having only a fixed policy. And in this case, so the MDP collapses back to just a regular Markov chain. That is a sequence of states where there's no agent. We just have to learn what is, for example, the most probable sequence of states. And analogously, the case of having no agent being in the case of partial observable MDPs collapses to what I call these hidden Markov models. Lastly, the extension also that I've remarked about this black boxing in reinforcement learning has a big implication in what we're trying to do with this composition of optics. And we want to tackle this difference between what is a known environment, that is a known transition function, known utility that allows you to simulate this environment to get a more accurate value function, compared to pure learning, where you have no idea of what the environment might be doing, and you have to learn also this transition function for yourself. And lastly, also a comment about the problem structure, which different fields tackle with more or less assumptions. For example, in the field of control theory, or more specifically adaptive control, you've got a lot of constraints about your state space or action space. You can think of states and actions being vectors, and dynamical system being smooth, where you can linearize or you can linearize locally. And this allows you to say much more things about your system. But in the case of, for example, in dynamic programming, we've seen that we have to compose co-recursively and get an updated value function with maybe less assumptions. And even more in reinforcement learning, you've got, again, even less knowledge about what the thing you're interacting with. So this is all. I don't know how much time I've got left, or if we should. Oh, okay. Then maybe we should comment a bit. Well, we've got some. Maybe we can if there's questions, we can first answer the questions, and yeah.
Any questions?
Okay. Yeah.
Thank you for the talk. My question would be, can we try to do this exaggerate comprehensive in for algebra or
yeah, we've been thinking about this. I cannot give a full answer. Maybe Matteo in the next presentation has some answers to this more concretely. But we've been thinking of like, yeah, this description of iteration in terms of traces, but it's difficult to define this inside optics as an external thing. So yeah, we're still working on it. So yeah, are you thinking of maybe like building coalgebras over optics? Yeah, yeah. There are some results by Hansen which try to describe this convergence properties in MDPs, where if you describe this fixed point of being a specific map from a coalgebra to an algebra, but this is sort of the check of a final solution, that if you got a policy that is already optimal, we can check that it commutes, and then we say we're all happy that. But we don't have a way of like getting to that point, and that was maybe our focus of this building lenses, like very visually. Thank you.
Other questions?
So mine more of a practical question. So I was curious if you already have an intuition of what advice you in practice over classical RL algorithms. If it's mostly about conceptual clarity, or maybe you can systematically, because RL algorithms are a bit of a jungle, like you can have model free, model based, on policy, off policy, filters, running. Can you use this as a tool for taxonomy to become more ordered, jungle, or can you give you new algorithms that would be hard to come by otherwise?
So I will just sum up the question for the online audience.
Oh, sorry,
the
I
question
didn't repeat.
Is, what does this buy you in practice?
Yeah. yes, that's fair. So that is definitely one of our goals, which is especially like looking at these algorithms from a very compositional perspective, so that it allows you to talk about these different algorithms in a very nice setting. But for now, we haven't given back anything. We haven't proposed any optimized algorithm or anything like that. But it's definitely our long-term goal, I would say. Yes. Thank you.
Yes, if you go back to the diagram, the string diagram of the current formulation. Yeah. So yeah. So I'm sort of wondering what is your outlook on sort of possible further, not factorizations of this diagram, but like when I look at this, I'm yearning to put this into sort of, because now the forward part has copies and then an F, and the backward has some wires, and there's two maps, and I'm trying to sort of factorize it in my head and think about some higher structure that's happening there. What's your outlook, whether there is one? And yeah.
Yeah, I think the question was if there's way more there's more ways of factorizing the diagram to have more meaning of these different building blocks.
Some more meaning.
Yeah. So my feeling is that if one wants to look at formalizing, let's say in quote unquote formalizing some algorithms that are used in practice, it's very difficult to have this sense of let's try to build a framework where you can compose these different building blocks, because there's so many varieties of algorithms and new ways of breaking what your existing formalization might be. But it's definitely, I think there's definitely a sweet spot of trying to describe with string diagrams what these algorithms are doing, and especially this policy function, which it sits a bit just ad hoc here, but it's definitely something that might have a higher hierarchical role in this algorithms. Definitely, yeah. I don't know if that answers your questions. Or...
Yeah.
We have time for one more question. Well, thank you, Rio, again for the very nice talk.
Thank you.
Carlo? Good. No, spoiler. You butchered the delivery.
So for the next talk, we will have Matteo Capucci, who will tell us about a diegetic representation of feedback in open games.
Yeah, thank you, Jeremy. Thank you for the organizing this conference as well. Let me first make a premise. There is still not live note-taking going on statebox.tv. It's really interesting thing. So if you feel like going, thought I'd remind you that it exists. Anyway, so this is me. I'm sorry about the title, is really not good. I hope I will convince you that there's some like actual meaning to that. So as you see, like the meme abstract of this talk is the following. Like, well, you see like that's, if you were here last year, or better in Cambridge, you might remember these diagrams. Was presenting something called Open Games with Agency, and they are like the currently best version of open games. Woohoo. But they're still not as nice as learners that we have here, gradient-based learning. And I hope to convince you that we can fix this. So let me first remind you what we mean by a game. So a game is a very simple situation, very general, and is the study of interaction of independent agents and players who have some kind of interest and interact in an arena. So you can partition like a game system into two parts. One is the arena, which is sort of like the game board where things happen, where you interact, you play cards and stuff like that. And then there's the players that are doing something as well, right? And the idea that we had last year is that parametric optics model this kind of situations very well. So all these situations are actually called in cybernetic systems. And as you see, like you can say always that there is an arena, so a system where things happen. Over the arena, there is a system of agents, which is sort of like intervening and doing things in the arena. And everything can be then surrounded at will by some kind of environment, okay? So in the center, you have an open system, which is what category theory is really good at modeling. And then you can just close it and get a closed system. Brilliant. And you might see that learners indeed fit very well in this pattern, right? So there is, here you see this is a differentiable model, particularly F is such. So think of a neural network when I talk about this thing, right? So there is a function which is receiving an input and giving an output, and it's parameterized by some weights or parameters. And on top of it, there is what it's really the learner, in the sense that this is the part of this whole system which is actually learning, like, right? The model is not doing anything. The model is just like a way to use what I learned, okay? Think of the body, which is the way I enact my changes, right? But what's like the part with agency is the one above. And then given such a model, so this is neural network, think of this gradient descent, and then around it, I can plug some like training data and a loss function here. And then I run this and everybody's happy. And you see that the colors match, amazing. But if we go with games with agency, which is again what I was presenting last year, well, this kind of fits, but it breaks down really because there is no morphism in the vertical part, right? And if something category theories know, those are morphisms are the good part, right? In particular, they embody systems, whereas objects, and this epsilon here is a decoration on the object, they're kind of dull and they're not really doing anything. So the moral of this is that it turns out that, well, okay, you can model game theory like this, but you're doing that extra diegetically, which is a hard way to say we're doing it externally, in the sense that players do not take part in the story, okay? So this system is really telling the story how the game is played, but it's not telling the story how the players reason about the game, right? Which is sort of like what game theory is about, actually. It's not about playing the game, it's about reasoning about the game. So in this work, I'd like to explain to you how I think this situation can be fixed and how this is actually a very conceptual story and tells us a lot of things on how learners exhibit this diegetic agency. So how come there is a learner in a learner and there's not a player in a game, and how reasoning about learners will tell us something about games. And we'll see that this will give us like a very interesting set of structures and a very interesting idea of what is the difference between games with agency, like 2021 model and the 2022 model. So let's start with learners. That's the thing we understand, or at least I understand the best. So the question I want to start with is, why is this not a learner? What?
So maybe how do I read this? What does it do? What's it do?
Yeah, let me tell you. So, well, this is a string diagram, and in the category smooth spaces, and you see lenses is smooth spaces actually. And you see, so here we have a model, okay, which is computing something, and this is the loss function. We have training data coming in. We have a label for the training point, which is parameterized in the loss function because the feedback we're receiving depends on how well we did. Okay, so this is supervised learning. And then we get a loss, and you can say, well, the learner is something that inputs a parameter. Okay, so it's a way I think I should play this game and gets out a loss, right? But it's actually not what we're interested in, okay? Because this is the model dynamics. This is what happens when we run the model, but this is actually very dull because, well, how do we get the model? So what we're really interested in is the training dynamics, right? So you see, we changed the diagram. So now there's no R wires anymore, but there is this T star thing, which I will explain in a moment what it is. It's usually what is called the gradient, okay? And you see, we don't have a loss anymore here. We have the differential of the loss. And this is telling us something. This is telling us we're not describing the actual dynamics of the learner, of the model. We're describing some kind of counterfactual dynamics. Why is it so? So let's think about what the differential of a loss is. So the differential of a loss, so imagine we have a loss defined on Y, which is a smooth manifold. And smooth manifolds are a thing called tangent spaces. You can think of as in giving an infinitesimal neighborhood to each point, which is the neighborhood of points which are infinitesimally close, or directions I can go to. And the differential of the loss is giving a linear function, also a kind of plane, over every such space of vectors, okay? So why is this a counterfactual evaluation? Because this is telling us how much would the loss change if I were to move away from the current state, which is Y, in a given direction V, which is a tangent vector, okay? So it's not evaluating what I'm doing, it's giving me a way to evaluate all the things that I could have done, right? So this is interesting. And it's, oh, well, also, this is called a covector, and this is T star Y. So this is called the tangent bundle. I think Pietro told us a bunch of things about that 2 days ago. And so if you see T star, think of, oh, this is kind of like a differential over Y, all right? And the cool thing is that this is functorial in the sense that if I have a map from smooth manifolds going from X to Y, then we have a derivative going from the in the same direction, but between the tangent spaces, which is telling us what is F doing infinitesimally close to each point. Okay, so what's the linear approximation of that function? And now, of course, if I have a function like this from Tx to Ty, and I have a function from Ty to R, then I can compose them and pull back dl over Tx. Okay, so T star is functorial, but it's contravariant. Okay, so it pulls back evaluations. And that's why backpropagation is called backpropagation and not forward propagation, right? Indeed, this is functorial, and I'm going to represent the action of this functor like this. Okay, so given a map, I'm gonna like have a backward wire going the other direction, which is computing this pullback of a covector or reverse derivative. This is what a reverse derivative is. And the idea about like doing learning the way we do here at Glasgow is that this stuff should actually be parameterized. So this is the parameter of our model. We can still differentiate our parametric model. You see there's still a reverse derivative here. But what happens that the update for the model, so the evaluation for the parameters and the evaluation for the rest of the learner, think of this as a layer, so there's more layers here. These have to be separated at some point. And therefore, we have to use a monoidal structure on T star, okay, which is telling us that evaluation on P times X, which is the input of F, is the same thing as evaluation on P and evaluation on X, okay? And this is invertible, so it really means it's the same thing. Now, once we have this, we have built what I call an arena. So this is modeling backpropagation in a model. So I do the forward pass here, and then here I have gradients coming in. And what happens above? Now, above we have an interface, which is parameters coming in and evaluations coming out. What we really want to do when we do gradient descent is to transform these gradients or differentials in a more precise way into actual updates of vectors I can move along to, right? In this sense, a learner or a gradient descent lens is a system of this kind sitting on top of the arena. And there's a bunch of differential geometry for who's interested. So what's the recipe now to build the model of a gradient-based learner now? You start with a model, which is something like this, which is, okay, again, a parametric differential function. Then there's losses, which flow trivially around. Then we apply parity star to differentiate the model and get the backpropagation dynamics of the arena. Then we put a learner on top. And then if we're really feeling like running this thing, we can even add a training apparatus, okay, which is a loss function, which has been already differentiated, and training data, right? Congrats, you have a learner. Now, we want to do game theory, remember. I would you into this, but so what did we use to do this? Can we imitate this for games? So remember how the differential arisen. It's evaluation in real numbers of possible changes from a given state. Can we abstract this structure for games? I say yes. So let's start with states. This is going to be a bit difficult. So states for learners are points in a smooth manifold, right? What are states for games? So think of yourself as in playing a game. At each given moment, you have a set of moves you can make and a set of payoffs you can expect to ponder about, okay? Things you can expect to get back. Could be like cows, it could be money, it could be I won or I lost, something like this. Okay, so it's a pair of things actually. And you might say, well, these are category of lenses, but I would argue that these are also category of lenses. That's why I was drawing this trivial backward wire before. There's a geometric reason for that. But anyway, this is smooth spaces. Changes over smooth spaces are tangent vectors, but changes over games are called deviations and are really trivial because in principle, if I'm playing something that I could ponder about playing anything else, right? In the simplest case. So the change from a given state could be any other state. Then about the values I can ponder about, well, it's losses for learners. So at any given moment, the learner is expecting a loss back, which is one real number. Whereas for games, as I said, it's expecting a payoff. And then a loss map corresponds to a payoff map. So this is a map between states and values. But when we differentiate, we get a map that given a state gives us an evaluation of changes in values. So a counterfactual evaluation of my state. And the same happens for games. So there's two ways to do this. If your R is nice enough, you can talk about regret, which is a very popular notion of feedback for things that do things. In which case, given a Y bar, I get a function that gives me the increment I could get in payoff if I were to play a different state, right? A different move. Or otherwise, if R is not good enough, you can just be the constant function and say, well, at every state, the evaluation of that state is given by the utility function, the payoff map. And here we can read off what are the evaluations. So what's the correspondent to a covector here, which is this part of the function, then it's going to be that part of the function, right? So a payoff map. So what's the idea behind this? So again, it's the difference between an actual dynamics in the game, which is like what you would see if you were looking at the situation of people like actually playing things, which is described by like Open Games 1.0. So where you have like this lenses with maybe parameters and that model like the dynamic of moves and the dynamic of payoffs. So you take that and you sort of like differentiate it. So what you're really interesting in is what happens in the little heads. Okay, and what happens in the heads is something like this, where players are playing but counterfactually. Okay, and so the system of players is going to be sitting above this counterfactual arena, and there's going to be a functor that promotes a node-style game into an actual dynamical system that represents not the game dynamics, but the strategic dynamics. So how players actually play and decide how to play and make different moves. So this is now the hard math. It's going to be a bit fast, but I hope you follow. So this is still what we did for learners, okay, but a bit more bizarre. So now we're taking a game, so think of a model, and we are differentiating. This backward part is simply a map that gets an evaluation, a counterfactual evaluation, which is some kind of utility function, precomposes it with the game function, and return the new evaluation here, right? So we've seen this in Reustalk. This is backward induction or value iteration or Bellman something. And well, something to notice is, again, like remember the strong monoidal structure of T star was very important before. And so is the monoidal structure of this functor, which is not strong anymore, it just lacks, okay? Why is it lacks? Because if I'm given a pair XS and a pair YR, then if I apply the functor and then I multiply and then apply, or if I multiply and apply the functor, I get two very different things. But crucially, since we are in lenses, this is actually something we can compare. So this is what I call the initiator. So here you see like the forward parts are the same. So we can simply use the identity, but on the backward part, I remember next time Y, I get a joint evaluation, and now I'm going to take marginals and split. So you see, like I use the two values that I got, and I fix them in each of the two components of U, right? In this way, I propagate just the part of the evaluation that I think other players will think about, or the rest of the game can vary. And again, this is crucially definable in lenses only. So this is some kind of lax monoidal structure for the covariant home functor, which is not definable in general. It's definable if you land it in lenses. So we can apply par again to this functor, but now since the functor we applied to is just lax monoidal, then we're going to get a lax2 functor, which behaves in the same way. So apply here the derivative, and then I split using the lax monoidal structure. Okay, so it still kind of works, and it shows me something important. This is why I'm so passionate about the initiator. It shows me what's the difference between players competing, which are like composing their arenas in this way. So each of them gets their own like set of counterfactual evaluations, versus players which are playing together, which are still playing two different strategies, but they get a joint counterfactual evaluation. So they can evaluate to deviate jointly from a given strategy, and this gives them competitive advantage. But the initiator breaks the coalition canonically. So if I apply an initiator here, okay, this wire is backwards, should go up. If I apply the initiator here, I marginalize the two counterfactual evaluations and now get individual evaluations, and I break the coalition, and the players are forced to compete now. They cannot collude anymore. And this is also, since the initiator is natural, this is equivalent to the game we had before. Okay, so the initiator is really breaking players. Now, long formula. What I want to say is that initiators, so this thing we do here, and lens composition make so that we exactly reproduce backward induction in games. So the compositional structure of the game theoretical analysis on some kind of extensive form, it's precisely this, which I find incredibly beautiful. You can stare at this for a while and realize this is actually what happens when you input a strategy profile in this wire, turn the crank, and get two utilities out here. Now, can we see players as systems now? Did we solve the original problem? Well, we start with an arena like this, and you see I can put on top now a lens which is completely analogous to the one we had for learners. So it's something that converts counterfactual evaluations to deviations, okay? And indeed, a morphism of this kind, if we think that blue stuff is possibilistic, so non-deterministic, a morphism of this kind is what is known as a selection function, which is what we were using last year to do game theory, and I'm still using this year because it actually embodies, like in a very general way, what does it mean for a player to have a preference? And I argue it means for them, given a counterfactual evaluation, to choose what is the thing they'd like to do, okay? And so the recipe is now the following. We start with a game dynamic. So this is describing how the game is played. Like this is the manual you get in the board, like with the board and the pieces. Then we differentiate it using para star to something that does the counterfactual dynamic. And then we add the players on top. And then we close with a context, which is given by an initial state, which is called nature's move in game theory, and a payoff function, which has been differentiated using something like regret, right? And tada, we get back a game, which is a coalgebra to answer by Roman Mario's question. It's going to be a coalgebra for the P functor. Or we can also just like not close it because we are in category theory, we like to compose things. And when we put those two things together, one can prove that you recover exactly what you had to recover. So you recover a player on top, which is the Nash composite of these two players. So the Nash product of these two selection functions. And that's pretty much it. So there's a bunch of conclusions I'd like to talk to you about because this opens a lot of avenue. We've seen how to think about the geometry of learners. We see this idea that like many systems can be actually broken down in a thing with states and changes I can compare, values and valuations. There is, from this situation, we get reverse mode derivation functors, which are these functors from the category of states to a category of lenses over this with some kind of backward part in values. And we've seen then a shader, which is amazing. And ta-da, this is the new version of open games, which I call diegetic open games, because finally we have players. We have backprop, we have compositionality, we have Nash shaders. It's amazing. Some future directions, because this opens a lot of avenues. So the first thing we can do is vary the geometry, right? So instead of talking about sets, we can talk about differential spaces, we talk about measurable spaces, we can talk about what your preferred category of spaces, and do different kind of game theories. So for example, evolutionary game theory, which is really interesting. We can also vary the section, like instead of using star, we can define a different functor and obtain something like value iteration. But most importantly for me, this new approach is like pinning down the dynamics of the game that we're interested into. So we can now treat a game like a dynamical system of a certain kind, is a cybernetic dynamical system. And I've been developing like an extension of J.V. Jesmeyer's categorical system theory, in which you can talk about behaviors for these functors. And you see a little hint here. And you can prove that Nash equilibria are now behaviors as a certain kind of this diegetic open game. So equilibria are not like a thing you put on top now, as we did before, but it's something you extract later in a canonical way. And you have all guarantees about compositionality and everything from like general abstract nonsense that we all love and like. And finally, this like triple thing, state changes and values, I think extends David Jesmeyer's like idea that dynamical systems are given by state and changes, and allows us to think what it means to promote a dynamical system to a counterfactual dynamical system. So a system that it's been analyzed by some agent instead of being like interacted with by some other system. And this is it. Thank you for listening.
So thank you very much for the talk, Matteo. Are there questions? We have time for maybe one or two. Yeah, okay.
Still confused.
I'm sorry to ask this question so many times, but what are these diagrams? I guess you intend them to be cells in some double category. Do you know which double category?
These are diagrams of optics, basically. But like you're puzzled. Are you puzzled by? So maybe I should repeat the question. The question of chat is, what are these diagrams? Let me get an example of a diagram, like here. Maybe here is a bit bigger. So yeah, this is basically a diagram of optics.
No, it's not. It's by far.
Give me a moment to answer. This is basically a diagram for optics. You have to realize that like you can topologically move this horizontally. So you know that this is acting as like a tensor as it should be. Or you can see it in a different way. For example, you can see it in some kind of double category as the one you constructed, in which you have in a vertical direction, you have residuals going on, and in the other direction, you have states and stuff like that.
So is it correct that the way I should see this is by moving everything to the left or to the right?
Now you should like rotate the top part. That's, I think, the easiest way to make this like sound and correct. Okay, okay.
So maybe one very quick question.
Yes.
Hi.
Sorry, I brought the mic. Can you go back to the slide there? Yeah. Well, actually, first of all, I really like this talk. I feel like this is
Thanks.
for this whole week. But for with respect to number one, have you thought about like because it feels like you need like something like a tangent category or like something to like do this like tangent space cotangent stuff on? Like, I've thought about like what kind of accidents you need to do
Yeah.
this, right? Like,
Yeah, that's a very good question. I thought about that question a lot. Oh, sorry. Yeah. So yeah, Nelson's question is, have I thought about like what's the axioms or general structure that I would require in a tangent space, quote unquote. And yeah, since you're asking this question, I know you're kind of thinking about polynomial comonads, and yes, this is what I'm thinking about too. But they are not like general enough in the sense that, for example, I don't know if you actually need a composition operation. So I'm more like you need something like a reflexive graph of some kind, an enriched reflexive graph. So you know you have like the zero change, and you have changes that go places, and you can consider where they go. But you can do something less. Like you might not know where they go, but you might consider like a notion of trajectory in it. That's what you need actually. So you can say, well, a trajectory in it is something that is tangent always to something I gave you. So I have something like generalized vector field, and a solution for it is something that at every point has a differential, so a change, which is exactly what is prescribed by the vector field. So you need something like this. But once you are here, then your structure is in a sense too general, because like any section of the view vibration, and I'm not explaining what this means, but it's basically good enough if it's lax monoid.
thank you.
Okay, let's thank the speaker again. I think the next talk is online. You share your screen.
I can't. It says host is.
We don't hear you.
Screens. Hello, can you hear me? Oh, cool. Okay.
You should be able to share your screen, but we still don't hear you.
Yep. But you still can't, because Mike gave me thumbs up to say that he can hear me. Maybe the sound issue is on your end. So you can't hear me.
Still nothing.
Okay, check in the chat.
Are speaking now?
Hello, hello.
Yeah, that works.
That's better. Cool. Okay. Awesome.
Okay, so our next speaker is Matteo de Meglio, who will talk about universality of asymmetric lens proxy pullbacks. Thank you.
Thank you. And thanks to the organizers for giving me this awesome opportunity to talk to you today. Now, I was very excited now that I live in Edinburgh and not Sydney that I'd be able to give this talk in person and meet you all in person and all of that. But, you know, COVID sucks. And here I am in my house in Edinburgh, rather, over there in Glasgow. Nonetheless, I'm very happy to give you this talk. So universality of asymmetric lens proxy pullbacks, what's that all about? Well, these asymmetric lenses that we're going to talk about are the same as the ones that Bryce talked about on Tuesday, these delta lens things. And these proxy pullbacks are about describing the composition of spans of these asymmetric lenses. And this comes up in applications when you want to model composition of these things called symmetric bidirectional transformations, which I'll tell you about in a minute, but they're really just about modeling like synchronization of systems. But the point of this talk is, okay, these proxy pullback things, they're kind of defined in an ad hoc way, but we want to understand the sense in which they're canonical. And in category theory, we usually turn to universal properties for that. But I mean, they don't satisfy the universal property of a real pullback. So, but we will see they satisfy I guess, a weaker universal property, but more on that in a moment. Okay, so what are these symmetric bidirectional transformation things? Well, I'm going to give you an example. So we're all familiar with the Messages app on our phone, and we could imagine the kind of data structure that the Messages app uses to store the data that's relevant. So here's a very simplified idea of what that might be. You know, for each person that you're messaging, you might have a list of messages and the direction of those messages. And the app interacts with a server, which also, I mean, we could imagine stores the messages that are being sent and received, but perhaps in a different format, because I mean, okay, well, it's going to have to remember who, not just one person, but both the person a message is from and a person the message is to, and things like that. And the process of sending and receiving messages could be viewed as keeping these two data sources consistent with each other. So if I send a message on my phone, it should appear on the server. If a message on the server to Matt appears, then it should appear also on my phone. And so this is an example of a bidirectional transformation. You have two systems that you want to keep in sync with each other. The symmetric part is about the fact that neither of the systems is sort of the font of all knowledge. And I've kind of contrived the example a bit to make that work. So on the server, obviously, it's going to have messages that aren't related to Matt. But on the phone, this is the contrived bit. You know, we're perhaps going to have these draft messages where you've typed the message out, but you haven't pressed send, and it's going to sort of remember that, but that shouldn't appear on the server. So you can't derive the state of the phone from the server or the state of the server from the phone. So there's a symmetry in the roles of both of the systems at play. So that's what a symmetric bidirectional transformation is. Now, in the introduction, I said that we can model these mathematically using spans of asymmetric delta lenses. So let me tell you a little bit about asymmetric delta lenses. So an asymmetric delta lens F from S to V. So here S stands for source and V stands for view. So there's already an asymmetry in the two systems. The idea being that the states of the view can be completely derived from the states of the source. So we're going to model the source and view systems as categories. So objects think states, morphisms think transitions. So F consists of two pieces of data. So the first is this get functor. So for each object X of S, so each state of the source, it tells you what the corresponding state of the view is. So there already we see some asymmetry. And the idea is also, if I take a transition out of that state in the source, then the corresponding transition that should happen in the view is the image of that transition in F. So that's one part of the data of an asymmetric delta lens. The other part is this put cofunctor. Now the put cofunctor has the same object map as the get functor, but it has the additional data of lifts. So if we start with the source and view synchronized like so, and then a transition G happens in the view, the put cofunctor tells you what transition should happen in the source that would correspond with the transition in the view. So I'm going to use this notation F superscript XG to denote the lift of G to X. Now, obviously, the get functor and put cofunctor have to satisfy compatibility axioms with the identities and the composition, and they should also be compatible with each other in the appropriate way. So that's what an asymmetric delta lens is. Now, let's see the way in which these spans of asymmetric delta lenses model the symmetric bidirectional transformations. So here's a span of asymmetric delta lenses. The objects in the apex category of the span should be thought of as witnesses to the consistency of the states which are its image in the legs of the span. So here we should think of f of x and g of x as being consistent states. And if a transition happens in one of the systems, say in A, we can use the put of f and the get of g to get the corresponding transition that should happen in the other system to bring them back into sync. And obviously, if we had a transition in B, we could propagate it to A using the put of G and the get of F. So, okay, we can model symmetric bidirectional transformations using these spans of asymmetric lenses. And it makes sense to think about, okay, if I have something that's synchronizing systems A and B, and I have something that's synchronizing systems B and C, well, if I combine these two things together, I should be able to synchronize A and C. So this composition of symmetric bidirectional transformations should be able to be reflected in this composition of asymmetric lens spans. Now, in category theory, normally when we want to compose spans, we use some notion of pullback. So we take the pullback along the co-span in the middle, and then we compose the legs of the pullback with the other legs to get the composite span. And you'd hope that something similar would work to model this composition of symmetric bidirectional transformations. So let's see what we can do. So if we have a lens co-span FG like so, then we know that F and G have get functors, and we can take the pullback of their get functors in cat. So let's call that pullback G prime and F prime. And the question then becomes, can we put cofunctor structures on G prime and F prime that are compatible with these functors and that form a commuting square, and then hopefully what we get is actually a pullback and it all works out. So we can actually put cofunctor structures on G prime and F prime. So for G prime, if we have an object of the source category of G prime, which in this case is a pair of objects, A and B from A and B, that are both mapped to the same object in C, and I have a morphism out of the image of that object in A, then I need to say what it means to lift that morphism up to P. Now, the lens laws for G prime tell me what the first component should be. It should be little a. But the second component isn't really determined by the lens laws or the commutativity of the diamond, but there is an obvious choice of morphism. What we need to do is we apply the get of F, and then we lift using the put of G, and that gives us a morphism on the other side. And if we define the lift of A to be this morphism up the top, then it turns out that turns G prime into a lens. And we can do the same thing for F prime. And it turns out that these lenses make the diagram of lenses commute. And I mean, this is what Mike and Bob Roseborough told us about a number of years ago now. This construction really does model this composition of symmetric bidirectional transformations. The only thing is, it's not actually a real pullback. It doesn't satisfy the universal property of a pullback. I'm going to use the terminology proxy pullback to describe this construction, because it does have many of the nice properties of pullbacks, even though it isn't one. And this name comes from Bumpus and Cox's work from last year about the tree width stuff that they did at ACT last year. But I like the name, so that's what I'm going to call it today. So okay, we have this proxy pullback construction. I've already told you it doesn't satisfy the universal property of a pullback in general. But it's defined in an ad hoc way, but like we'd like to know the sense in which it's canonical. well, perhaps, okay, it doesn't satisfy the universality with respect to all spans that form a commuting square with the cospan, but perhaps there's some class of spans for which it is universal. And if we could understand this class, then that might tell us something interesting about what this proxy pullback is really about. So in other words, we're looking for a class of spans Kj such that there exists a unique comparison morphism L that makes the triangles commute. Now, if you sort of think about it and were to set off on this quest to find this class of spans, well, you might start by asking, well, if we know that this comparison lens L exists, what can we say about the span Kj? And it turns out there's two properties that turn out to be important here. So the first I'm going to call compatibility. So Kj is compatible with Fg. And the second I'm going to call independence, for want of a better name. Independence is the more mysterious property. So I'm going to tell you about both of these in a moment. But let's start with compatibility. So, okay, so I have this square of asymmetric delta lenses. And I mean, it makes sense to say what it means for this square to commute. So the get functors sort of give a way of taking morphisms in D down to C along the two sides. And so, and the put cofunctors let me take morphisms in C around the two sides up to the top. And commutativity of this square sort of says that the going either way, it gives you the same thing. But there's also, if we sort of look at the cofunctors and the functors together, I can lift morphisms along K and down along J and vice versa. And so compatibility is going to be the stronger notion of commutativity, where we're also asking for each object D of D and each morphism A out of K of D. If I lift along K and then apply the get of J, or I apply the get of F and the put of G, so that gives me two morphisms on the other side, they should both be equal. And also, if I did the same thing going the other way, then I should get equal things as well. So compatibility is a stronger notion of commutativity. And it's really saying that if we view the span Kj as a symmetric bidirectional transformation and the cospan Fg as a symmetric bidirectional transformation, then they act as the same symmetric bidirectional transformation. Okay, independence. This is the more mysterious one. So here I have a lens span K and J, and for each object D of D, and now we're going to have an alternating sequence of morphisms in A and B. Sort of think of it like, you know, I'm going to synchronize from A to B, and then a change happens on the other side and synchronize back. So I have a morphism A in A out of K of D, and I synchronize across to B, and then I have a morphism. So another change in B, and I synchronize back to A, and then I have another change in A, and then I synchronize to B, and I keep going. And I could consider another sequence of such morphisms out of the same starting state. And so if both of these sequences are the same in both A and B, so I'm asking that the diagram in A commutes and the diagram in B commutes, then the independence property says that the sequence of morphisms in D should also be equal. So the diagram in D should commute. Now, as I said, I don't really have like an intuitive idea of what this is actually saying if we interpret this span as a symmetric bidirectional transformation, but I'd love an interpretation that actually sort of makes this property make sense. But it turns out it is the right property. So I told you that both of these properties were necessary conditions, but it turns out under some additional assumption on the proxy pullback span, they also become sufficient conditions. So in other words, so this extra property I'm calling sync minimality. So if G prime F prime is sync minimal, then the proxy pullback G prime F prime is universal amongst the independent and compatible lens spans. And actually conversely, if we have this universality, then you can prove that G prime F prime is sync minimal. So the sync minimal thing is actually quite easy to explain. It's saying that every morphism in P is a composite of lifts from A and B. So we have this actually characterizes I mean, the universal property of this proxy pullback when it has one. So that's all I wanted to say today. So we saw that the sync minimal lens proxy pullbacks are universal amongst the independent and compatible lens spans. If you go see my paper, you'll see how this actually allowed a better understanding of when lens proxy pullbacks are real pullbacks. So this goes back to work that was talked about at ACT last year by me and Cholet et al. So Bryce and the ACT adjoint school group. And I should say that my approach to proxy pullbacks was inspired by that of Boom and Simpson when sort of looking at pullback-like constructions in other categories. So yeah, thank you for your attention.
Thank you for this talk, Matthew. So we still don't have an audience microphone, so it's going to be a bit complicated. Maybe if people online want to, oh yeah, yeah. Oh, okay, we have actually the speaker's microphone that can do that. So any questions?
Okay. Thank you, Matthew, for the talk. It was really nice. I wanted to ask if one has an implementation of databases using these lenses for synchronization, is there a way that we can find the proxy pullback when we are in some reasonable conditions? So my question would be, if I have an implementation of these databases and we have lenses that satisfy the conditions for this to be unique, can we construct it? Is there a way that we can find it?
I mean, yeah, I think so. So, I mean, Mike is probably the best one to talk about how these things are actually used in real world applications. But certainly, when Zinovi Diskin proposed the idea of delta lenses, both the symmetric and the asymmetric case, like the prime use case he had in mind was modeling synchronization of databases. So you might think you have two companies with databases and they're trying to communicate with each other. But I think, at least my understanding is, in practice, the lenses are used more as a model of actual existing systems that sort of keep two things in sync. I'm not sure whether there's actual software that allows you to concretely specify a lens in mathematical language and then turn it into a system that synchronizes two databases. I don't know whether that exists yet, but does that kind of answer your question?
Yeah, kind of. Yeah, thank you very much.
Other question? So thank you again for the very nice talk. We have a coffee break.
Is there someone around who? Oh, they are open. Cool. Okay, I'm going to move to the breakout room if anyone wants to come and break it. Is there a break? Oh, I can. Oh, I'm co-host, so I can do it. There you go. Let's see. Does this actually? Cool. Did that actually work? Yeah. All right, I'm going to move to breakout room 1. Anyone who wants to chat can move there too.
Yeah.
I don't want this.
Okay, welcome back everyone to session 2 of today's ACT conference. I'd like to introduce Malin and Altenmüller, who will be talking about the category of surface embedded graphs. Thank you.
Thank you. Yes, so as Priyaa said, I'm going to talk you to you about a surface embedded graph and why they're interesting. This is a thing I've been thinking about with Ross, and we're still thinking about it. So why should you care about graphs in general? You'll have seen lots of string diagrams over the last couple of days. So we like string diagrams because they're syntaxes for monoidal categories, which we also like. And then if you want to implement a rewrite theory for monoidal categories, you need some form of combinatorial representation of your string diagram. And that's usually done by some form of graphs because it looks very similar. So this is where we're interested in graphs. And just kind of a quick disclaimer. So what we're going to do is that in our graphs, the vertices represent the generators of the category and the edges represent wires. Specifically, identities are just going to be edges, so no vertices involved. And then why should we care about surface embedded graph? Well, sometimes in your monoidal theory, you may want non-trivial topologies. So like non-symmetric monoidal categories is one example where you don't have a crossing. And the kind of typical example is quantum processes where crossings are expensive. So we can't just build them into our theory. We need to like kind of do something more with them. And I have an easy example here as well of a graph which is embedded into a surface. And we see that, so it's the same graph, right? The sets of edges are the same. But on the left side, so on the right side is a planar graph. So it can be drawn without a crossing. And on the left, it's non-planar. And we're actually going to work at the level of the embedding. So in our representation, these are two different things. And then we use topology to tell us how to actually encode an embedding in graphs. And what we're going to use is rotation systems. So if you look at these two examples and at this vertex at the bottom there, you see that the order of edges around the vertex is different. So that's what makes a graph embedding. And there's a theorem which says that rotation systems actually uniquely determine a graph embedding onto some surface. And our plan is going to be to construct some category of graphs with some specific properties, and then afterwards add this rotation information to each vertex. And we want this kind of second step to be quite easy by doing all the work in the first part. Okay, and what we want to do with this is we want to implement rewriting strategies for diagrams. They're usually done by this double pusher construction. So you start with a rule. I can probably also use the mouse. You start with a rule at the top. You want to rewrite a left subgraph with a right subgraph. And you have this B in the middle, which is kind of the common boundary of your subgraphs you want to exchange for. And then you have this map here, which embeds the left-hand side into a bigger graph. And then in the middle, you have this kind of graph you started with a hole, so with L removed, and then that's where you can plug in your right subgraph. Yes, so actually I wanted to do this. So a left subgraph, and then this is kind of G with L removed. But if you look at this left-hand side of the diagram, if you give this kind of context like G with a hole a name, then you can also view your left graph as G with the context removed. So it's kind of an interesting hole, so which is kind of the outside hole. Okay, and for this, what we need our category to have is push-outs, because we want to do this double push-out construction, push-out complements, because we want to compute this context graph, and some notion of embedding, because all of these arrows are kind of graph embeddings into bigger graphs. Okay, and we start from the kind of usual category of graphs, which has a set of edges and a set of vertices and a relation of a source and a target vertex for each edge. And then morphisms are pairs of an edge map and a vertex map, such that everything kind of works out. And I have a disclaimer, so I'd say it's source and target, but actually all the pictures I'm going to draw are undirected because it's just easier to look at. Okay, so the main problem with graphs embedded on a surface are inputs and outputs. So like diagrams definitely will have inputs and outputs, right? So somehow we need to encode this in graphs. And there's different approaches. It could be open graphs, so kind of dangling edges, or we can represent each dangling edge with a vertex, or we can do some of these co-span constructions we've seen earlier in the week. But none of those really serve what we want, because whenever I view my edges separately, if I have a graph morphism, that doesn't preserve the surface necessarily. So this is a problem. What do we do with this? So we can't have inputs and outputs kind of dangling around, and we can also not look at them individually. So our approach is, let's identify what's the outside of a graph, and then we kind of identify this as a region, and we attach all the loose edges onto this region. So this is a different way of drawing this. So I have this region with edges attached. And then we're going to represent this outside region by a special vertex, which is called the boundary vertex of the graph. So which it has all inputs and outputs nicely attached to this. And this gives us total graphs. So everything, like the graphs are all total, that's very nice. And also we can actually deal with these outside connections, but also we can deal with any sort of hole in a graph as well, because any hole in a graph also has some loose edges. So we can do the same trick with any holes in the graph. But having this kind of special representative vertex means for our morphisms, we need some specific requirements. So, okay, well, ignore this bottom thing. What if we want to now embed a graph into a bigger graph? So we want to replace our kind of, so we want to add something to this outside region. Because this outside region is represented by a vertex, we need to be partial on the vertex map, because we want to replace the vertex map to something bigger. So all things need to be partial. And then the other thing is, what if my kind of outside region is an identity or a cup or a cap or something like this? Then we have maps like this, which means we definitely cannot be injective on edges, because we need to be able to join edges together. And then more requirements. So because vertices represent generators, they mustn't change their arity. Like vertices always have to have, if they're mapped across, they need to keep all their edges attached to them. And then we have another thing. So because we also have loops in our system, so we can do something like this. We can forget a vertex and map the edge into a loop, but the other way around, we don't want to allow. Okay, so to get all these kind of requirements on morphisms, I'm going to introduce you to flags, which is the structure we're going to talk about, which are the connection points between a vertex and all the edges attached to it. So it's kind of a pair of a vertex and an edge. And then a graph morphism, so an edge and a vertex map, induces a kind of flag map by mapping. each of the components of the pair. Yes, so something like this. And it's partial, right? Because if we forget a boundary vertex, potentially, then we also are partial on flags. And then this flag map, this is the thing we talk about, and we use specific properties of this flag map to characterize what a morphism in our category is and what embeddings are in this category. So let's look at that. So we have as objects total graph as defined above with this boundary vertex. And morphisms are pairs again. And for the category morphism, we ask the flag map is what we call surjective, which gives that flags at a vertex, the number of flags at a vertex cannot increase. And that's a category. And then we also characterize what embeddings are. So further to these first conditions, we have that the flag map also has to be injective, so that we don't have a decrease in flags at a vertex. And this is a category. Ooh. Okay, so let's do rewriting in this category. So we have a lot of conditions here. So it's not a very well-behaved category. So talking about rewriting in a kind of general sense, it's not very good. So we're going to restrict the case in which we want to rewrite to exactly the useful case. So we're starting with this. So remember, we have this boundary in the middle of the DPO diagram, which is kind of the common boundary of the left and the right-hand side of the rule. So we're going to define exactly what type of graph this boundary has to be. And it's this. So we have an outside, which is represented by this boundary vertex here. So these are kind of equivalent, but sometimes it's better to imagine one way or the other. But then also, we want a hole because we want to actually rewrite something. Or we actually want to define the context as well. And the whole is kind of represented by this dual boundary vertex. So you have these pairs of boundary and dual boundary vertex. And the important bit is that they're connected with some set of edges. And then the thing we exactly want to rewrite is spans, which we call partitioning spans, because they exactly partition a graph into two parts. The first one is this kind of left-hand side of the rule. So this is kind of the left-hand side of your DPO diagram. So you replace the dual boundary with some graph. So you replace 1/2 with a graph. And then on the other side of the span, you replace the other side. So you replace the boundary vertex with a context graph. But because they're connected, means that you can't really do anything with the edges, right? They're going to stay the same. And then the first really nice result is that pushouts of partitioning spans exist, and all of these morphisms are actually embeddings. So for partitioning spans, we ask L and C to be embeddings, and the maps into the pushout then also happen to be embeddings. Okay, so pushouts, that's nice. So what about pushout complements? So now what about calculating this kind of context? So we have a kind of equivalent or kind of counterpart to partitioning spans, which are called boundary embeddings, which is going to be the input for constructing the complement. So we start with a boundary graph again, and now we first have replaced the dual boundary with a graph, and then we replace, so it's kind of a composite, then we replace the boundary vertex with a graph, and that gives me the total graph at the bottom there. And then from this, I can, and this is the second nice fact, I can actually construct the pushout complement from these things. And these are unique up to some degeneracies. So having these two things, we can actually do a rewrite. So for example, this is a rewrite rule with a boundary graph in the middle. And then we also need to know this embedding of my left-hand side into a bigger graph. And then we can compute the pushout complement. And afterwards, we push out to the right, and then we get the rewritten graph. Okay, yes, so we have this category of graphs. But so far, I mean, I've drawn these things in a specific order, but so far the edges are only sets. So, but we can now add rotations or rotation systems on top of this graph category. So rotation systems are kind of these graphs, but in addition, we assign a list of edges to each vertex, like a cyclic list. So that means the edges are ordered. And as we know from before, this rotation for each vertex determines an embedding. So we're actually talking about embeddings. And then morphisms for rotation systems are the same as in the underlying category, plus a preservation condition on these list things as well. So a bit like a surjectivity condition on the lists. Okay, and then the really nice thing here is that we've done all the work in the graph category, so we don't really need to do much more here. So pushouts and pushout complements are actually the same than as in the underlying category. So this is really, yeah, we really did all the work earlier. Okay, so this is the kind of general thing. So now we can do rewriting with rotation systems, which means rewriting with surface embedded graphs, which is very nice. So now I want to talk to you about a kind of bit of an odd case, which made us think about surfaces. So given this, which is a boundary embedding, so I have some edges, and here I have some like connecting edges together. So this could be identities or cups or caps or something. And then this gets pushed out into a loop. So no vertices, just a loop. So now how do we construct kind of what's going on inside here to get a loop, right? And there's a solution, which is this, so kind of pairwise. Also, I've drawn these directed now. Yes, full stop. This is directed graphs, but that means you only have so many choices of connecting edges together. Okay, and this, if I construct the pushout of this, that's actually a loop, which is kind of a little bit like this, but it's plane because both sides are plane as well. But now if you think about this problem, there's also a different solution to this, which is this, which looks a bit odd. And if we like construct the pushout of that, it looks like this. And it's not very plain. Like there's even loops, like this is not a plane loop. It's not also not planarly drawable somehow. And so this is a thing where rotation systems kind of fail, right? Because rotation systems only work if you have a vertex, but you have your loop, you don't have a vertex. So you can't really say anything about loops. The nice thing is that we can say something about loops because we know that this is not going to be plane because this half is not plane. So yeah, there's a bit of a bit more thinking to do here because yeah, what do you do with this situation? And we have a conjecture that there's actually only ever going to be one plane solution, but this is only conjecture, it may not be true. And yeah, so kind of constructing this complement, maybe you could restrict your rewrite rules to something that definitely has a plane solution of your complement or something like this. So there's a little bit more thinking to do about loops, but this is a very degenerate case, right? We do need to think about loops, and actually we have to think about them quite a lot, but they're not actually that important in your theory necessarily. But yeah, there's definitely also more to think about here. So take home messages. Number one, if you want to do topologically interesting things, you need to fix any dangling edges like all together, not just individually. And if you have a category which is not very well behaved with pushouts or double pushout rewriting, it makes sense to restrict your rules to very meaningful cases, like this thing of a partitioning span. That's actually the interesting case we want to consider. And yeah, I showed you that we construct this category of graphs with circles, which is quite easy to extend it to rotation systems because everything is fixed into vertices. And then yeah, future thoughts. One of them is what to do with these surface embedded loops. How does that work? And the other one is how about like not just having one boundary vertex, but more than one? What does that even mean? Does it have any, yeah, what is in there? There may be something in there. And that's me. Thank you very much.
Thanks, Malin, for the talk. Are there any questions?
So when you've been saying surface embedded, it seems that when you're saying surface, you're meaning planar embedding as opposed to being able to embed in any 2D surface. And I was just wondering if you'd given a thought as to how that changes, because the class of graphs that is embeddable in a 2D surface depends on the surface, like the
Yeah, so rotation systems actually don't only work for planar things, but also for higher genus surfaces. And there's even a version of rotation system which work for non-orientable surfaces. So the kind of easiest example and like best to draw is plane things, but this is totally works for higher genus surfaces as well.
This was really cool. Thank you.
Thank you.
Have you thought about like formally relating like this category to a symmetric monodic category or one maybe with like caps or whatever? And like, is there some fun period there that will actually like get you something about like these diagrams and then actual string diagrams that come out of that?
So, I mean, we are trying to like actually implement this string diagrams for categories, right? Monodic categories. So yeah, there's like a translation then. It would be a translation from a string diagram into your graph, which is your combinatorial structure, and then you can do all the rewriting. Like you can translate the diagram rewriting into graph rewriting. Is that what you mean?
I guess what I mean is like it's a function there, right? Like from some like symmetrical monodic or like from categories, symmetrical monodic categories to like something I don't know exactly what it would look like, but like you can still put that in a categorical setting, like that translation.
Maybe.
Okay. Spirits.
One more question.
So if I take the planar embedding of the loop, say, is there a difference between one string crossing over another one and under another one?
Yeah. So there's a whole thing. So there's also like a whole thing in computer graphics actually about this on when is it the same thing, when do you need a different level or layer. So yeah, there's different types of crossings. I think this is not the kind of normal form either. I think you can pull one of those out definitely.
Sure.
But yeah, there's different kind of this.
I think these are knots then, right? The planar embeddings of the loop are what people study as knots.
Yeah, I'm not sure, maybe.
Hey, let's thank our speaker again.
Thank you.
I think our next talk is online.
Priyaa, are you speaking for the next talk?
Yep. Yep, I'm ready.
Do you need to say yes? Okay, and now you should be able to share your screen, Priyaa.
Okay.
And we can hear you. Excellent.
Yep. Right. Please give me a moment. Share. Okay. Okay. I'm sorry. I have to quit Zoom and come back. Just give me a minute. Sorry. Okay. Is my screen visible?
Yes, it is.
Okay.
Okay, you ready for it?
Right. Hello, everyone. I thank the organizers for this opportunity to present our work at ACT. So today I'll be talking about extending monotones using Khan extensions. So in this project, we demonstrate an application of Khan extensions to resource theories, in particular, extending the monotones for resource theories. So resource theories model physical systems in which certain operations are considered to be free of cost among the set of all operations. So for example, if we place a glass of chilled water at room temperature, then the water warms up to the ambient temperature. So these transformations are considered to be free. And if to prepare a glass of chilled water, one requires non-free transformations such as a refrigerator, which consumes electricity. So another example of resource theories would be from randomness. So randomness is an essential computational resource that is of practical use. So it is used in computer algorithms to solve certain problems. And in cryptography, we generate random keys for secure communication between devices. So for such systems which utilizes randomness, the transformations which does not increase randomness will be considered to be free. And the transformations which produce randomness are non-free transformations. So one of the main goals of resource theoretic modeling of systems is to determine the existence of free transformation between any two resources. So if we can answer the question about the existence of free transformation between two resources, then we determine a pre-order on the resources of a resource theory. And this pre-order is based on the usefulness of the resources. Once a pre-order is determined, we can assign a value, a real value to each resource in the theory, depending upon their usefulness. And such an order preserving assignment from the resources to the real line is called as a monotone. An example of a monotone would be entropy, which measures randomness. So Shannon entropy expresses the average surprisal on the outcome of random experiment. Let us consider this scenario where a resource theory embeds in a larger theory. So for example, classical theories embed in quantum theories, or pure state quantum theories embeds in mixed state theories. So in this scenario, we can ask a question, if we have a monotone for the smaller theory, can that monotone be used to say something or quantify the resources that are exclusive to the larger theory? And this question arises from the observation that the resources that are exclusive to the larger theory can be converted to resources in the smaller theory, or vice versa. So the answer to the question is that it is not possible to strictly quantify the resources that are exclusive to the larger theory, but we can approximate the value of, we can find an approximate value of the resources in exclusive to the larger theory by computing the upper and lower bound on the value of the resources. So Gore and Thomas Michel, they provided a set theoretical framework for extending monotones from a subset of resources to the entire set of resources. So what they did is to provide based on their previous experience on working with resource theories, they provided a formula for computing extensions of monotones, and then they proved the properties of the extensions thus computed. And we find similar construction introduced by Gonda and Speckens. But our observation coming from category theory approach was that the monotone extensions that they computed are special cases of more general categorical concepts called pointwise left and right Khan extensions. So we take a reverse approach compared to physics. We first define the properties of monotone extensions using Khan extensions, and then let those properties determine the formula that should be used to compute those extensions. So for those who are not familiar with Khan extensions, I'll just give a brief overview. So given a functor f from a category x to d, and we can, if we want to construct a functor from y to d, given a functor x to y, we can ask what is information theoretically, what is the most conservative such functor that can be constructed from y to d? And the answer is the right Khan extension. Right Khan extension of f along k is a unique functor from y to d with the natural transformation going in this direction. And this natural transformation is universal. in the sense that if there is any other functor from Y to D with a natural transformation alpha from this composition to F, then that transformation should factor in this way. And similarly, for left Kahn extension, we ask the question, given a functor F from X to D, and suppose we want to construct a functor from Y to D along another functor K from X to Y, what is information theoretically, what is the most liberal such functor that can be constructed from Y to D? And the answer is the left Kahn extension. So the left Kahn extension of F along K is a functor from Y to D, but the natural transformation now goes in the opposite direction. And this natural transformation is co-universal in the sense for any other functor G from Y to D with the natural transformation alpha from F to this composition, that transformation should always factor through psi. So Kahn extensions are not always guaranteed to exist, but we can compute Kahn extensions under certain conditions. So whenever the target category D is co-complete, then left Kahn extension exists and is computed using the co-limit formula. So the idea is that for each object Y in this category, we look at all those objects that has arrows into Y from under the image of K, and the co-limit kind of chooses the object which is nearest to Y in D under the image of F. And similarly for the right Kahn extension, we use when the target category is complete, we can use the limit formula to compute the right Kahn extension as the limit of this diagram. And for this, we look at for each object Y, we consider all those objects under the image of K, which has arrows from Y into it. And then we choose the nearest object to Y under the image of F. So now that we know what Kahn extensions are, and I said like we want to set up monotone extensions as Kahn extensions, which means that we want to describe monotones as a functor. But to describe monotones as a functor, it has to be a functor of resource theories. And to describe functors of resource theories, we want to describe resource theories as categories. So the first step is to come up with a categorical description for resource theories. So here is the definition. So resource theory can be described as a partitioned category. A partitioned category is just a category X, with a chosen subcategory of free transformations, and the inclusion being bijective on objects. So this means that the larger category and the free subcategory has the same objects, but the transformations are the subset. So the objects of the category are interpreted as resources, and the maps are interpreted as resource transformations, and the maps in the subcategory are the free transformations. So this idea comes from Cooker, Fritz, and Specken's work on mathematical theory of resources. So here is an example. So this is a formal representation for resource theory of randomness. The resources are finite probability distributions, and the transformations are row stochastic matrices satisfying this equation here. The identity transformations are identity matrices, and the composition is given by matrix multiplication. So in this resource theory, the free transformations are those matrices which are deterministic, which means that the matrix represents a set function. So there are only zeros and ones, and every row has a single one, and the rest of the entries are zero. Okay, so the next step is to describe functors for resource theories. A functor for a PCAT functor is basically a functor between the categories, the large categories, such that the functor preserves the free transformations. So if we consider these two diagrams, these two shapes here as partition categories, as you can see from the transformations in the subcategory gets mapped into the transformations in the other subcategory, the free subcategory. However, the non-free transformations can go to either non-free or into the free world. And a PCAT functor is full whenever the underlying functor F is full, and it is faithful if the underlying functor is faithful. So now we can describe monotones as PCAT functors, but there is an intermediate step. So as I pointed out earlier, free transformations of a resource theory defines a pre-order on the resources, but every pre-order can be encoded as a partition category as follows. So given a set X, which is a pre-order, the larger category is the indiscrete category, where there is a single arrow between every two objects, and the objects of the category are given by the elements of the set. And a transformation from A to B is considered to be free if it respects the pre-order. So this is a pre-order encoded as a partition category. And now that we can encode a pre-order as partition category, we can now encode the information about the existence of free transformation as a pcat functor. So given a resource theory and a pre-order on the resource theory, a pre-order collapse is simply a partition category functor from the resource theory into the pre-order category. And finally, a monotone is simply a pre-order collapse onto the real line. So as I have pointed out here, M is a monotone for resource theory X, and this is a partition category functor. And what this says is that if F from A to B is a free transformation, then the cost of A is lesser than or equal to the cost of B. But this is a little bit absurd, because if I can convert A to B freely, then A should be lesser expensive, right? So the notion of op monotones are more frequently encountered in physics. So the op monotone just says that it's a contravariant functor and contravariant pcat functors. It says that if F is a free transformation from A to B, then the cost of A is at least as high as the cost of B. So here is an example of a monotone. As I pointed out earlier, Shannon entropy is an example. So we can construct a functor Shannon from the resource theory RAND onto the real line, which assigns for each finite probability distribution its Shannon entropy. And it's easy to verify this is a monotone. So now we have all the pieces that we need. We have described monotones as pcat functors. So now it is straightforward to describe a monotone extension as Kahn extension of that monotone along another pcat functor. So for that, we first observe that a monotone is always concerned only with free transformations. So in order to extend a monotone, it suffices that we focus only on the free subcategory. So with this information, we have two definitions. So the minimal extension of a monotone M along a functor K is the right Kahn extension of the monotone along K only on the free subcategories. And similarly, the maximal extension of a monotone M along K is its left Kahn extension along K, again only on the free subcategories. And now we can examine the properties of minimal and the maximal extension. So the first property says that for every resource in the source category, the cost of that resource is bounded by the minimal and the maximal extension as follows. So if I look at the image of that resource in Y and look at the cost assigned by the minimal extension, that is always lesser than the cost assigned by the original monotone. And similarly, if we look at the image of the resource and the cost assigned by the maximal extension, it is always greater than or equal to the cost assigned by the monotone itself. So this is the first property. And the second property is that the monotone extensions themselves are monotones on the resource theory Y. And finally, like about the optimality, the extensions are optimal. So what this means is that if we provide any other monotone for Y, which reduces to M, then it is bounded by the minimal extension as follows. And similarly, if we have any other monotone extension, which is bounded by the original monotone, then we have then it satisfies this following equation. So it is its value is always greater than or equal to the maximal extension. Now that we have examined the properties of minimal and maximal extensions, now we can look at the formulas to compute these extensions. So for all, the minimal extension is computed as follows. It's computed from the limit formula. So what this does is for any resource y in the resource theory, so it looks at all those resources in X which can be converted from, which can be obtained from Y. So, and then it chooses the least cost of all these resources. So that's what the minimal extension does. And for the maximal extension, what the cost it assigns is it looks at all those resources which can be converted into Y, and it chooses the greatest value of all those resources and assigns it to Y. And because this category, like the real line, which includes 0 and infinity, has suprema and infima, we are guaranteed to have, we are guaranteed to compute these extensions always. So here are a few examples. So these are the examples that are already in the literature, but we find that these examples coincide with the framework provided by the Khan extensions. So we can extend the entanglement monotone given by Schmidt number from pure bipartite states to mixed states. And we can extend Shannon entropy from classical states to states of a general physical theory using this framework. And classical divergences can be extended to quantum setting under the same framework. So all of the above extensions are along a full and faithful inclusion functor, but we are yet to explore more examples along these lines. To summarize, in this project, we generalized the set theoretic framework for monotone extensions using Khan extensions. And our generalized framework can be used to extend a monotone along any arbitrary functor instead of just a full and faithful embedding. And our framework also generalizes extensions to arbitrary preorders with suprema and infima. And here is the link to our archive paper. So that ends my talk. Thank you. Yeah.
Thank you, Priyaa, for your wonderful talk. Are there any questions in the room or online?
Thanks for the talk. Yeah. So I didn't catch all the details, but some of the ideas look reminiscent of kind of enriched categories where you're enriching over 0 into metric type of free like different zeros between them. Is there some connection or?
Sorry, I can't hear properly.
Let me try without maths. Is that better? Can you hear me now?
Yep.
Oh, great. So, so much of what you were doing looked sort of similar to the kind of things you do with sort of an enriched category theory approach to metric spaces, and your sort of free things being like 0 distance.
Yeah.
It's the things that you can do in this that you can't do in the other framework, or other connections, basically.
I did read the paper and I can sense the connections, but I didn't look through it carefully. But there seems to be a connection between like what's happening there and like this sort of arrangement of resource theories. I should look at it more carefully.
Great, thanks.
Yeah, thank you.
I can see we have a raised hand online. David, do you have a question?
Yes. So I'm looking at the computations with the infant soup, and I guess what I'm wondering is, how in what circumstances does this sort of not collapse to, the minimal extension just gives you the minimal cost out of anything in X and vice versa?
Oh, so if I repeat your question, you're asking me under what circumstances that the minimal extension and the maximal extension coincide, is that right?
No, not that they coincide, but that like the minimal extension is just going to report the cost, like the infimum will pick out the the terminal object in X and just always give you the cost of that because there's always a map to that in the free subcategory.
Right. That's a very good question. I don't know an answer on top of my head, but I'll think about it. Yeah, I don't know when that sort of scenario arises. I don't know. I should think about it more, sorry.
Okay, let's thank the speaker again for the talk. Next up, we have another online form.
Is it Fosco or Todd speaking?
Yeah, it's me, Fosco. I'm here. Can you hear me?
Yes, we can hear you.
Okay, you should be able to share your screen now.
Yes. Okay. Let's try.
Okay, so next up
you
we
should
have,
see full screen now.
yes, that's
Okay. Perfect.
So next up we have Fosco Loregian speaking about differential 2 rigs. Take it away.
Hi, welcome. Thanks for coming. So first of all, apologies for the lack of video because I'm using a very old laptop with no webcam. So this is a joint work with Todd Trimble. It's not the first time I give this talk, but I hope you won't be too bored. The idea for this work was, in a sense, very simple. I wanted to understand what exactly is a category which is equipped with derivation operation. So, at the cost of starting this talk too simply, I would like to start by recalling what is a ring. Of course, we all know what a ring is, but let's start from there. So, a ring is a set R equipped with two operations, sum and product, such that the sum makes R an abelian group and the product makes R a monoid. Of course, my rings all have identities. And on top of this, multiplication is a bilinear operation. So the multiplication is distributed over the sum. Very good. Then we have to understand what is a differential. Well, if you come from calculus, you might think of the derivation operation of a function and differentiability and all that calculus contraptions. But since I like algebra more, my idea was to categorify what a derivation on a ring as an abstract algebraic operation is. And for algebraists, algebraic geometers, a derivation on a ring is just an end function, which is linear, and Leibniz. So it satisfies the Leibniz property, which is the property that you prove for the classical derivation in calculus, and it imposes an axiom for the abstract algebraic operation. So this is what I want to categorify. And well, first we have to understand what is a categorified ring. Well, yeah, the reason why we like differentials is that one can turn the correspondence that sends a ring or a module into the space of all these derivations into a functor. And this is not a random functor, it's a representable functor in the sense that one can realize the space of all derivations on a ring, or modifying slightly the definition, the derivations on a module over that ring. One can realize this space as an OM space, an OM set. And the presenting object is a very interesting object for algebraic geometry. It's called the object of Cayley differentials. So we want to categorify all these notions, and in order to do this, we have to understand what, first of all, what is a categorified ring. So if you think about this just for a second, you will realize that there is a problem with the presence of additive inverses, because for a category it is extremely restrictive to ask that objects with respect to monoidal structure have inverses. And because this request turns the category into an extremely rigid object. And well, when it happens, it's not by chance that we call the categories rigid. So instead of a ring, we would like to categorify what is a semi-ring. So when instead of being an abelian group, the sum is just another monoid. So in a category, another monoidal structure. The idea is that a two-rig is a category. So rig instead of ring, because a rig is a ring without negative numbers. And the two-rig is a category with two monoidal structures that are playing the role of addition and multiplication, such that the multiplication distributes over the sum. And well, this idea is not new. It's dates back to Laplace, who was interested in proving a coherence theorem for categories equipped with the structures on the same lines of Maclay coherence theorem. But for the whole discussion and in the whole paper, we took a simplified point of view, because for us, considering the case in which the additive structure was just given by coproducts, simplified the coherence theorem that Laplace found, which is notoriously quite complicated, and it was enough to produce a lot of examples. So for us, a two-rig is a category with two monoidal structures, but in fact with just one, because the other is just the co-Cartesian one, and we ask that the tensoring with an object distributes over the coproducts in the sense that it preserves the colimit that the coproduct is. So all the coherence that would be needed if Cap was another monoidal structure is here just given by the presence of canonical maps. So way simpler. Categorifying what is a differential was slightly more difficult, because originally, of course, the equation that one would like to have is an invertible morphism of this kind that exhibits the Leibniz rule and plus some coherence conditions on top. But in the end, we realized, well, Todd realized, that's the reason why one of the first reasons we entered the project, that you can give an extremely more streamlined presentation of a certain endo map, an endo functor of C that satisfies the Leibniz rule by just requiring that this red map, the highlighted map, splits by the universal property of coproducts into two maps of this kind. And what you have to ask now is simply that V exhibits the structure of a strong endo factor. People in computer science call them applicative functors, if I recall correctly. And then, as a consequence, a derivation on a category is precisely an endo functor, which is equipped with a left and right tensor strength. And on top of this, we ask that the natural map obtained by the universal property of coproducts is an isomorphism. And this is at the same time kind of a natural request, because the notion of tensorial strength is quite well understood in category theory, in applied and pure category theory. But at the same time, it's a quite restrictive assumption, because if you start thinking about examples of strong endo functors, you rarely come up with examples where this property is true. So it's interesting to see where this axiomatics brings. And well, it's also interesting to understand from a bird's-eye point of view, what is this theory about? Because it's certainly interesting to try and build a general theory of this now that we have a definition. It is certainly interesting to find and build examples of this structure now that we have these axiomatics in mind. But my aim, my overall goal as a general idea is to understand how this theory can draw a connection between two seemingly very different aspects of very different applications of category theory, because on one side, differential algebra is a staple of a certain branch of algebraic geometry and also multiple theory in the last 15, 20 years more. But On the other hand, the main motivating example of a differential theory is the category of species, which was invented by André Joyal in order to put category theory into enumerative combinatorics. So what does combinatorics have to do with algebraic geometry? Yeah, I find this question very ill-posed, but at the same time quite intriguing. So what can we do with this? Well, among many, a first very remarkable, in my opinion, result is that you can prove very simply that whenever you have a two-rig, and of course, the two-rig has a monoidal structure, the multiplicative structure, and you can consider monoids with respect to tensor. And if you derive the monoid and you use the Leibniz rule, what you get is that the multiplication map splits into a pair of maps that essentially say that M as a monoid is acting on its derivative. So as a rule of thumb, the derivative of a monoid is a module over that monoid, which is surprising. I wasn't expecting it, that the proof was so simple. I'm still trying to find a concrete instance of this because seemingly people in, I don't know, differential geometry disregarded this idea. I tried to interact with people doing real geometry. I'm not a real geometer, I've never been. But, and it is also surprising how simple the line of argument is to prove such things that essentially says, well, if you have a derivative operation on a category, the derivative of a monoid cannot go too far from the monoid because it inherits a natural action of the monoid, which is, again, interesting. So, again, as I said before, the main motivating example for this is understanding more conceptually the structure of the category of species, which is already a quite abstract object, but you can always go a little bit further. So let me recall what is the definition of this. It's a very simple definition. You take the category of finite sets, and but you only take bijective functions, and then you take free sheaves over this. So this category has all the structure that I outlined so far. It's a very important fundamental example of a differential theory. And especially the derivative operation is interesting because you take a functor from P, finite sets and bijections to set, and then its derivative essentially shifts by one the action value. So instead of acting on a set with n elements, now F is acting on a set with n plus 1. So you can prove that this satisfies indeed the Leibniz rule. You can prove that this functor is quite a well-behaved functor because not only it's linear and Leibniz, but it also has a left and a right adjoint. So it must preserve any limit, any colimit that you might think of in the category. Joyal gave a very slick proof, a very elegant proof of the chain rule, which is the derivative of a composition of functions. And we found with Todd another way to provide proof of this, which is slightly more conceptual. It adapts to settings where you don't take exactly the category of species, but you take a different codomain, a different domain. You fiddle a little bit with this idea of a pre-sheaf category over a certain shape. And in all these cases, you have a derivative and you can prove a chain rule, which is remarkable. The category of species was studied having in mind its differential structure by many people, mostly by I discovered with great pleasure that it was a big school of combinatorialists in Canada, which was very interested in understanding category theory, and well, not only in Canada, but mainly in Canada. And understanding category theory to understand the combinatorial content of classes of differential equations. So solving differential equations has a combinatorial meaning, and problems in combinatorics can be seen with differential equation like goggles. It's very remarkable, and there's a huge body of literature on this, especially by Leroux and Vienno. This is the Canadian school, but also Labelle and people that work in group theory and combinatorics. So you see a very enticing, a very fertile field of study. And my hope is that at some point we can get a more conceptual grasp of all this body of literature, which is quite interesting, but it needs more structural thinking. And well, one idea that makes this task of understanding conceptually the category species more concrete, more grounded, is that one can easily come up with the notion of a free to read on a category or on a set or any set of symbols, just to be slightly informal. And the idea is you take your base category sigma, and then you build the free monoidal category, symmetric monoidal, braided monoidal, depending on your taste. And then you take the closure of the pre-sheet category of M sigma under finite coproperties. By construction, this is the free object in the category / 2 category of two rings. So, and with this in mind, one can prove that the category of species has a universal property as a two ring, because it's the free to read on a single generator. The category is just a discrete category with a single object, where on top of that, you add all colimits. And the monoidal structure preserves not only coproducts, but all colimits. And the category of species in a countable set of generators is instead the free co-complete differential to read on a single generator, meaning that you now not only add well, a single indeterminate and then all its powers, and so you build polynomials and all or form a power series, but now you take form a power series of differential operators, which is remarkable because this category, the category of species, acquires not by design, but by accident, differential structure. And in differential algebra, that's exactly what happens, because the polynomial rings and formal series rings acquire a differential structure in a suitably canonical way without us requiring that the differential structure was part of the free structure we wanted to build at the beginning. So, in my opinion, although superficial, although a little bit naive, this is a very strong parallel with differential algebra. So, we can also categorify what happens with the representability of the derivation factor, because we can build a categorified version of the object of Calle differentials, in the sense that one can define in a very straightforward way a notion of morphism derivations. So one can turn derivation on C into a category. And as a category, this is equivalent, more isomorphic, to the category of two-rig morphisms. They are just functors that preserve all the structure from C into this category C epsilon, that can be characterized precisely as some sort of quotient of Cy. Cy is the free to read on the single generator Y, quotienting by Y squared, which is exactly the categorified analog of what you do when you build the ring of Calle differential. So this is another strong parallel to differential, because the universal property that you obtain by killing powers of Y squared is precisely what you need to represent derivations, both in the world of rings and in the world of differential tools, which is remarkable. So, to wrap up a little bit, what we want to do now, and this will be the end of my talk, I would love to understand more what this story with differential equations. I would love to find a way to connect the theory of differential equations with another well-established part of category theory, which is the theory of initial and terminal coalgebras for endofunctors, because with just a little bit of effort, you can define what is a differential polynomial endofunctor by just adding to the definition of polynomial endofunctor the derivation operation. And then you can start looking for solutions to differential equations. But what is a solution for a differential and for a polynomial endofunctor? Well, in a sense, you would like to find fixed points, because asking to find zeros is a little bit more restrictive. So how can we connect the theory of fixed points and of initial and terminal coalgebras to this world of differential equations. How far can we go then to understand what's the connection with algebraic geometry? Can we study more deeply the theory of quotients? Can we understand more properties of Carlo differentials? Can we attack ideas of the formation theory, which is another staple of algebraic geometry that employs a lot of the ideas from differential algebra? Can we do Galois theory for differential equations when we have a decent understanding of differential equations themselves? So you see, a lot of questions. I look forward for inputs from the audience every time I present this talk. I'm still in the process of writing down the final version of this paper with Todd. There's a lot of ideas on the table. Some of them are, in my opinion, very, very enticing. So feel free to ask questions, to contact me if you have ideas or views that you want to share. Thank you.
Okay, thank you, Fosco, for your talk. I already see that there's a couple of raised hands online. So would someone like to ask a question?
Sure. I'd like to just ask in that last slide with killing the square, that sort of superficially looked a lot like the Cock-Levier axiom. Can you say a sentence or two about that?
Which slide, sorry?
Just the last, I think the previous slide, the one where you're killing the square of epsilon. It just sort of reminds me of this sort of free introduction of nilpotents in synthetic differential geometry. Does that make sense?
Yes, I see the connection. I remember, I think I know what you're talking about, probably not in detail. What I find remarkable about this result is that you can really write down the naive universal property that you would like to impose on this object of Carlo differentials is that all the powers, all the polynomials that are divisible by y square, that are killed by the quotient that you perform. And that's exactly what the converter does. I didn't go into details for what is this converter gadget, but the idea is that it's precisely a quotient as a category. And I find this remarkable. Does the Cock synthetic differential geometry approach that you mentioned say something on these lines? Or?
Yeah, I'm not sure. I'll leave it at that for now. Thanks.
But I'll have a look, because honestly, I didn't bother to reread. It's been a few years since I skimmed the book, so I didn't bother to reread it now. But thank you.
Was there another question online? I saw two raised hands there before.
Yes, I also had a question. So one of the fun things about derivations is that if you look at a manifold in differential geometry, you can define the tangent bundle as giving to each point the derivations on local functions. So could there maybe also be some kind of tangent bundle over a category in this way?
Well, not exactly, but one connection with you of course you know that the space, the dimension of the tangent space on a manifold is precisely the dimension of the space of derivations, local derivations on a point on the manifold. Probably I didn't state it correctly, but you know what I'm talking about. Actually many categories have no non-trivial derivations, which is, in my opinion, far from being a hint that this theory is not interesting, because in a sense, categories, for example, no Cartesian category can have a non-trivial differential structure if you ask the Cartesian structure distributes over the Cartesian distributed categories. And this is remarkable and not trivial, because in a sense it's saying to you that Cartesian, bi-Cartesian or distributed categories, but also module categories over rings, they have dimension 0. So I cannot make this precise, but I believe there is a way to talk about dimension theory for categories in terms of the space, the category of its derivations, which is not exactly what you asked for, but nearby.
Okay, I think we'll finish there. So let's thank our speaker again.
Thanks to you.
Is the microphone working? Is the microphone working?
So our last speaker for this session is Dylan McDermott, who will be talking to us about canonical gradings of monads.
Okay, thanks for the introduction. So I'm going to talk about a problem that comes from kind of semantics of computational effects. Kind of the general high level story is that we can model computational effects using monads. But at some point, if we want to actually reason about our programs, we actually want to grade monads in some sense. And if you think about this for long enough, then eventually you start asking, well, I have some given monad, what can I grade it by? So this work is kind of an answer to kind of what is the best grading of a monad in some sense. Okay, but I won't go through the computational effects stuff in too much detail, but I'll start with some slightly artificial example that does come from computational effects. So firstly, here is a monad, right? So if we have a set C, we can consider the monoid of lists over C with concatenation, and then we get some writer monad. So essentially we say, if we have a set X, we get a set writer of X of computations over X. And a computation is just a pair of a list over C and an element of X. And this forms a monad. It has some unit in multiplication. Then we can talk about grading this thing. So I won't say what a grading is yet, but I'll just give you kind of some examples. Hopefully these give some intuition. So we can grade this monad by natural numbers. So given a natural number E, we can say a computation of grade E is now a pair of a list whose length is at most E and an element of X. Right, so now essentially we're just carving out a bunch of subsets of this writer monad. And then we can also assign to the unit in multiplication some appropriate grades. And we can also grade by subsets of C. So we can say, consider lists over E, where E is a subset of C. And now we get some other subset of the computations. And I'll show one more example of this. So this example is kind of special in some sense. So we can also grade by subsets of lists over C. So given a subset sigma, we can say a computation of grade sigma is a pair of an element of sigma and an element of X. And again, there's some kind of appropriate grades that we can give to the unit in the multiplication. Now, this one is special in a sense that every other grading of this monad kind of arises from this one. So if we take the first grading, for example, we grade by natural numbers. And for every natural number, we have a subset of the lists, like lists of length at most E. So we get a function from natural numbers to these kind of canonical grades that I was calling sigma. And then we can compose with this third grading that I showed. And the composition is actually the first thing that I showed. We kind of get this first graded monad. And there's a similar thing with the second one as well. We can compose with this canonical grading to get the second grading. So the point of this work is to kind of explain what's going on here, kind of in more generality. So for this talk, I will actually work at the level of monoids instead of monads. So the general setting will have some monoidal category D, and we'll talk about monoids inside D. So the monoidal category might be endofunctors and we get monads, or it might be something else. Then we also assume a class M of morphisms from D. So this will give us some notion of subobject. So in the case of endofunctors, we can take component-wise injective natural transformations, and these are essentially subobjects just where we have a family of subsets of the computations. So this is kind of what I was using at the beginning. So now the point is we can define some notion of grading of a monoid, and we can show that under some circumstances, every monoid has a canonical such grading. Okay, so I'll actually start with objects instead of monoids. So I'll just forget about unit and multiplication for a while. So I'll say if we're given some category D, a class of morphisms, and an object T inside D, I'll define a notion of grading of this object. So it consists of a category of grades that I'm calling G. Also a functor that assigns a functor that goes from G to D, and some natural transformation whose components are all from M. So the last two bits of data essentially say for every grade, I have some kind of interpretation of that grade as a subobject of T. So for example, the things that I showed on the first slide are the kind of examples of this, right? So we can say my grades might be natural numbers. My functor just says, given a natural number, I get this kind of endofunctor where we pair with lists of length at most E. And the natural transformation is just inclusions, because I'm just using subsets, really. Okay, now every object T will have a canonical grading in some sense. So the canonical grades will be, the category of grades will be the slice of M over T. So a grade here is just a pair of an object S and some morphism from S to T, so forming a subobject. Then we have some functor, which says for every grade, I can just assign the domain of the subobject, this object S. And finally, we have some natural transformation, which just says, well, take the subobject and just assign the actual morphism, the morphism that really witnesses this as a subobject. So this is the grading in the sense of this definition that I showed on the previous slide. And it's canonical in the sense that every other grading will factor through this one, essentially uniquely. So one way of looking at this is to construct a grading of an object T, I really just take the canonical one and compose with something. The precise statement is it's pseudo-terminal in some 2 category, but I won't really expand this out and explain this properly. So we can now talk about canonical gradings of endofunctors. So these are given by this slice of M over T, which in general might be quite complicated, but in some cases, we actually have a kind of reasonably nice concrete description. So a subfunctor of the identity functor, well, there's exactly 2 such subfunctors up to isomorphism. So we can either say every set gets mapped to the empty set, or we can say every set gets mapped to itself. And these are really the only 2 up to isomorphism. So now we can say the canonical grading is essentially, we have 2 grades, which here I'm calling bottom and top. Bottom essentially denotes the constantly empty functor, and top denotes the identity functor. And this is canonical in the sense I had on the previous slide. We can do a similar thing for this list example, and essentially the subfunctors here are just subsets of list over C. I'll show one more example, which is a bit more complicated. We can take the underlying functor of the reader monad on a set V. So we fix a set V. Subfunctors of this thing, this endofunctor says for every set X, I get a set of functions from V to X. And subfunctors of this thing are essentially the same thing as sets of equivalence relations on V, which satisfy some closure condition. The point being, given any such set sigma, I can say I now have some subfunctor of this functor, where we just take the morphisms from V to X that respect at least one of the equivalence relations inside this sigma. Right, so there's a bunch of examples of this. I won't show any more, but we get these canonical gradings. So now I'll talk about graded monads for a second. So I won't really say much about these, to be honest. So I'll give you the kind of slick and maybe not so helpful definition. So if we fix a monoidal category G of grades, then a graded monad graded by this G is a lax monoidal functor from G to endofunctors. So if you expand this out, you get something that looks a bit like a monad. But instead of having a single endofunctor, we just say have an endofunctor for every grade. And the unit and multiplication have some grades which come from the monoidal structure on G. But again, I'll work at the level of kind of monoids and lax monoidal functors. So we can now talk about what a grading of a monoid is. They're very similar to gradings of objects. We just kind of insert the word monoidal in various places. So we say the G is now a monoidal category of grades. The functor has become a lax monoidal functor. And the natural transformation is now monoidal. So it respects all the kind of units and the multiplications. So for example, we can take the first thing that I showed, the first grading I showed where we have natural numbers, and say the monoidal structure is addition. And we get some lax monoidal functor kind of using the same structure as the writer monad. Okay, now we can ask whether we have a canonical grading of a monoid. This takes a bit more effort. So firstly, the big problem is that we need to make M over T into a monoidal category. And the way to do this is first to note that D over T is a monoidal category. So T has a unit and a multiplication, and we can use these two things to construct a unit and a tensor on this category D over T. So the unit of D over T is actually just the unit of the monoid. And the tensor says, if I'm given two morphisms with codomain T, I can combine them to get another morphism with codomain T just by using the multiplication. So we get some monoidal structure, and this functor that assigns the domain, the domain of an object of D over T is actually a monoidal functor now. Okay, but we want to do this with M over T. This takes slightly more effort, but we can say, well, suppose that M forms a factorization system. The point being that if we're given an object of D over T, we can canonically turn this into some object of M over T by saying, I have a morphism, so I can factorize it in some way. Then I can take my monoidal structure on D over T and just factorize the morphisms I was using for the unit and multiplication, the unit and tensor. And this actually gives us a monoidal structure on M over T under some closure conditions. And this functor that assigns the domain is now a lax monoidal functor. So actually, we can use this data and put it all together, and we get a grading of the monoid T. Right, so we have a monoidal category of grades, which is M over T. We have this lax monoidal functor that assigns the domain, and this natural transformation is automatically monoidal. So this is canonical in a sense, essentially the same universal property that I had before, but now we just insert monoidal in various places. So now we have some construction of a canonical grading of a monoid. And I'll just show one example. So we take this writer monad. We can kind of look at what this monoidal category is. So I already said that the subfunctors are essentially subsets of list over C. And we can kind of transfer along this monoidal structure that we've constructed. And we find that just by when we consider subsets of lists over C, we get kind of component-wise concatenation of lists. Okay, now there's just one more thing that I want to mention. It's often the case when we're modeling computational effects that we don't want to have sort of arbitrary gradings of things. It's sometimes the case that we just want to consider shapes of computations. So if a computation is an element of T of X, the shape of the computation is the element of T of 1 that we construct by saying map along the canonical map from X to 1. So we essentially just kind of forget the results that come from X and just look at the shape of the computation. And we can actually fit it in kind of grading by shapes of computations into this framework too by considering a different class of morphisms M. So if we say that M is now natural transformations that are Cartesian in the sense of naturality squares being pullbacks, and also such that their one component is injective, then we'll actually get some factorization system. And it will be the case that the M subobjects are now subsets of T of 1, up to some isomorphism. So we can kind of use all the stuff that I showed on the previous slide for this particular class of morphisms M, and we can get some kind of canonical gradings by sets of shapes. Okay, but that's really the last thing I wanted to mention. There is also some story about algebraic operations and how, so the point being that to model computational effects, we need to talk about algebraic operations, which kind of actually interpret the effects. And these actually fit in quite nicely into this story as well. But I won't actually explain how this works. I don't think I have time. So I'll stop there. Thanks.
Okay, thank you, John, for your talk. Are there some questions?
Have you thought about, is there any application of this stuff to ideas in computational complexity? Is there any place you can see them? It's giving you something that you would like in computational complexity theory, but don't know how to do.
I have not thought about this. Do you mean applications
I'm
of?
thinking the grading is something about the complexity of the algorithm that you want, so that kind of captures.
I guess in theory that could be the case, but I haven't really, I haven't thought about this.
Okay.
I mean, there's a bunch of applications of grading kind of outside of computational effects. But yeah, I don't think I've never thought about complexity, so I don't really know. Perhaps there is.
Okay, thanks.
Other questions? So just a question that I had is that you were talking about grading with monads, I guess, on a category.
Yeah.
Can you also talk about gradings of monads in a bicategory?
I think it's not so obvious. We would need an appropriate notion of Laxmanoidal functor, and I'm not entirely sure what that would be. I guess it's probably something that can be done, but I really don't know.
That's right. Thank you. Were there any questions online? I can't see, so if you have a question, just speak there. Okay, well, in that case, let's thank our speaker again. Before everyone goes off to lunch, there is an announcement, which is that at 3:30 today, so that's at the beginning of the afternoon coffee break, there will be a group photo. And that'll be outside in the garden across from the building as we exit. So thank you.
It's not a bad show.
So I just want to ask that question at the end about
Do you want to mute this?
Can you hear me already? Does it work? I don't hear anything, so that's.
Okay, we can start. So welcome everyone to the first section of the afternoon. It's my pleasure to introduce Andreas Kluger, who is going to talk about the D-separation here in California.
Yeah, thanks a lot for that nice introduction, and also thanks to the organizers for this wonderful conference. So today I will be talking about joint work with Tobias Fritz. He's unfortunately not here in presence, but I'm not sure, but perhaps he's joining online. So since there are still a lot of people arriving, let me start with some fun fact I want to share with you. Oh, it's not working. Does it work now? Okay, yeah, thanks. So did you know that there is a correlation between the average chocolate consumption in the country and the number of Nobel laureates? Well, this has been shown in that study of 2012, and the author there even claims that there is a causal relationship. So more chocolate consumption leads to more Nobel laureates. And a lot of newspapers have even written an article about that. But at the end, so many other researchers have rejected that claim. However, this doesn't exclude other possibilities of causal structures behind. We don't know. So there could be other causal structures giving rise to that correlation. Now, talking about causal structures, a common framework studying causal structures are Bayesian networks. So Bayesian networks are described by a dialectic acyclic graph, where every node represents a random variable and every error represents a causal influence. So for example, here, a probability distribution is compatible with precisely that causal structure if the probability distribution factorizes precisely in that way. So Z is freely sampled and X and Y are independently sampled given the information of Z. Now, one common problem when studying Bayesian networks is the following. Assume you have given some probability distribution from some measurements, some experiments, completely unstructured. And you want to decide whether this probability distribution is compatible with a certain causal structure. Can we decide that, or what are the possibilities to decide that? Well, one way to decide that question is to look a little bit deeper into the conditional independences which arise from a certain causal structure. So again, the same example here. If you have a probability distribution which is precisely compatible with such a causal structure, then X must be independent of Y given Z. Well, that follows directly from the definition because X and Y are independently sampled given the information set. Now, on the side of dialectic acyclic graphs, this fork-like scenario here is an example of D-separation. So in other words, if we have a fork-like structure, then this is a certificate for this precise conditional independence on the right-hand side. Now, another example of D-separation is the following scenario, namely such a chain-like structure. Also there, you can show that every probability distribution which is compatible with such a causal structure has to satisfy that conditional independence. Now, let me give you one non-example. If you have a causal structure like that, where you sample X and Y independently and then send that information to Z, then there exists some probability distributions where X and Y are not conditionally independent given Z. Simply think about tossing a coin, X and Y independently toss a coin and then send that information to Z, and Z reveals, for example, whether the coin tosses are the same or are different. On the other hand, on that graph theoretic picture here, this collider structure here is a non-example of D-separation. So here, Z does not D-separate X and Y. Now, this idea I've presented in the last slides have been generalized to the so-called D-separation criterion, which tells us the following. if we have a probability distribution which is compatible with a given causal structure, then this implies that every d-separation in the Bayesian network in this directly acyclic graph leads to conditional independence of the compatible probability distribution. So we have a necessary criterion for probability, for compatibility. However, it also holds in the other direction. So if you have a causal structure and a completely unstructured probability distribution, if you can show that for every d-separation in the graph, we have conditional independence for the probability distribution, then this implies that the probability distribution is compatible with the causal structure. And by d-separation here, I mean a criterion which goes beyond those examples I mentioned at the beginning. Yeah, so there are certain rules, but I don't want to go deeper into that. Now, the d-separation criterion has already quite some history. So it has been first shown in the late 80s by Pearl and colleagues, but only for discrete random variables. And since then, it has been generalized in many ways. So there are a lot of algorithms deciding d-separation and so on. But it has also generalized to other types of random variables. So for example, to continuous random variables or mixed random variables in a measure theoretic setting. And this has been done even already only quite recently, for example, in the measure theoretic setting. Now, in this talk, I would like to give you a completely different perspective on the d-separation criterion, namely a categorical perspective on d-separation. Namely, we want to study, or we show the d-separation criterion, first of all, in the setting of categorical probability theory, and our causal models are based on string diagrams. Now, you might ask, well, why should we care about that? The separation criterion is already quite well understood, as you have seen. So why should we care about a categorical view on that? And I claim that such a view from categorical probability theory, first of all, makes the proof and the criterion itself much simpler, or our proof makes it much simpler. On the other hand, we can apply the d-separation criterion at the end to way more examples, as we will see. So for this reason, let me highlight some of the main differences between the classical approach of the d-separation criterion and our categorical approach. So first of all, as you have seen, in the classical approach, the d-separation criterion has been shown for different probability classes, always separately. So you need for every probability class a different proof. In particular, if you go into the measure theoretic setting, you of course need measure theory. On the other hand, in our categorical approach, we prove the statement on Markov categories, which are completely agnostic about the type of probability class. And in particular, we can also show the d-separation criterion completely diagrammatically. So we don't need any measure theory. And also using string diagrams instead of directly acyclic graphs as blueprints for our causal models has a lot of lead to a lot of differences. So first of all, as you have seen at the beginning, with directly acyclic graphs, you only study probability distributions and causal compatibility of probability distributions. However, using string diagrams, we will see that this automatically generalizes to stochastic maps, since string diagrams naturally have inputs also. And one surprising fact we also found is that if you translate the d-separation on directly acyclic graphs to string diagrams, this leads to an extremely simple criterion, much simpler than the criterion on directly acyclic graphs. Namely, it's just disconnectedness of string diagrams. Okay, so with this, let us go a little bit deeper into the work. The rest of the talk is structured mainly as follows. First of all, I will recap the main framework which where we are doing our proofs on, namely Markov categories. And I know many of you might know Markov categories even better than me, but I just want to give you some basic idea. And in particular, we will use Markov categories also as a framework to to generalize causal models, or as a framework to talk about causal models instead using Diegetic acyclic graphs. In the second part, we'll talk about the two main ingredients for the separation criteria, namely conditional independence and categorical deseparation. And at the very end, we can then talk about the deseparation criteria. So what are Markov categories? So Markov categories, the main idea behind Markov categories is to have a categorical framework of talking about probability distributions. So the main idea of a Markov category is that its objects are purely the sample spaces. So for example, finite sets, as we will see later, or it can be also measurable spaces. And the morphisms are stochastic maps. Now, as you see already in that, So for example, if you have a stochastic map, that samples are random variable depending on the input in the sample space X, for example. And if you have a trivial input, for example, then you get automatically a probability distribution. Now, also, as already indicated by the string diagrammatic formulation here, Markov categories are symmetric monoidal categories, simply because we can sample multiple random variables with a simple probability distribution, and we can also apply Markov kernels in a parallel way. Now, Markov categories have also some additional structure, namely a comonoid structure, which represents basically the two basic operations you can do for every sample space. Namely, you can copy information and you can throw information away. So you can discard the information. And these two operations, these two morphisms, have some certain properties. For example, if you discard one of the outputs in the copy map, then you get the identity and so on and so on. Everything what you would expect naturally from these morphisms in a realistic setting. Now, one particular property I would like to mention here, because it will be used quite often throughout the rest of the talk, is the naturality of the discard map. And you can simply think about it in a way that assume you're sampling a random variable and you're throwing it away, then it doesn't make any difference how you have sampled that random variable. And that's precisely represented by that equality here. Now, let me give you some examples of Markov categories. Now, the simplest example of a Markov category is the Markov category Finstoch. In that setting, the objects are simply finite sets, and the morphisms are finite stochastic maps or finite probability distributions. Composition is given by the natural composition you would expect from composing such Markov kernels. And you can also generalize it, or you can extend it with a monoidal structure. A different example is the Markov category Gauss. In this Markov category, the objects are finite vector spaces, R to the n, and the corresponding probability distributions, the morphisms are Gaussian, multivariate Gaussian vectors, and the morphisms are just linear transformations plus some Gaussian noise. So these maps preserve, of course, the Gaussian structure. But you can go even further. You can also introduce the Markov category Stoch, where every object or the objects are measurable spaces, X with a sigma algebra, sigma X, and the probability distributions are just arbitrary probability measures. Now, one subcategory of Stoch I would like to mention here, that's the category Borel Stoch, where we just restrict our objects to standard Borel spaces. So if you are not familiar with standard Borel spaces, just think about the real numbers and an arbitrary probability measure on the real numbers, which is a probability measures on the Borel sigma algebra over the real numbers. Now, we show the deseparation criterion only for particular Markov categories, namely Markov categories which have conditionals. So what does that mean? A Markov category has conditionals if every morphism which has two outputs, so just generating two different random variables, we can generate these two different random variables in a sequential way. So for example, first generating the second random variable and then generating the first random variable from the information of the first random variable and the input. Now, it seems quite intuitive that for probability distributions, something like that should always hold, right? And indeed, for finite probability distributions or Gaussians or Borel probability distributions, this is true. However, there are some examples in the most general Markov category Stoch where this does not hold. So therefore, our proof only applies to the first three examples. Now, as you have seen, we have now introduced 4 different concrete Markov categories. And of course, there are many, many other Markov categories, even going beyond probability theory. But I would also like to introduce a completely different kind of Markov category, because this type of Markov category will be our basic building block to talk about causal models or to talk about Bayesian networks. And these are 3 Markov categories. So you can simply think about them in the following way. Given some objects, a finite set of objects, and some finite set of morphisms, the 3 Markov category is precisely that category which contains all the morphisms which can be generated by that finite set, or it could be even infinite, in a reasonable way, using all the structure we have in a free Markov in a Markov category. Now, I don't want to talk about the construction of such 3 Markov categories in detail. I will refer here to the work of Tobias and Wenham, which has been recently done. But we will use this idea of 3 Markov categories to talk about causal models. And if we talk about causal models, we also have to talk about compatibility. Now, compatibility means the following. A concrete a morphism in a concrete Markov category is compatible with a causal structure or equivalent with a morphism in the free Markov category, if and only if there exists a functor which maps every box on the left-hand side to a concrete morphism on the right-hand side. Now, this idea is not completely new. It goes back to a lot of other works which also rely on string diagrammatic formalisms of causal models. So I forgot to say that there are, of course, a lot of works which have been doing that already before us. Now, I've told you at the beginning that string diagrams can parameterize way more causal models than Bayesian networks do. So let me show you that by some example, namely a causal model or a Bayesian network which arises directly from a dialectic acyclic graph. Now, this particular example can be written as a string diagram in the following way, namely generating a random variable set, then copying that, and then generating x and y from that information in set. Now, such string diagrams which arise from a dialectic acyclic graph have some particular properties. Namely, every box has precisely one output. That comes from the fact that a dialectic acyclic graph, every node represents just one random variable, right? We also have no global input wires, which show that there are no, that we usually only talk about probability distributions. And finally, every wire is also a global output wire. And that shows, or that emphasizes that we have access to every variable in the model. Now, we show the separation criterion to way more string diagrams than just string diagrams arising from a dialectic acyclic graph. So we don't need that assumption that every box has just one output and that we don't have any global input. However, for simplicity, Can you hear me again? Perfect. Okay, so where did we stop? Yeah, so I just said, well, we are proving the D-separation criterion for even more causal models, not only arising from directly acyclic graphs. So string diagrams do not have to have just single output boxes, and we can also show it for string diagrams with global input wires. However, just for simplicity, I will restrict to the case of probability distributions for the rest of the talk. I will comment on the fact of that we have also proven it for string diagrams with inputs at the end. There are some technicalities which are happening. Okay, so in the second part now, we have to talk about the two main ingredients to formulate the D-separation criterion, namely conditional independence on the one hand, a string diagrammatic formulation of conditional independence, and the categorical D-separation. Now, for conditional independence, there is not much to say. There is a very natural candidate for probability distributions to talk about conditional independence. So if we have given 3 disjoint sets of wires, or you can think about them as a single sample space, then a probability distribution or a morphism shows the conditional independence X independent of Y given set if the morphism factorizes precisely in that way. And that's very natural because that comes directly from the formulation of conditional independence in the dark case. So there is more to say for D-separation because this way of defining D-separation on string diagrams is completely different as the classical way. Now we have, again, 3 disjoint sets of wires, and we say that these disjoint sets of wires set D-separates X and Y if the wires X and Y are disconnected when removing the wires in set. Okay, so let me show you that on some examples, because then you might understand it in a better way. Let us go back to our usual suspect of example. And here we expect from the classical D-separation that C D-separates X and Y. Now, why is this the case? Well, we just have to remove the wire corresponding to Z. And we see that X is D-separated by, or is disconnected from Y. And so we have also in the string diagrammatic formalism that Z D-separates X and Y. Now let us consider a little bit more complicated example. In this example, I changed only one thing, namely I added here to the last example an additional box generating this random variable W from the inputs in X and Y. And I claim that Z and W here does not D-separate X and Y. And that's also consistent with the view in the dark case. Now, how can we show that? Well, let's do the same as before. Let's remove the wire. And we see that X and Y are connected with each other. However, in the same example, I claim that Z D-separates X and Y. So no W in here. So we have to get rid of W. So let's discard it. And discarding this wire here means that the box below gets completely irrelevant. So we can ignore it or we can remove it. And now again, removing the wire set and removing also the box, we end up in that string diagram. And it's again obvious that X and Y are disconnected and therefore we have the D-separation. So with these 2 definitions, we now end up with the final theorem, namely the D-separation criterion. And I would like to split it up into 2 parts. First of all, I will talk about the soundness of the D-separation criterion, namely, if P is compatible with a causal structure, then this implies that every D-separation in the string diagram leads to conditional independence. And of course, we can only prove it, or we prove it for Markov categories with conditionals. Now, let's look at an example again. Here we have a new string diagram And the reason why I've chosen it, it's not some fancy application here. It's just the simplest example, which is non-trivial to show you the whole proof idea. So we again generate set, and then we generate x and y from the information in set, and then we generate w from x. And as you can see, set and w deseparate x and y, right? Because if you remove the wire set and the wire w, then we again have the disconnectedness between x and y. And so therefore, the theorem tells us that x is independent of y given set and w. Now, from that string diagram here, that's not obvious, right? Because we first generate set, and then we generate x and y, and at the very end, we just generate w. But this statement here means that we first should generate set and w, and then we generate x and y, only depending on the information of set and w. Okay, so how can we prove that? Well, we can use the existence of conditionals, right? So let's consider this brown box here, which has input set and output w and x. And we wanted to generate first w, and then we want to generate x. So therefore, we just apply the existence of this particular conditional where we discard x first, and then generate x from w. And if you look closely to the string diagram, that is precisely that statement, because we first generate set, then we generate w, and then we generate x and y given those two random variables. Now, you might ask, where did we actually use deseparation here? Well, we used it in a way that this argument works. Namely, we used it in the fact that we can show that this brown box here has particular in and outputs. So, for example, if we wouldn't have the output w on the left-hand side, but the output y, then this argument would break down. So this separation is really important to show that this argument works. And you can do it for arbitrary causal models in the same way. Now let's go the other direction. Now we claim that every deseparation in the string diagram, if every deseparation in the string diagram implies conditional independence, then this shows that a given probability distribution is compatible with the causal structure. And this statement here is also called the global Markov property. And as you will see when I show you the proof idea, we actually don't need all the deseparations. We just need a tiny number of deseparations. And so therefore, you can also relax that statement to the so-called local Markov property. But I won't talk about that more in that talk. So in fact, we want to show that if we have a morphism P on the left-hand side, which satisfies the global Markov property, then it is compatible. It can be written precisely in that way. Now, from the deseparation on the right-hand side, I've now picked two statements of conditional independence, which will suffice to show that we can represent P in that way. Namely, we have W is independent of Y and Z given X. Well, again, you can simply see that because if you remove the Y or X, then W is disconnected from Y and Z. So therefore, we must have that conditional independence. And our usual conditional independence X independent of Y given Z can also be seen quite easily here. Okay, now let's construct our string diagram from these two conditions. Let's start with the first one. Now the first one shows that our string diagram, our four-partite probability distribution, can be factorized in precisely that way. Now, you might miss here the third box, which generates Y and Z, right? But I've merged it directly to the root distribution because we don't need it. So we end up with this morphism of that structure here. And we have now a root distribution with 3 output wires, X, Z, and Y. So let's directly apply the second conditional independence condition to that root distribution. Applying this conditional independence to that root distribution, we directly end up in the causal structure we wanted to show, right? And so therefore we have shown that our probability distribution is compatible precisely with that causal structure. Now, there is one thing I've mentioned quite often during the talk, but I've never been precise about that, namely that the deseparation criterion also works for Markov kernels or for string diagrams with inputs, right? And while the deseparation itself on string diagrams works precisely the same as for string diagrams without inputs, we have to talk about conditional independence, because I've only defined conditional independence for string diagrams without inputs. So how to generalize that to string diagrams with inputs? Well, there are a lot of possibilities, right? You can generalize it in that way, that generating X and Y only depends on the Z wire. You can also generalize it in this way, where X and Y additionally depend on the input. But the deseparation criterion suggests a completely different way of defining conditional independence, a little bit a weird way, namely an asymmetric way of conditional independence, where Y depends on the input wire additionally, but X, generating X, only depends on Z. Now, we are not the first one who observed that strange way of conditional independence, that this is necessary for the deseparation criterion. This has also been already discussed in that recent paper by Patrick Faure, but in a classical setting, not in the categorical setting. And he coined that term transitional conditional independence. Now, with that, oh, I have a lot of time left, right? I would like to come to an end. Of course, I have a lot of open questions for you still. So one thing I have not talked about, and I haven't been precise about that, is that you could also study the deseparation criterion to symmetric causal models. And symmetric causal models are also particular morphisms in a free Markov category. So symmetric causal models are simply causal models where the Markov, so the processes which generate random variables are, there are multiple morphisms of the same structure in your causal model. So for example, think about a De Finetti type causal model. There you have a lot of symmetries in there. And although we have shown that the soundness of the deseparation criterion works well for these types of symmetric causal models, we have to additionally impose some symmetry conditions for those causal models, and we were not able to do that so far. Another very vague open question is, well, can we apply the deseparation criterion also to other types of Markov categories? And I'm curious if we would get then some weird results. And the last open question, it's also a little bit broader, namely, what to do with that connection between disconnectedness of string diagrams and independence, as shown by the deseparation criterion. So from an unbiased view, if you would not know anything about dialectic acyclic graphs, it's not so surprising that there is such a connection between, because such string diagrams model precisely the information flow, right? And therefore, the disconnectedness in the information flow should correspond to some type of independence. However, if you go back to the picture of dialectic acyclic graphs, there is no similar statement. So, for example, this deseparation for dialectic acyclic graphs is very complicated, and there is no direct disconnectedness in that criterion. And this, of course, raises then the question, well, what's the more natural approach for such causal models? Is it string diagrams, or is it directly acyclic graphs? So if you have any suggestions, okay, yeah, not important. If you have any questions or suggestions or comments on that, please, we are open. If you write us an email, we can discuss that. And you also can check out the paper if you're still interested. And yeah, thanks a lot. And I'm taking questions.
Thank you for the talk. Are there any questions?
So I guess regarding disconnectedness and independence in string diagrams more generally, there is a sense in which the deseparation criterion is not algebraic, right? I can't express it as an equation between two terms built out of the thing I'm interested in. Do you think there's any hope of getting a sort of more algebraic characterization of it?
Well, so one thing. So I was not precise about that, but disconnectedness. So this going from such a string diagram to the disconnected version is can be written down as a functor, but not in the free Markov category. So you have to dig a little bit deeper. First of all, so these string diagrams are constructed via cospans of some hypergraphs, and on that category you can define a functor which does precisely that operation. But of course, in the language of Markov categories, you end up with some normalization problems there. So you have to go there. And about your question, then I'm not sure how to.
That is at least more satisfying to me.
Yeah.
Yeah, so you said that a stock doesn't have these conditionals. Does it mean that also this Loregian criterion does it like also fail to come to the construction?
I think so, because if you look into wait a second, into the existence of conditionals here. This one here. So if we forget for a second about the input there, you have two outputs there. So you can think kind of a causal model also there, right? So of course you don't have the three inputs, the three outputs as you usually have, but you have two outputs, and somehow one term, the Y term, for example, is the empty set. So I haven't constructed an explicit example also, but if it's already failing in that simpler scenario here, I would expect that it also fails in the general setting.
You mentioned the hypergraphs, like algorithms on the hypergraph representation of string diagrams.
Mm-hmm.
Can you say more about, like, does this conditionals? Is this like a rewrite rule in that?
Oh, I'm not sure about that.
Like how do the conditionals interact with string diagrams representation?
I cannot give you an answer to that. I'm sorry. Perhaps if Tobias is online, I'm not sure if he has a better answer, but I'm not sure if he's online.
Yes, I am. Can you hear me?
Yeah, we can hear you.
Okay, so yeah, I think a free Markov categories basically never have conditionals, because it's only the equations that hold, are just only those that are enforced by the string diagram calculus itself. And in terms of a rewriting rule, I don't know. I haven't thought much about rewriting, but I imagine that it could be possible. Yeah, that one sort of for every morphism that one gets a new generator that corresponds to the conditional, and then maybe it could become a kind of rewriting rule. But yeah, I haven't really thought about it.
Hey, thanks for a nice talk. I'm aware that in quantum causal models, there is also some kind of deseparation theorem. So I'm wondering how far away you think the proof method you're using is to proving one of the quantum causal models.
Oh, that's interesting. I'm not aware of a proof of deseparation in the quantum causal model. I know that there are other ways of deciding compatibility of causal models. For example, one severe restriction here we had, but which is very natural for deseparation, is that we always have to that every variable has to be an output variable, right? We need some access to it, right? But you can also have causal models where you have latent variables, right? And there, for example, one criterion to decide compatibility there is the inflation technique. And I think, for example, the inflation technique can also be translated to Markov categories. There, I'm pretty sure. About quantum Markov categories or in a quantum way, I'm not sure about the structure of quantum Markov categories, for example, which would be a approach for that. But I'm not sure about if you can generalize it. But yeah, at least for more general causal models, I'm pretty sure we can extend that compatibility problem also there.
Okay, let's thank you again. So now our next speaker is Carlo, who's going to talk about the category-theoretic proof of the rhetoric.
All right, thank you for having me. So we're gonna talk about ergodic theory, which is for some people something like an expansion or like a derived field from probability theory. Think a little bit like geometry and topology. And there's a lot of concepts in ergodic theory that I think lends themselves very well to treatment using categories because they're very conceptual. And they're about like dynamical systems, which as we know are some types of arrows, but in a little bit of a different way from how we've been doing them in ACT. But let's first try to see what we mean by ergodicity, okay? Because that's the central thing that we want to look at. So ergodicity, why does this doesn't work? Okay, all right, is a situation where all the mass is well mixed. Okay, so imagine that you're like putting milk in your coffee and wait long enough, or like spread butter on bread, and at some point you want to see that every molecule of your thing can be perfectly exchanged with some other molecules, but just acting on your system, okay? So for an example, let's take a group, say a disk. Imagine this is a disk like a vinyl that's rotating, and we're in a situation where there's a measurable space and this acts measurably, all right? So you have a point of your space, which can be, let me say, smeared or spread along its orbit, okay? Now, of course, if M is a monoid as opposed to group, orbits are not this nice. So they may start at some point, but not go back. But for groups, orbits are much nicer, all right? So this is a situation, and now we put measures on our space. And the generic measure, imagine a pile of mass there, can go along with the action of the monoid, all right? By just a push forward, which is defined in the usual way for measures. Or if you want measures for a monad, so they're functorial. So if we have a diagram, we get a diagram at the level of measures. All right, so what makes now a measure somewhat very well mixed? Okay, first of all, something that's very well mixed needs to be very well spread, okay? And so an invariant measure is a measure such that if you rotate it or you act on it, it stays exactly the same. So that's called an invariant measure, but this is not yet ergodic because you see that, for example, no amount of rotation can replace a block in the outer circle with a block in the inner circle, all right? So you would like to say that an ergodic measure is not only invariant, but in some sense, it's uniform along each orbit and supported on a single orbit so that everything can be interchanged with everything. But first of all, as I've mentioned, if we have a monoid as opposed to a group, orbits are really not the thing you want to look at. They're like not nice enough. But also, we don't have a notion of support because we don't have a topology. So this is just a measurable set that doesn't really tell you where the points is. It's not a topology. It kind of only tells you how big these things are. And also, we don't have a metric. So we don't have a notion of saying that something is uniform. We cannot say the derivative is 0 or anything like that. Okay? So an invariant set is a set that basically has this property. Each point is in the set if and only if it will still be there after applying your dynamics, okay, for every element of your monoid. So in the case of groups, orbits are invariant sets, but you see also unions of orbits are invariant sets, okay? If it's not a group, if it's a monoid, it's a little bit more complicated. So we look at now the measurable sets which are invariant. They form a nice sigma algebra. And now we say that an ergodic measure is a measure that gives either all the mass or no mass to each invariant set. Now you see this one here will give measure 1 to each of the invariant sets that include like this middle circle, and 0 to the ones that don't include it. But a more generic invariant measure, you see, will give measure not 1 and not 0 to the orange part and also to the rest of the part, okay? So that's the definition of an ergodic measure. An ergodic measure is a measure such that it gives all the mass 1 or no mass to each invariant set, all right? Okay, so you might already suspect this. Well, it looks like you can always decompose any invariant measure into all these pieces, all these subsequent circles, and get a decomposition into ergodic measures. And that's indeed the case. So it's a famous result that says that every invariant measure is a mixture of ergodic ones. So this one, for example, is a part of this plus a part of this for a part of this. And all the components are ergodic, okay? Now, okay, in general, of course, you have to imagine this is continuous. So there's not just 3 levels. So imagine, for example, infinite amounts. This could be a Gaussian, and you have to make it like an integral of these. So there's some measure theory involved in proving this statement. And also there's this idea that here we have a group, so orbits are particularly nice. In general, things are a little bit more complicated. But I hope that this picture gives you at least intuition that the ergodic measures can be seen as the basic building blocks of all the invariant measures, all the like equilibrium things. Those of you that have worked in things like Monte Carlo simulations that use Markov processes might have seen something similar. Sometimes you have several equilibrium points, but there's like these basic components, and those are the ergodic ones. That's an instance of this idea. Okay. All right. Let's now try to make sense of this theorem using Markov categories and try to understand ergodic measures a little bit more. Okay, so we saw in the previous talk already what a Markov category is. We have processes that which we draw string diagrams going up that are something like random transitions, for example, Markov kernels. Tensor products mean that these processes take place independently, and the processes of the from the monoidal unit are states. So for example, something like a random state, a probability measure on X. Each object is equipped with this copy and delete maps that make it a commutative comonoid, and the delete map is natural. All right, so I'm not gonna spend too much time on this since the previous talk was already very well explained. The 2 main examples that are of interest for us are finstock and stock. So one is basically stochastic matrices, the things that have discrete conditional probabilities and are composed just like matrices, or stock that are basically the same, except that you have integrals, and instead of evaluating the probability at points, you have to evaluate an entire measurable set. So it's the probability of ending up in that set, because single points usually have probability 0 or in general. Okay. So these are these two main categories, and there are some concepts in probability theory that you can express in terms of Markov categories, the most structural things, and which play a role once we move from probability to ergodic theory, to like dynamical systems. So first of all, maybe the most important notion is the one of deterministic morphisms that say, basically, if this morphism involves some randomness, then if you do it twice, you're not going to get the same result. Okay? So if, for example, f is like roll a die and add that value to a, and that's your x, then you see that, of course, this is random, but these two things are random in a different way. Because the two instances of x on the left are going to be perfectly correlated. Those two values are going to be random, but equal. Okay? Perfectly correlated. On the right, we're throwing the die twice, and so the values are going to be perfectly independent given the input. All right? But you see also that if there's no die involved, if there's no randomness, then these two things are equal. So that's like the definition of something deterministic in a Markov category. All right. In Finstock, these are just the 0, 1 stochastic matrices. Like, for example, if they're squared, they're just permutation matrices. And in stock, these are these kernels that index measures that have only values 0 and 1. So that already should ring a bell that ergodic measures should fit here, and that's going to be exactly the case. But for us, for now, you can think of them as those measures that are perfectly sure about whether something happens or not. So each event has probability 0 or 1, nothing else. All right. So an example of deterministic measures are Dirac deltas. So they're really states that are really just points, if you want. But there's more. Okay. And this is going to be crucial that these are not just basically two index points, but this idea of 0, 1 is, in some sense, more fundamental and will allow us to talk about ergodicity. Markov categories come with the notion of almost sure equality. So you say that f and g are p almost surely equal for some state p. You can also do it for more general morphisms. Here we just need states. If this diagram holds, if this equality holds, so in the finite case, that's just saying that they are equal on the support of the measure. And more in general, it means that they only differ on a set of measure 0, and everywhere else they're equal. Okay? So this corresponds to the usual notion in measure theory, but it's just an algebraic equation for us. Another thing we need is conditionals. So this kind of conditional is a little bit simpler than the one in the previous talk. So it's, first of all, just for states, but also we require this only for a special class of objects and morphisms. But you see that if you call Q this distribution, it gives you some kind of Bayesian inverse. So the formula in Finstock is basically the Bayes formula. And in the continuous case in stock is basically the same, but now for integrals. Okay. If f is deterministic, then this is a little bit like coarsening to a course of sigma algebra and doing conditional expectations. So this situation is particularly simple if f is deterministic. And when this holds, we say that x satisfies a disintegration theorem. So standard Borel spaces satisfy a disintegration theorem regardless of y and regardless of f, as long as f is deterministic. Okay, so here we are requiring less than in the previous talk. All right. Turns out that this is all the measure theory that we actually need in this talk. So if you want end of the measure theory, really. The first new things that we first did for Markov category is how to talk about convex combinations. How do you decompose states? So we want to say that the measure P on X is, for example, a convex combination of these two measures Q1 and Q2. And you see, this looks like additions of real numbers. So when one might ask, where's the category theory here? This is as numerical as it gets. Not quite, because this is a convex combination. So the lambdas are non-negative reals, and their sum is 1. But we have a way of talking about it. That's just a probability measure on a 2-element set. What else is that? No? So we're saying that P, which is a morphism from the monadal unit to S, is a composition in the categorical sense of lambda, which is a measure on 2, and Q, which maps each point of 2 to a measure on X, like Q1 and Q2. Okay? And this mixture is exactly the categorical composition, or matrix vector product. Nobody, of course, forbids us to use integrals instead, and it's just the same way. So what is going to be a decomposition of a state? Well, that's just basically a factorization of it in terms of categories. And in the middle, you don't just put 2, you can put 3, 4, 5, or even an infinite set. And the measure on that infinite set will be your convex mixture, okay? So this is a way that can be done in arbitrary Markov categories. Let me also mention, this works for measures, but for states, for non-states, for arbitrary morphisms, it's not quite like this. You might know the reason is that Markov kernels form polytopes, but not simplices. So their convex combinations are like not what you think they are. But for states, this works very well, and that's what we're going to need. All right, so that's the first ingredient, the decomposition, because we want to talk about the decomposition theorem. The second ingredient is how to talk about invariant measures, but that's easy. What is an invariant measure? Well, measures are just states, and cones are invariant measures, like the things that make the Zygon commute. Slightly more complicated, what are invariant sets? Well, what are invariant observables? Invariant observables are functions on your space that make this triangle commute. Now, if this map S is deterministic, especially if the object S is like a 2-element set, and those are precisely the invariant sets. And more in general, we can talk about a deterministic map from X to X that commutes with M as an invariant observable, okay? And you can prove that if those are measurable, then for every pre-image of a measurable set of S is an invariant set of X. So the categorical way to talk about invariant sets is basically as deterministic co-cones out of your dynamical system written as a diagram for each M. Okay? All right. Co-cones are classified by co-limits. So we can look at the co-limit of our diagram, but we want to look at a particular type of co-limit. So for the ones that are versed in enriched category theory, if you want, it's enriched in pairs of sets. But for us, it's just saying that. What is the usual property of a co-limit? Well, basically, if you have an observable S and this co-cone, then there's a unique map from this co-limit to S. Now we add the requirement. If the arrows of the co-cone are deterministic, so is this unique map. Okay? So in particular, the arrows of the universal cone, of the co-limit cone, are deterministic too. These are. The same measurable set X as before in the case of star. But now with a different sigma algebra as the original, namely the one only of invariant sets, is exactly the co-limit in this sense. So you have a categorical characterization of the sigma algebra of invariant sets. All right. What are ergodic states now? Well, okay, first of all, we want ergodic states to be invariant. So P needs to be invariant, as in the previous page. We also want them, remember what the definition was, these need to be 0, 1 on invariant sets. So basically, we want to say, okay, take any deterministic observable S. The resulting composition, which is now a state in Y, needs to be deterministic. And those of you that like universal properties might realize that's the same thing as if Xinv exists. That's the same thing as saying that R composed P is deterministic if the colimit exists. All right. So I want to say that this condition you saw in the beginning of ergodicity that seems a little bit ad hoc or a little bit technical, right? Because when I say, why can't you just talk about orbits? Well, you can't because of technical reasons. You have to come to invariant sets and say that something is 0, 1. It looks very technical. In the categorical formalism, this is the most natural thing you can do. It's a lot simpler to use category theory. It's just you take the colimit, and the resulting morphism needs to be deterministic in the sense of Markov categories, which fits perfectly here. Okay. So I want to say determinism in Markov categories does not just capture Dirac deltas, but also ergodicity. So it's some more general thing that encompasses both of these concepts and possibly more. All right. Okay. Well, we're ready for our main statement. So take a Markov category, take a deterministic dynamical system with an arbitrary monoid of arbitrary cardinality. Suppose that the disintegrations exist, for example, Sander-Borel, and suppose this Markov colimit exists. Well, then every invariant state can be written as a composition such that K is Q almost surely ergodic. So if you instantiate this in the category stock, this is just saying that if you have a measurable dynamical system, actually even a bit more general than that, but in particular, if you have a measurable dynamical system on a space that has this integration, then every invariant measure is a convex mixture of ergodic ones. All right. The proof is so simple that it's just string diagrams. So you form your conditional of the map R, the one that goes to the colimit, and now everything else is just string diagrams. So this, for example, shows that we have that the resulting measure PR is almost surely deterministic. This shows that it's almost surely equal to the identity. We're basically just using the original equation and the fact that R is deterministic, which it is because it's the arrow of this Markov column. And the other part of the diagram that shows that the measure Q is P almost surely invariant, again, follows the same thing. So for example, this first equation is again using a conditional. Then here, the second one, we are using that R is invariant. Then we're using the determinism of M and so on. So this is just following these basic building blocks of string diagrams. And this is already the end of the proof. So no measure theory. The measure theory was just in the fact that those conditionals existed, but we can just focus on the conceptual aspects and see where each things enter. For example, where does it enter that the monoid acts deterministically? Well, that's the equality in the middle. You see, we're copying M. So to conclude, this is, of course, one small result in ergodic theory out of many. Hopefully, we're going to be doing much more in the future, but it already gives us a lot of insight into what ergodic measures really are for us as category theorists, and how to do some things like talking about mixtures without having to actually sum real numbers. Also, I think this demonstrates quite well how you don't need measure theory except to build one of the blocks, and then you can just use that block without having to open the box. You don't have to worry about any of the measure theory once you have these integrations. We hope that using the same formalism, in the future, we're going to be able to talk about more stochastic stuff, so stochastic dynamical systems as opposed to just deterministic, which should work in a Markov category, and possibly also the main ergodic theorems, which are about tending to these uniform measures, a little bit like law of large numbers style, which should be like our ultimate goal. Hopefully, next time I'll be able to tell you something about that. I'll stop here. Let me just mention, if you want to know more, there is this paper that just got on the archive, which explains more in detail all the stuff that I have presented today. Okay, thanks a lot.
Thank you for the talk. I think we have time for one quick question, and in the meantime, the next speaker maybe.
Yes, I did have.
Okay.
So classically, ergodic components are related to sufficient statistics.
Mm-hmm.
Have you thought about any connections?
Yes, I've thought about that, but I still don't have a definite answer. But I believe it's we can express that in terms of Markov categories too.
Awesome.
No. Thanks.
Check which one it is. Is it like use this one? You might be like use this one if you check in the Dropbox. Is there only one? Okay.
Let's see.
Yeah. Where is it?
Oh, use this one. Okay.
Yeah.
No. Use this one.
Yeah.
Let's use this one then.
Yeah. Is that good? Oh, yeah, sure. Can everyone hear? All right, cool.
So it's my pleasure to present
The room.
okay. And he's going to talk about non-probabilistic graph of categories for causal modeling in machine.
Okay. All right. Hi, everyone. So before we start, here's the little outline. So there's gonna be a lot of motivation for why we're going to be doing this. Then we'll discuss how we apply category theory, and then how we can use string diagrams specifically to do quite a lot of interesting stuff in causal inference. So the motivation for causal inference, first of all, is the fact that machine learning itself is quite useful at modeling really large data sets. However, it's very causally blind, let's say, because you get quite a lot of spurious correlations. One fun example I like to use is the fact that if you wanted to give like a machine learning model data on climate science, one of the correlations that will come back with is the fact that pirates in the 15th century have all died off. And if you look at it, it'd be like, if we looked at just correlations, we'd be like, that's the cause of climate change, which, as we all know, I think it's not the case. So causal modeling, what is it? So essentially, it's a probabilistic method in which we can measure causal influence on one event onto another. And we typically represent it through a DAG model. So here we have an arrow from A going to B to represent A having a causal influence on B. So when we have an arbitrary DAG, we then represent its probability distribution via this equation. And we use the do operator to simulate causal interventions, or sorry, experimental interventions, and we change the DAG whilst we do this. So when we do this, we denote it by having P of Y given do X, which essentially deletes all incoming arrows and replaces it with a constant X equals X. So here's some interesting examples from causal modeling. So if we were interested in the effect of a drug on a patient's health, and there's a confounder in the age of the patient, so we could represent the causal DAG like this, where the age is influencing both the health of the patient and the how the drug might be responding to the person, since that's how drugs work. If you're older, you might have a different response. And obviously we have the drug affecting the health. We use the backdoor model to essentially understand what the causal effect of taking a drug would have on a person's health. So a much more famous example as well is the front door example, which is something that you can use to measure about whether or not smoking could cause cancer in the lungs. So if we have, if we assume that smoking is X and it affects tar buildup in the lungs, M, and then which also then affects having cancer in the lungs. But we're interested because there's some maybe cigarette executive saying, well, hang on a minute, there might be some kind of unobserved variable that we don't know, a so-called smoking gene. We should have that in the model, just so that we're all fair and like, you know, it's not just one-sided. Well, we could then make use of the front door adjustment in this case to then say, well, we actually can show that smoking does indeed cause cancer, and it's not some kind of smoking gene. So why do we need semi-fields in our formalism? So in order to normalize, we need an algebra that has a multiplicative inverse, and for our purposes, no additive inverses are needed. And quite usefully, in fact, semi-fields can be used to represent some machine learning models, such as the min plus semi-field, which you see quite a lot in like deep learning applications. And we also have the probability semi-field here. So the definition of a semi-field is essentially the same as I think a talk was given earlier today. It's essentially just a field, but we put on some restrictions into it. And now, so this is now us defining the category. So essentially, we use a Markov category as defined in Tobias Fritz's paper, but we define a semifield Markov category wherein we have some underlying semifield, as we have here, which essentially defines the composition. And then we also have a special case, which is what we'll be using mostly in this talk, called the affine semifield Markov category, where we have an associated terminal morphism for each object X. So if we have a semifield as we defined before, where we have like a O times no plus, composition between two morphisms is then denoted like this, where we have a big O plus over the Y and using the multiplication. And then we also have the affine requirement over here. So when we want to describe marginalization, we assume that C is an affine semifield Markov category over some arbitrary semifield S. And essentially all the marginalization requirement is that we're just using the affine requirement for computing it. And normalization is exactly what you'd expect it to look like. Yeah. And extraction is essentially just taking out one of the variables from our morphism and then normalizing the morphism overall. Again, this is pretty much what we expect it to be. Nothing really groundbreaking here. But quite fun, what is quite fun is that we can actually use these categories to essentially do some fun stuff in machine learning. So like here, state normalization under the min plus semifield. Essentially, when we compute all of this stuff here, we essentially can get the Lomax distribution, but instead of having to get it in the standard way, which is via integration, we've done it by differentiation through minimization, which is quite useful, trying to sidestep integration essentially. So now we define a semifield homomorphism. Essentially, it's the same as any other kind of homomorphism that we'd see in group theory, but just applied into semifields. And then we define a functor between our affine, that should say semifield Markov categories. Essentially, it's just applying the semifield homomorphism onto any morphism, semifield homomorphism onto the morphisms in our category. And on objects, it leaves them essentially unchanged. And quite interestingly enough as well, if you have an isomorphism of semifields and you were to build a semifield transport functor on top of them, you'd also get an isomorphism of categories. So quite an interesting application into machine learning is the information transform here, where we can actually go from the probability semifield into over here. If we see like before the oh, how do I use the like little red dot? Oh yeah, okay, cool. So yeah, if we see here, this is essentially what we call the soft min plus, and when we take it to the limit of a equal a to infinity, we can essentially obtain the min plus semifield from the probability semifield. So essentially we can start doing computations probabilistically and then talk about it in like a machine learning perspective and vice versa. So now we then go on to our idea called the fixing morphism, which is essentially take an idea from causal calculus, which is so-called fixing operation, which essentially generalizes the idea of conditioning on variables in a DAG. And yeah, so we represent morphisms of the type x to dy in the form from down to up. And then if we have multiple inputs into a morphism, it's just like that. And if you see a copy is just like any sort of standard copy, and having a deletion at the end is just done by a black dot on top of it. So if we have a DAG that has this sort of structure, we can then represent it in a string diagram notation like this. It's essentially using like the same idea that Jacobs and Kissinger had in their string diagram for, I think it was string diagram surgery. It's the same sort of idea here, where the morphism at the bottom here, A, encodes the probability of A. The morphism B encodes the probability of B given A. And if we have a variable that's unobserved, then this output wire, so the one that goes to capital A, will just be it just won't be existent. So now we generalize the idea that they gave in that paper, which was a they called it the cut functor,
which allowed you to do causal intervention. We take this to a new level called point state cut functor, where their limitation was the fact that it used a uniform state, whereas we use a point state. So essentially it acts more like a Dirac delta distribution. So it is more closely aligned to what you'd expect to see in like a causal intervention where you're intervening on variables with like an x equals x. In your interventional distribution, whereas the uniform state was just one value over the entire distribution. So now we talk about marginalizing on a string diagram. So if we have a morphism where it has an output of A and X and an input of W, to marginalize out X, it's just a very simple following manipulations. We essentially use the affine property of the category to discard the output of X. And then we're just left with the morphism F of A given W. And now we describe the fixing morphism as such. So we marginalize out all the inputs to the morphism we want to fix on. We replace the morphism with an identity wire. We then extend this new identity wire to become an input to the entire diagram. We marginalize out the variable we want to fix at the output of the diagram. And then after fixing, we include a point state for the interventional variable added at the input of the complete string. So here we have quite a nice example. So if we're fixing on X, in this example, it should be a small x here. Sorry about that. Essentially what we do here is we've deleted or we've discarded X here at the output. And since this is quite a simple example, all that happens is we then join a little point state here and we end up with something that looks like f of A given X and W. Some cases which we show whilst we're writing up the paper is that we can actually have something where X might just be marginalized out in certain cases, which is what you want to see since fixing should act like a generalized idea of marginalization and conditioning. So, and on obviously on morphisms where the fixing variable isn't present, it's just left unchanged basically. So now we talk about the topological properties of causal strings. So we have to define an idea called a district, which are essentially a set of unobserved common cause morphisms, and they provide inputs to other variables. So in this one, we can see that the district here is f of x, y given z, since, let's see, just this little shaded bit that I've highlighted here. So rewriting the backdoor adjustment through fixing, we can actually have a backdoor string diagram represented like this. When we apply fixing to the diagram, it simulates intervention on X by obtaining this morphism here. So essentially, we discard the output, put a point state at the bottom there. And then after diagram simplification, we get this. But if we remember what the backdoor adjustment formula looked like, we had like a little summation of what would be here C over C. So to do that, we then marginalize out C. And this is exactly the backdoor adjustment formula that we wanted. And then for the front door, usually it's quite difficult to actually do the front door diagram in string diagram notation, since you have an unobserved variable hitting two input variables. So what we use is an idea called latent projection. So essentially, it's an idea in causal modeling where you can just take away an unobserved variable and turn it into a bidirected edge. So essentially, just 1 hour doing this. How am I doing on time? 10 minutes? Oh, okay, I'm nearly done. So when we want to do the front door adjustment through fixing, we essentially start with our little factored front door diagram. And we can identify Z as a district here, and we have a valid fixing sequence of X and Y. So first of all, we fix on Y. We obtain this diagram. Then after fix on X, and through some diagram simplification, we essentially eliminate X at the output. And then this is the final kernel diagram for this district. And then once again, we then can identify a district in Y with a valid fixing sequence of X and Z. So once we fix on Z, and after some diagram simplification, we then have this. And then after fixing on X, since X has no children in the string diagram at this point, as we can see here, it just, there's nothing that goes into X. we just obtain something that looks like this. But interestingly enough, when we look at the two final kernel diagrams that we had, we can see that the Z here corresponds to the Z here. So we can actually compose these two sequentially. And if we adhere to the topological consistency, so Z goes to Z, we can then obtain a diagram that looks like this. Once again, though, at the end, we have to get rid of this X, turn it into a point state, because that's how we define fixing. And the point state becomes the input of the diagram. So then this results essentially in the front door adjustment formula as desired. So what we've done here in this work is that we've introduced a method in which to conduct causal inference in a non-probabilistic setting. We've shown how it's possible to create a formalism in which to conduct causal inference and machine learning together. And hopefully we can actually find some more examples of this. Yeah, that would be actually one of the interesting future works that we would like to do. We can actually apply do calculus problems with category theory. And as a matter of fact, one other future work that myself and Max are really interested in is actually trying to completely rewrite the do calculus, but in the string diagram formalism or even category formalism. And this gives us a novel approach onto and a new perspective on DAG models, specifically when it comes to topological ordering. Yeah.
Todd, are there any questions?
Can you go back to the slide?
Yeah, sure. There's a lot of slides, yeah. Yeah. Yeah.
Like requirement that has to be like convex diagram, or is it like in can be more general shape?
I think it can be a more general shape, yeah. Like it can take a like, yeah.
Because there is some like complications if you rewrite regions of string diagrams that are not like convex regions.
Right.
So I'm just saying you should like
yeah, okay.
keep that in mind.
Okay.
Any other questions?
I'm very interested to talk. I'm just kind of wondering about where you can go with this. Is the idea to do machine learning when you know sort of the network, the causal network? It's not the technical term.
Yeah.
The idea to discover causal relations from data using
Yeah. Yeah, eventually we'd want to be able to like do the two in tandem so that we can find correlations in a machine learning algorithm, but then use causal inference to be like, well, is this actually a spurious correlation or not? And yeah.
Thank you.
Any other questions? We can thank the speaker again.
Is it photo time?
Right, no rest for the weekend. Let's have the group photo outside now before we have the coffee break.
Hi, Ryan and Spencer. Can you hear me?
I do. This is Spencer.
Yeah. So I made you both co-hosts, which means that you should be able to share your screen eventually.
Let's see. Oh.
Yep, looks good.
All right.
Okay, so we've done some small changes to the order in the program. So maybe I'll just put it in the chat so you know when to be ready. I'm not sure, Ryan, if you want to try something out. Oh, you can't unmute yourself. That's not deliberate, but. That's a bit strange. So the allow participants to unmute themselves button is ticked. Let me remove it and tick it again. Yeah, try to rejoin. I think that would be good. I noticed, Joe, that everything you're saying is picked up by the subtitling.
Wait, is it like it only fixes the sound or something?
Testing.
That sounds good.
Huh, weird. Go figure.
Do you want to try and share your screen as well? Are you still a co-host? No, you're not. Let me make you a co-host again. And now you can try and share your screen.
Yeah, but I think it's very well.
Can people see my screen? Like there's nothing there, but it's.
Yes, I'm a bit scared of your desktop, but.
Okay, cool. Now how do I stop the share? Oh, it's on my other monitor. That's fine. Oh, yeah. Okay. I have to be careful to pick the right window.
Right. Yeah.
Okay, I'm good.
Good.
There's at least one group that's having trouble logging in because of the, like, you have to, anyway, I'm seeing email that, yeah, so just FYI.
Right. Okay, let me see.
The idea of, I don't know, I mean, soldiers handing out big students, like, oh, as in, it's like this obsessively masculine. It's like
Okay.
practical, like super decorated sword.
That's. Do you know anything about this, Malin? Is it possible to join this meeting without the Zoom client? Can you do it from the web?
Probably, I can try to open.
normal sort, not like one of it is so strange. It is so strange. Seems to only but you know, like any film that has yeah, so if you have a weapon which is like the amount of military, the only way you can use it is if the text on the script. So every time you see it, military, you know, oh, the Pentagon looks at this, and we're like, this is okay for us. And when we don't,
Okay, you're all set.
Updated presentation.
Yes. Yeah. Right, but can you sign in and then do? I mean, I already asked Brandon to do this, but
Advertising.
right. I think, Spencer, maybe if you just share your screen.
You have mixed states like and then like somehow like you're uncertain about like the entropy of like something where you're yeah, like bring have a more probabilistic.
Hi.
I'm speaking last.
You're speaking last. Nope,
And then,
that's
and
it.
then somehow bring in like it could be like a strict something that was like more strictly convex would be like the
Okay, everyone. We have a quite tight schedule for this session, so I'm going to be rude and just cut off all your interesting conversations. So this is the industry session. Jules has found lots of interesting industry speakers for us, and then he decided to get COVID so that I had to do all the difficult timing. So we have 8 minutes per speaker, and I'm again going to be rude and make sure that they stick to these 8 minutes. So it's going to be a worldwide tour of interesting companies working with categories in some way or another. And let's just start with the first one, who is Spencer Brainer is going to tell us what they're doing with local models at NIST. Take it away, Spencer.
Okay, thank you for having me. Thanks to the organizers and also for the opportunity to mentor in the summer school, which was a really great opportunity. So I'm going to talk a little bit about some work we've been doing at NIST on integrating category theory. We're trying to approach systems engineering with category theory. So the central thesis really of this project is that the model of a system should be a system of models. So down here on the left, we have a picture of a refinery or a chemical plant. And if we look inside at what's going on, then there's a distillation column somewhere inside. And if we look inside that distillation column, it has many layers. And we can look inside each one of those layers and look at the flows that are going through those. And if we zoom in on those, then eventually we get down to some sort of concrete material thing that we can touch. And so there's a lot of ideas that connect the things that are going on at the bottom and the things that are going on the top. And we would like to be able to take all of the models and the data that we have about these things and put them together more easily. So that, for instance, we can ask questions like, if I change some feature of the material up here at the top, how is that going to impact the flow rates and the output of the factory? How is it going to impact the cleaning schedule and the maintenance schedule, because there are many sort of different questions that feed into the things that we care about at the top. And so in order to kind of frame all of this information, we've been looking at kind of a four-part structure that involves these things that I'm calling local models at the bottom, and also process and structure, hierarchy and abstraction, and data and computation. And each one of these corresponds to some piece of categorical machinery. So the local models at the bottom are written in functorial semantics. The processes and networks are described in terms of diagrammatic syntax like string diagrams. Operads control hierarchies and abstraction, and C-sets or O-logs, sort of general approaches to categorical data and logic, allow us to put in the details and connect with computation. So by local models, I'm just going to sort of give you a few examples and then zoom out a little bit to see what we can't do with them yet. So this first model involves two pieces. There's a stepper, that's F1. So it gets a value in and it steps it by 0.1 value. And then it also takes some kind of Boolean reading on that value and then sends off the truth value that it sees. And the second component is B2. It takes two arguments. One is a Boolean value and one is a natural number. And if the Boolean is true, then it counts one. And if it doesn't, then it just leaves it alone. And so we can compose these at that Boolean value and we get a new function that goes from R times N to R times N. And of course, now we can iterate this thing and look at its dynamics and you get the plot that you would expect to get, where the stepper steps basically linearly, and the counter counts linearly, but then enters and exits the region that is being tracked. Now, of course, we can change one of these components and we get different dynamics. So now we're sort of doing something more complicated and we get something funnier on the other side. But we can also, so that's one thing that we can tune. We can sort of tune the components that we put in, but we can also tune the sort of the type of components that we put in, the semantics that we're using. And so maybe now we're going to step with some kind of tolerance. And so now when we advance this process, we see that tolerance expanding out in the way we expect, but we also see that that uncertainty flows through into the deterministic process. And so we can also do the same sort of thing with probabilities. So maybe we don't want to add a fixed tolerance. We want to add some kind of Gaussian error. And then we're talking about things that are happening maps in prob, right? And we can analyze those with Monte Carlo analyses. And so down at the bottom, we have all of these sort of different kinds of formal methods to describe the things that we care about. And one of the things that holds all of these together is the fact that they are referring to the same processes or the same networks. So here Q1 is the stepper and Q2 is the counter. And we can use this diagram to construct some kind of free monoidal category. And then we can represent each one of these different models as a functor from that category into a target semantic. So whether it's sets or rel or prob, it doesn't really matter so much. And so that allows us to live at the high level and sort of not go down inside if we want to. For hierarchy and abstraction, though, we need to recognize that this process that we're looking at is just one of many processes that's happening in this system. And so we can use the fact that string diagrams and various flavors of string diagrams form an operad to give this sort of dual representation where now I'm thinking of the hierarchical structure on the right as being a picture of the same thing as the network structure on the left. And when we do that, it's sort of much easier to see that the process that we were analyzing in the first place is just one small piece of the system that we're looking at. And maybe it's not down at the bottom, maybe it's in the middle, and we have some other things underneath it that are informing the dynamics that we put in there. And so then that starts to guide us towards thinking about how we might put these models together. And more generally, because string diagrams form an operad, we can talk about attaching string diagrams to each node in this tree, and then assembling processes that, that sort of allow us to zoom in as far as we want on individual components, while also leaving other components black boxed at a higher level. And so this is one way to zoom into a component process, to zoom into a system process in terms of 12 components. Okay, and so then the last corner of this diamond that I showed you is data and computation. And so if we go back to that first model that I wrote down, there were some magic constants in there, right? So how did we know that we were stepping by 0.1 and that 0.5 was the limit that we wanted to analyze this dependency against? And what we would really like to do is actually replace those by some kind of parametric representation so that we can explore possible design spaces. And what's really critical here is that when we change a parameter in one model, it needs to change everywhere because we're talking about the same materials. And so if we change something that's going on in that distillation column, then it's going to have an effect that resonates throughout all the models that depend on that distillation column. And so we need to have a way of embedding all of that information in a way that we can query it out to get the things that we need, but also sort of let it sit next to this additional parameter mu that we're not using yet, or that we're using somewhere else. And so now here's a very provisional definition of what a systems model might look like based on this sort of an analysis. So we would start, the mathematicians and engineers always start at opposite ends. So mathematicians start at the top and engineers start sort of in the weeds. But for mathematicians, we want to start with that abstraction operad, which will often but not always be a free operad. Then we're going to attach diagrams to the nodes, just like I said, by using a functor into some category of string diagrams. So the particular doctrine that you want to do, whether it's symmetric monoidal or compact closed or hypergraph categories, doesn't matter so much for the particular representation, but really this is a place, analyzing the relationships between all those doctrines is something that still needs to be worked out. We also want a query functor on that abstraction operad that's going to attach both a schema and an instance to every one of the objects in that operad, which somehow represents an abstraction layer in the system. And then from the diagrams and the queries, we would like to construct these local models. So the idea is that a particular local model should involve a context assignment that is an arrow in this operad, often built up from multiple layers. We want a semantic category that is going to be the target. And then we need a semantic functor that lets us take the data that we have and the diagram that we have attached to the, so we have a context, that's a subtree in our larger tree, like the one I drew here. That's what A here represents. And then we want to get a functor that attaches to every instance of the associated schema and to every diagram that can be constructed in the associated process or in the associated diagrammatic category, a semantic functor. And so this basically is just going back to these guys and saying that we're going to fill in 0.1 and 0.01 and n+1, we're going to change those values to be parameters and then allow them to vary according to what we have in our database.
Sorry,
and so
Spencer,
as I said, that's very provision. Yep,
that's your minus 30-second warning.
Yes, thank you. All right, so as I said, it's very provisional and there's a lot more to think about, both in terms of the dependencies that are going on with both of these diagrams and the kind of lensy information flow that goes on from the top level to the bottom level. And so we're working on trying to build some implementations that will help us test out these ideas. But this is something that I think category theory has a lot to add for systems engineering. So I'll close it there. Thank you.
Thank you. Right, so there's no time for questions, but I'm sure all the speakers will be delighted to if you reach out to them with anything. So next up, we have Ryan Wisniewski from Connexus. So take it away, Ryan. Thank you. We can't hear you if you are saying something. If it's interpretative mouse movements, then that's...
There we go. I had to
There we
unmute
go.
myself.
Excellent.
Yeah. Okay. All right. So yes, my name's Ryan. I'm going to be talking about Connexus. So this is going to be a company overview. We have a poster had a poster about algebraic property graphs in the session a few days ago. So hopefully people were able to catch that. So anyway, what is Connexus and what do we do? So we're a startup. We came out of MIT around 2015. Our goal is to commercialize functorial data migration. So this is a body of work originating with David Spivak. It's about co-presheaves and that kind of thing. I'll talk about it a bit after this slide. So we spun out with grants. Now we have revenue and venture capital funding us. Clients range from energy to banking to government. In all cases, what we're trying to do is use category theory to do data integration, data processing type of stuff. So we have a strong technical focus on how to do all that at scale, which involves a lot of automated theorem proving, these things called chase algorithms that do left con extensions and stuff like that. So anyway, we're also the developers of the CQL IDE. If anyone's been to categoricaldata.net and played with that software, that's us. And so we're looking to collaborate both with academics. You know, like I said, we had a poster and still do some research, but also people who want to integrate data commercially. You know, you can always go play with our open source software, but you know, we'd like to hear from you. So with that, I'll spend the rest of the time just giving a brief overview of like the kind of capabilities we're offering. So as Spencer mentioned, there's a lot of ways to use category theory to do what you might call model management. On this screen, you're seeing basically a finitely presented category up at the top, and then a co-presheaf, a set valued functor at the bottom. So we think of these as database schemas and instances. So the finitely presented category at the top, you know, you've got your generating edges, you've got your generating objects, you have your generating equations. So this is basically a database schema that talks about employees and departments. In your, you know, equations in your presentation say things like every secretary is the department for the same department that they are working in and stuff like that. So if you have data that looks like this, you can think of it as a co-presheaf, and you can use our software and many other people's software to do category theory to it. What does that look like? So if you have two categories that you're using to store data and you create either functors or profunctors between them, on this screen, the intention is to show a profunctor. But the idea is that when you connect schemas / categories together in this way, you can move data back and forth between them, like sort of bidirectional. You can push data along a profunctor and you can also move it back the other way, where these things are in an adjoint relationship, like here on the screen, they sort of invert each other, but in general, you just have an adjunction. So anyway, that's the kind of data transformation we do in practice. You can generalize that to also integrate data. So before I was just showing, like, here's a query, you're going to like transform the schema of some data. Here's basically a push out where we have two databases, one on the upper right, one on the lower left. We have some overlap that's in the upper left between them. We do a little con extension and then some co-limits, and we get this integrated database out in the right. So I know that's basically, you know, that's going to be too much for people to really understand what's going on. But the point I want to make is that we have real software that does this, and we have the kind of software that works with presentations of things rather than like full infinite objects. So this is a screenshot of this open source CQL tool you can download from categoricaldata.net. It has a textual rendering of that employee's department schema that I had before. And what you can do is, like, you can give it a handful of equations that say, hey, create the co-presheaf, the initial one that satisfies these equations that I have, and the tool will actually go and do automated theorem proving and construct an initial model, like including like symbolic unknowns. So in this like database that we've created on this co-presheaf, like not all the employees have ages. One of the employees has an unknown age, but there's like, you know, a rule in our category that says there's a cumulative age column that sums up like his age. And so you get these like unknowns in your data, and like everything's working as you would expect. So anyway, there's a few different ways to do like C-sets, attributed co-presheafs, and this is one particular way that is very expressive. So Like other cool stuff that the software can do, it can check functors and profunctors between categories using automated theorem proving. So this screenshot is just showing, somebody tried to create a profunctor between two schemas and they made a mistake, like they created something that wasn't functorial, and then the tool goes off and warns you before like even moving your data around. So lots of nice stuff you can do in the tool. And to support it, like we have to do a lot of automated theorem proving and stuff. So for example, you can give our technology the product category for groups. You say, here's my definition of groups, and then the tool builds a decision procedure so you can ask it equations like, is it the case that for every group element, if you square it, you get identity? Like, no, but is it the case that if you take something and then invert it on the right, that's true, even though like the equation we wrote down like says inverted on the left? And so anyway, to really do computational category, I claim you have to be able to solve word problems, like decide equations between arrows and finally presented categories. And that's exactly what the tool does. So this is second to last technical slide, just shows you how far you can go with this. So if you give the tool a presentation of the quaternions, for example, then you can actually build a Cayley graph, and it can tell you like, hey, there's exactly 8 quaternions, the 4 generators and their opposites, and they're related by this graph here. So lots of cool stuff you can do with decision procedures. And then just like at a practical level, you can like, the tooling we have, it's pragmatic. You can import, export JSON, RDF, XML, like all kinds of different representations of your data. This is just a XML-ish looking representation of something we already had. So anyway, I will leave it there. We are Connexus. My name is Ryan Wisniewski. You can reach me at ryan@connexus.com. Check out our poster, algebraic property graphs. And yeah, I will try to end there 1 minute early. Thank you.
Yeah. Excellent. Thank you very much.
Oops, I have to stop the share. There we go.
Is Kreshnik, have you managed to join the call? No. Okay, Brandon, I think you managed to join. Let me make you a co-host. Okay, so now, okay, we can hear you, great. And you should be able to share your screen.
Okay, sharing now. Let me know if it comes through.
Yeah, we'll do. Yeah, we can see that. Great.
Awesome. Okay, great.
Okay,
Well, thanks for having me. My name is Brandon Baylor. I work for Chevron as a systems engineer, and specifically in the domain of what we call assurance. So basically, it's about how do you take technical requirements or constraints or best practices and preserve the meaning and intent of those requirements as different people need to interpret them to do engineering work and to design the systems that we create here at Chevron. And we're exploring the use of category theory to help in this space. Particularly we're using CQL, as you see here. And the hypothesis here was like one that individual engineers could take existing models and convert them into OLOG form. So that was part of the point of this proof of concept. The other proof was to basically test whether you could enable model composition without pre-coordination or consensus. And why that's important is because a lot of the solutions we have today are focused on standardization or reduction or consensus-driven approaches to how we think about requirements or models or aligning information between multiple domains. So what we tend to do is get a lot of experts in the room and agree on a final model that supposedly represents us as a collective. But the reality is that there's not enough space to include everyone. We're working across time zones. We're talking about the scale of a global corporation here. So how do you reconcile these different perspectives while preserving their uniqueness and specificity that each person needs in their own domain, their own mental model to solve complex problems? So just moving through this quickly, we took an existing pressure calculation model that is very common in my domain. It's used to preserve sort of the anticipated pressures that engineers and people in the operations are expected to face, and that drives a lot of the design. So we took that existing model, and 2 engineers basically modeled it separately without ever talking to each other. And we tested how we could use the formality of category theory and the math to help us drive consensus on the underlying structure on how we could put our pieces together. Even though we may call things differently, even though we maybe decompose a problem differently, how can we help trust the math to compose and form an integrated view? So this is my individual OLOG, I guess you could say, in the CQL IDE that Ryan was talking about. Here's my schema, basically, which doesn't have any data here yet, but it's my tables, it's my my column names, and we used Excel basically as the form with which to create the OLOG and then ingest it into the CQL IDE here. So it has a very much a tabular form that's easy for engineers to grasp. Then you have specific data. So this is my data on the OLOG, and I just want to show a couple of the benefits quickly. One of the benefits you get through composition is that, say we have this calculation, which is very basic, but it's really integral to the overall pressure design. Through composition, what we can do is sort of simulate what happens if you imagine that value just evaporated from the model or disappeared. And the value of composition is that the system repairs itself in the sense because it can take another path to get from the source to target there. So, I like to tell people, imagine that a cell in Excel just disappeared and it would break everything, right? With no understanding of why or what it impacted. So that's really a cool benefit. Perhaps a more powerful benefit is, like, say I'm an engineer, I leave my job and some new engineer comes in. Maybe they make a local design change and they change this value of this calculation. Basically, the benefits of the automated theorem proving here is that I can see in near real time a contradiction that this created based on all the rules and constraints in a context that I baked into the model as a subject matter expert. And we can pinpoint exactly where the initial contradiction occurred. We could also present sort of the cascading effects of this. And this is really powerful when we talk about integrating systems across domains, because people are making local design decisions all the time, and others have to absorb those changes without any awareness or traceability as to why. So the provenance and contradiction detection here is a really powerful capability just in my individual OLOG model. So that was one part of the test, but we also tested, what if two people, again, like I said, two engineers modeled the same system, interpreted it completely differently, and how did you compose them? So, you've got my schema, you've got my colleague James' schema who participated in this proof of concept, you've got our instance data, you've got the definition of the quotient here on how we went about, creating the integrated schema, and you've got all the overlapping rules and constraints that you'd see in a typical, I guess, sort of co-limit construction there. So just to show you quickly what that looks like. So this is after I ran it in the tool. So we've sort of pushed the button and we get a couple things here. One is the individual schemas from each. So this is my schema. Again, my tables and columns from my Excel sheet. You've got James's version of it, which you can see they're different, right? So even though we were looking at the exact same engineering model and objects, we interpreted it completely differently that when brought into our respective worldviews. This preserved my individual data from the model. So this is one of my tables. It's a key to the calculation. I had 29 rows of data because I did more pieces than my colleague James. He only did 6 rows of data, even though this is a similar part of the calculation. So this is a key point, because when we go to integrate, he's going to get all the information that came from my my 29 rows. 6 of them are aligned, and we'll show how they are sort of fused together. But he's also going to pick up fresh information from me just by integrating in this way, and also being able to see it in his schema view that is optimal for him. And we can go and see that here in the co-product instance. So now we have 35 rows of data. So this is basically just adding his 6 to my 29 to get this total. But then we built these constraints and rules on top that said, some of these rows need to be glued together. And that's what these rules help define. So basically, we treated these rules as if they were like the overlap in the co-limit construction, and they helped with all the mappings and the functors and whatnot. And it allowed us to, smush together the overlapping rows based on the constraints we had provided, and preserve the rest. And so that's sort of what happens here. If we go to James's backwards schema, so now he's information went into the integrated schema, and now it's back propagating to his view of the world. So he got my information basically for free in his, structural view that made sense to him. So that's a really cool demonstration, I think, of getting emerging sort of insights without ever having to talk to each other. So James and I never we never actually coordinated to predefine these things ahead of time. We just based our understanding on this overlap, this general requirement, which is a guidance that's distributed across the globe for how we do this calculation. We encoded it as our overlap, and then we basically mapped back to it and then integrated based on that overlap. So that's basically the gist of how we're thinking about using applied category theory to help with model composition, to help with integration, and how to do so in a way that's scalable and adaptable. So I think I'm close to time, so I'll end there, and I appreciate you having me. Thank you.
Thank you. Okay. David, you're here, right? So I suggest we put you in the live block and we move on to Jelle.
Hi. Since I didn't have time to test, I assume you can hear me?
We can hear you. So whenever you're ready.
Good. I'll help you by not giving a very long talk. I wasn't actually able to finish a bunch of demos and things, but some of you have already been using some of our software on Statebox TV. In particular, I would like to give a shout out to David, who has by now done over more than, I think, 200,000 keystrokes on it. So David, amazing. We were a little bit, the background to this Statebox TV project was kind of born at the Statebox Summit. We were live annotating a lecture by David Spivak collaboratively, and yeah, this was very successful, and we wanted to try this at ACT, even though it's not necessarily the best format for it. At the Statebook Summit, we do more, we do less sessions, more research oriented, and more like, let's say, blackboard or whiteboard lectures. But yeah, very nice to see that this was actually useful, or at least being used. I'm gonna go share my screen. I'm not gonna say too much more. Let's say how this is work. Share screen. Okay. Yeah, I believe you're now seeing my screen.
Yep.
So, oh, this is kind of the year where I'm still in. It has been quite a dark period for us with very unfortunate timing with Corona and everything. But luckily, and crypto crashing and all of that. So, but luckily we are founded now. We're a very small team, me and another engineer, and somebody else in management. But we are working pretty hard on this. We ended up rewriting. We've done many years of research. Last 4 years have been lots of experiments, and we've been rewriting lots of things, or me in particular. And yeah, I wanted to mention, like, category theory is a little bit like having a hi-fi installation. You replace your speakers by, let's say, wiring diagrams. And now you realize your amplifier isn't so nice. So now you need to replace your amplifier. And before you know it, you're replacing your wires by very expensive wires. I don't actually do this, but we are doing this sort of with kind of all of computing. So we're writing our own cloud infrastructure, our own type system for messages, etc. Because if there's friction, categorically speaking, let's say, this amplifies, and we end up having a really hard time implementing things. So it's been breaking down, rewriting again, breaking down, rewriting again. And what you're seeing on my screen right now is what's running on Process.io. And I'll give you a short demo, for instance. This is a vending machine example from a computer file. I was watching it and I thought that's funny. So this is, for instance, how you would, you start the machine, and you can either put in 10 cents or 5 cents. If you 5 cents, then it's like you have 5 cents in the machine. You put another 10 in, now you have 15 cents, and you get your I don't know what you get for 15 cents, piece of candy. nowadays nothing anymore, right? Or you put in 10, and then you can put in another 5, etc. This system is also able to use, my Zoom is in the way, so let me hide this thing. It's also able to compose these things into one diagram. So that's a little bit of category theory right there. Then there's for each section, like each paragraph is a morphism, and all the paragraphs together are a morphism, but each page itself is also a morphism, and multiple pages are morphisms. So that's what I wanted to say about that. And then lastly, almost lastly, we're currently looking for someone who really likes category theory, let's say, but is also good at the traditional development. This is, you can go to this URL, so statebox.io-bv.homerun.co/webdeveloper. Looks like this. So there's a bunch more information here about it. You can read that up. This is what it would look like when you would land on the page. So some tutorials and things. I'm now using it nearly every day. You can see here all the various nodes from running on the Statebox TV infrastructure. So it would be funny to show. And then I left here my email address. We are particularly looking for, we're going to be doing another investment round at some point. So if you're interested in investing, please write here. If you have some project you think that could benefit from wiring diagrams and so on, project proposals, also write. If you would like to have an invite for Process.io, we will be giving those out soon. Same situation. And we are planning to organize a research event in the future. So if you want to participate there, also please write. One final thing that I don't think I made that clear actually is that this right now has the semantics of Petri nets, discrete Petri nets. The thing I would wanted to demo was something that has. I mean, these things look a lot like wiring diagrams. They're just, in a sense, directed hypergraphs. But we can give that the semantics of streams or state machines or stochastic Petri nets, chemical reactions like this. So that's the idea is to make this a very generic platform to do category theory in, also over non-discrete, non-finite, non-computable structures. And I'll stop there.
Okay, thank you very much. Right, Kreshnik, have you arrived to the meeting? Last chance. You have not. Okay, in that case, let's move on to the in-person part of this. Maybe, David, I will put you at the end. No, why don't you start if you want? Okay, should be ready.
All right.
The end of jealous time.
Okay, so my name is Davidad, or David Dalrymple, and I'm here on behalf of Protocol Labs. So first, I just want to say some things about Protocol Labs as a company. So if you've heard of IPFS or Filecoin or libp2p, those are some of the sort of in production things that Protocol Labs has produced so far. But our mission is much more general than things to do with file sharing and peer-to-peer networks, breakthroughs in computing to drive humanity forward. We have a sort of techno-optimistic perspective that breakthroughs in computing can in fact drive humanity forward in good and morally valuable directions. But we combine that with sort of skepticism of the default route by which this happens, and also thinking a lot about things like existential risks of artificial intelligence and the sort of bad prospects about the default development of brain-computer interfaces and things like that. Also, as a company, we have pretty strong connections with academic research groups. We do a lot of research grants, especially compared to other companies our size. You know, we're not doing as many grants as Microsoft Research, but it's unusual for a startup. Protocol Labs is a fully decentralized company, so there's sort of a vague nexus in the Bay Area, but no office or anything. And Protocol Labs team is distributed across 20 countries apparently to date. And because of the original nexus in the Bay Area, and also because our CEO Juan Benet is a very generous fellow, compensation across the globe is set above market relative to the San Francisco Bay Area. So that's a bonus, unless you can get a job at Google Brain or DeepMind, in which case, you know, the compensation is a completely different spectrum. But anyway, so I'm now going to, instead of trying to tell a coherent mathematical story, apply the sort of Billy Joel, we didn't start the fire pedagogical approach, and just give you a buzzword soup, because Protocol Labs is interested in a whole bunch of different things. So I hope this just sort of gives you a flavor. So one particular category that has a bunch of research areas within it is the idea of decentralized collaborative editing of causal models, which would then be used to do things like predicting, you know, forecasting the future, but also allocating the attention of researchers and engineers to different R&D problems, and also allocating funding to different kinds of initiatives. And so that would involve, in my conception of it, would involve using some categories, that these causal models would be morphisms and categories, and depending on what sort of features you want to add to them, like action spaces and observation spaces that may differ from the state spaces, you know, this goes all the way from dynamical systems through to partially observable MDPs, and we'd like to have open versions of those and versions of those that have this sort of operatic composition of wiring diagrams, and being able to take pushouts and pullbacks and products of models and, you know, combinators for combining them in ways that are sensible but also automatic, and can sort of automatically track as individual people update their components of a larger global model. We also want to look at CRDTs, convergent replicated data types, as a way of allowing people to do sort of decentralized version control with automatic or at least semi-automatic conflict resolution in cases where people are modifying different parts of a causal model that actually don't conflict with each other. Then we should be able to commute those updates. And you know, bidirectional transformations, and thinking about schema evolution, specifically in the context of where with our schema is, we're talking about string diagrams. So the schema is what's the set of generators and equations, or what are the families of generators and equations in this diagram. And as those get revised over time to incorporate more modeling approaches, or to merge different modeling approaches into more general forms, that sort of thing, how can we allow all the string diagrams to update along with that? And then finally, for this section, the sort of incremental computation and efficient implementation of the various sorts of queries that you want to do on these kinds of models, like what's an optimal policy? We can do value iteration or policy iteration. We're going to do model checking to be able to get guaranteed bounds on regret, for example, or expected value. And that involves also a sort of probabilistic programming aspect when we're looking just at feed-forward causal models. If they incorporate real data as score functions, then that leads into this sort of domain of probabilistic programming inference algorithms. Another general area is decentralized databases. This is closer to Protocol Labs' core products, because we have a lot of people who are interested in using IPFS or Filecoin to power applications, but the way those applications work is not by periodically writing terabytes of data to the cloud. It's by doing database updates. And so we're interested in various approaches to advance the state of the art, and how decentralized databases can take advantage of technologies like hash linking, and also then do incremental query evaluation, because we don't want to be actually revising the blocks of data that have already been persisted into Filecoin, because Filecoin keeps those around for at least 6 months at a time. So we want to do incremental computation by taking into account all the blocks that have been written since some snapshot period. And then generally just, I'm really interested in bridges between, there's a whole bunch of different approaches to thinking about how data in databases change over time and how you can integrate data in decentralized systems. And it just sort of seems like there ought to be some kind of category theoretic picture that unfolds into most of these as special cases or just as particular ways of looking at it for certain applications. And then the final area, actually not quite final area, the final penultimate area I want to mention is mechanism design. So I've been spending a lot of my time recently thinking about designing mechanisms for resource allocation, for credit assignments. I've been thinking about impact certificates. You can find a couple of talks I've given at Funding the Commons about this kind of stuff. And I think there's a lot of potential for looking at an operatic or category theoretic approach where we want to some extent, maybe some kind of lax extent, for these mechanisms to compose, in the sense that if you have groups of people run the mechanism with each other, and then as a subgroup take the result of that and join into a larger group and run the mechanism in a larger group, that this would produce a similar, or at least not too much worse result than if everyone were able to participate synchronously in one large group. So interested in things like that. And then the final area I want to mention is AI existential safety. I am going to go out on a limb and make the bold claim that AI existential safety is quite plausibly more dangerous and a sooner, more urgent risk than catastrophic climate change. So this is something that I spend about half of my time thinking about at the Future of Humanity Institute in Oxford, and Protocol Labs is quite interested in sort of trying to mitigate this risk as well. In this field, there are a bunch of concepts that have been floating around for years, like the orthogonality thesis, that goals and capabilities are independent in some sense, and things like that, which basically don't have a clear mathematical concept yet. So applying category theory to that, I think, could be very fruitful. So I'd love to talk to anyone interested in that. So here is just a list of the sort of ways in which Protocol Labs can support people. We get grants for people who are still in academia, part-time roles, full-time roles. And so if you're interested in any of the concepts that I've just thrown out there, or especially if you're interested in several, please reach out to me on Twitter or by email, or find me. I won't be around that much in person, but I would love to talk to you or set up a call or something. Thank you.
Right, Stanislav, I think you're next up. Yeah.
Right? Yes, that is great.
Okay. So next up we have Stanislav Kapulkin from Vieta.
Yes, thank you. I'm Stanislav Kapulkin, and I represent the company Viet, and we developed no-code modeling platform based on category theory. Idea of the Viet is to provide a single environment where you could put a program logic, a task description for the program, and also could describe the business model to what the task will be part. And also you could provide the proof for the program that it solves the task and explanation how the task relates to the business. Well, as Viet is a no-code platform, we develop some visual elements from which we build a visual language, of course, category theory based. So first is elements are object and morphism. Morphism could have a label, so it's become familiar to string diagrams, but now we use usual classical diagrams. Well, and also provide such visual element as a link. Link allows to provide an object as a variable and refer to any complex category diagram right here, variable refers to the morphism, so it represents the morphism. So if I will draw the morphism from the variable, that will be morphism from morphism. Well, we could interpret the arrow f in another way. For example, if the objects here are categories in a category cat, then we could interpret arrow as a home set of functors, and then the variable will be the category of functors. So this is some ambiguity, but it's comfortable when you, for demonstration purposes, when you want to draw some diagrams and interpret them, it is comfortable for you. It's not good when you need strong semantics for evaluation, for example. So this is the open question, how better to distinguish morphism from home set. Enriched categories is one of solutions. Well, also we have a syntax sugar, visual syntax sugar for products and coproducts, and we have some more elements. Let's look at some example. We will meet other elements, by the way. Well, there's an example of the task of keeping data in the cloud, and we want to be sure that the file will not be changed. The solution here is to evaluate signature and keep it in a public blockchain. We will see it later in details. Well, and what we have here, we have initial state is a pair of file and label that file on the client side. After uploading the file, we move it into the cloud, and sometime later we get an alternative. The file was changed, the file is not changed, and we want to have a check file persistent function which will give us the correct answer. Well, also there's file and change file as just a label. We could add the semantic to describe the change file is not equal to the file. Well, there is a solution. Here we assign to every file a file ID. It's comfortable to keep signature in the blockchain and associate the signature with the correct file. And we also have the implementation of check persistent function. We could map the problem statement to the solution and use function for that. There is a UI how the function could be described. Well, and there is somehow how could draw a business model. It uses some part of the solution diagram without technical details and brings some details related to business, for example, payment details. Well, now we could come to the proof for the solution correctness. Well, to do that, we should describe some properties of the signature or cryptographic hash function. In other words, there are two properties for keeping privacy. One states that privacy is not broken, and other that it's hard to find the collision. When I state that it's hard to find the collision, I add some labels like reasonable time and practically improbability to some morphism. It's some attempt to describe enriched categories where we assign some space, for example, metric space to the morphism. There is here reasonable time is just a label, and to define it in a strong way, we should introduce a one-way function. Well, there are in this diagram there are some nodes like evaluation time which have upper bound as a polynomial time and probability object which have upper bound also. And to define labels like reasonable time, we should just link the labels to the correct objects in the one-way function diagram. And when we do that, we should remember that link allows us to refer some variable to the more complex diagram. That means that we virtually could substitute the diagram of y function into the definition of the signature property. And if we will compose virtually, we will get a strong definition of the property, but it will be too complicated. So there, I choose to decompose the property definition into two parts and link parts of the more abstract property description to the diagram with more details. That's how the compositionality looks in the VS. Well, we refer to some parts of the submodel, and these specific elements in submodel works like an interface to the whole diagram. Well, if we have, so now we have defined all necessary properties for signature, and we could, to make a proof, what we want to prove. We want to prove that when the file really changed, our check persistence function will return changed label. So there will be just one result, and we have the necessary property in the signature which works with change file, but it has two branches. One of them is marked as improbable. So to use this property, we should eliminate branch, and here we could use reduction rules. The example of reduction rule is drawn below at the bottom, and in the upper part there is reduction where we eliminate one branch. So there is two parts, one with two branch and the other is eliminated. Well, and to show the connection between the reduction rule and the reduction, we could, for example, for the demonstration purposes, to map the reduction rule diagram into the target diagram. It's not necessary, it's useful only for demonstration details. What's more important, we could draw the arrow from the reduction to the reduction rule, and there is embedded a check that if the rule is applied correctly, then the arrow will be black, otherwise it will be marked with mistake label. Well, there is no automatic reductions right now. You should all do manually, so it's an obvious target of the development later. And right now we are in a closed beta. If you're interested to try the editor, please add into our chat in Telegram or find me in social networks and write me. And thank you for the attention.
Okay. Next up, we have Mario Alvarez-Picado from Hawaii. This is the PowerPoint indeed.
There's also a PDF.
Yes, but then I would need to download it. So.
Hello, everyone. This is brilliant. So, hello, everyone. I'm here on behalf of Huawei Research, in particular the.
Sorry,
it's quite all right. I'm here on behalf of the Huawei Research group at Edinburgh, specifically the Programming Languages Lab. The first thing that you may find surprising is if you know Huawei, you mostly know us for our electronics. I reckon probably a significant number of you have a Huawei phone. But what I found surprising when I heard about it is that Huawei does indeed have anything to do with programming languages at all. But it turns out that, yes, we do have, in fact, we do a surprising amount of programming languages research. We do a lot of it. I would like to give you a sort of, first of all, a broad overview of some of the company-wide interests that Huawei has. And then I would specifically like to go over the projects that we handle at the Huawei Edinburgh Research Centre. At a company level, I think the main three areas that we're currently involved in are, first of all, trusted programming. As you may know, Huawei is in fact a platinum founding member of the ROS language governance group. And we have a significant, we've in fact hired as full-time employees a significant amount of members of the core Rust compiler team. One of them, in fact, is my colleague at Edinburgh. We also undertake projects on generally approaches to safe programming. There are groups working on verification of algorithms. There are groups working on explainable machine learning. On the topic of machine learning, we also, not us specifically at Edinburgh, but Huawei also develops a framework that you may have heard about called MindSpore, which is, it intends to be a framework for specifying and running machine learning models. And this is, in a way, it's similar to TensorFlow. You can think of it as a next generation TensorFlow-like platform. And we've also developed an extremely high performance C++ compiler that is specialized to Huawei hardware. So as you can see, there is a surprisingly strong culture of investments in programming languages and programming tools at Huawei. But more specifically, I want to talk about our own work at the Edinburgh Programming Languages Lab. This picture is not here just to look pretty. This is actually the view from our conference room, which we are very proud of. And I think something that probably everyone in the audience will find interesting is perhaps the flagship product of our research group is a intermediate representation for programming languages and program manipulation that is based entirely on higher order string diagrams. So this was inspired by our lead researcher Dan Geeka. So he has worked extensively on string diagrams. He developed this graphical representation called the Spartan calculus, together with some of his PhD students who built some rather impressive tools for handling it. And so we took those ideas and we developed them into an intermediate representation that is, it truly is much higher level than something like the LLVM-IR. And we've leveraged this very high level intermediate representation to basically build a compiler on top of it. And for example, one thing that we do is we formulate all of our optimizations are formulated as graph rewriting rules. We're also working on graph-based visualizers, graph-based debuggers for this intermediate representation. We're also undertaking theoretical work on this. So the theoretical foundations of our intermediate representation were recently are scheduled to appear in FSCD 2022, where we describe these higher order string diagrams in detail and show formally how one can do double push out rewriting on them. We have some employees that are in fact working on a fully mechanized presentation of this intermediate representation. And as I said, we do a lot of very practical, fairly low-level work that is based on this. We do optimization, we do abstract interpretation, we do program analysis based on this. And we have a number of rather noteworthy projects that are building on this graph representation for delivering more sort of high-tech programming language features. One of our most significant achievements, for example, was the development of a whole program automatic differentiation algorithm that is based entirely on string diagrams. Now, automatic differentiation algorithms are notoriously hard to understand, but thanks to our graphical treatment of it, we took one of the more famous reverse mode automatic differentiation algorithms, which I won't explain here because it gets quite technical. But we were able to produce the first proof of soundness for this AD algorithm by rewriting it in terms of these higher order string diagrams. There's a preprint available online. but this sophisticated representation lets us handle some very high-level program features. This is a very exciting project, and I'm not saying that just because I'm the main person behind this project. It truly is very exciting. We are building an AD framework that does things that nobody has ever done. And part of the reason why that's possible is because we've framed everything in terms of these string diagrams. We can do some extremely complex transformations, some really complex program transformations. We can write them as very local, very simple rules for just rewriting string diagrams. We have some extremely ambitious projects in the horizon. Another one of them is effect handlers. Effectively, we want to build effect handlers into a language based on these string diagrams. There are already some publications on this topic. And we are currently collaborating, or we are going to be collaborating with Phil Wadler to build a type system for our particular vision for effect handlers. We're also working on probabilistic programming, and I'm told I should hurry up, so I will. The point is, we do a ton of research in programming languages. If you're at all interested in string diagrams, differentiable programming, probabilistic programming, effect handlers, or just programming languages in general, and you want to take part in shaping up an actual real programming language that will have thousands or hundreds of thousands of users, please get in touch with us, because we're always looking for interns, and we are also hiring for permanent positions. Yeah, thank you very much.
Okay, Ross, you're up.
Hello. Right, hi everyone. I'm Ross Duncan. I am the head of quantum software at a company called Quantinuum, which might not be a name that many of you are familiar with. Quantinuum is a full stack quantum computing company. It's not existed very long because it was formed by a merger between my previous employer, Cambridge Quantum, which is a quantum software company, and a unit which used to be part of Honeywell, which makes ion trap quantum computers. So this is now somewhere north of 400 people, about half on the blue side, which is mostly based in the south of England, but also Tokyo, Munich, and soon Paris, and the white side, which is almost exclusively in Colorado in the US. So I am interested in quantum software, so I won't tell you very much about how to make an ion trap, but what do we do particularly in the software side of the business? Really two big categories: system software, which is the stuff you need to make your quantum computer actually do stuff that you care about. So compiler and optimizer, various systems for programming it and having these programs actually run. Online services that allow you to access these devices, because those devices are all in Colorado and not in your house. And more of a research focused direction on quantum error correction, because as we'll discuss later, quantum computers are very error prone. And the other big thing is applications of these devices. So the big ones for us are based on simulating systems which are themselves quantum systems. So we're talking about molecular chemistry, condensed matter physics, material science in general. Some things which are slightly more long-term would be looking at machine learning using quantum devices, looking at quantum natural language processing, and a lot of algorithms based on Monte Carlo methods, again, using quantum computing. So the point of all of this, I should say, is to try, the company's overall mission, I say, is to make a quantum computer do something useful. And by useful, I mean two things. One, somebody has to actually care. And secondly, it has to do it better than a classical computer. And from a complexity theory point of view, this is quite non-obvious. There's basically no theorems and very few examples which are really convincing. But we do believe that exponential or better speedups can be achieved for certain problems, especially these quantum simulation type problems. Okay, so here is a product that we have recently released. It's called InQuanto. It's a set of tools for doing computational chemistry using quantum algorithms. Unlike all the other software I'll mention in this talk, this one is not free software. This is extremely expensive software. But it is aimed at people who are, let's say, in the business of discovering new materials so they can make 10 billion LEDs every year, this kind of thing. So what is the actual problems that we try to do in this stuff is to basically to compute the energetics of different systems. And actually quantum chemistry from a theoretical level is exceptionally well understood and exceptionally computationally expensive. So you have these methods, for example, the full configure interaction method, which can compute everything exactly, but you probably can't do it for any molecules bigger than hydrogen. And as we go down the complexity cost curve, things get more expensive. And so we tend to use different methods which are less precise. So the aim of the computational advantage we want to see in chemistry is to get more accurate answers than these more approximate classical methods that already exist. And classical methods can give you pretty low precision answers, even to quite large molecules like big proteins. So what would such a software look like? This is the kind of rough shape of thing. I'm going to go into any of the details here, but if you go from left to right, you can see gradually the changes of what's your theory you're working in. So in the top level, you have something which is comprehensible to a chemist working, for example, in metallurgy. And then this has to be transformed into a formalization of the problem, which is more amenable to computation. And then we start thinking about how to make this into a quantum algorithm. And this algorithm then has to be compiled into something that runs, and eventually a number comes out. But you can see this kind of descent of different levels of abstraction in the picture here. So this is Irfan. Irfan's one of the people who makes this software. And he mostly thinks about things like molecules, spin orbitals, energy levels, and so on. But unfortunately, the quantum computer that he speaks to doesn't care about any of those things. It cares about quantum circuits, and it gives him back only counts, as in how many times it saw certain results. So when we actually write this software, we have to think also about the quantum computer as a bigger system. So at the bottom level in the fridge, you have a hard real-time system. So qubits don't live very long, so you've got to do everything in the lifetime of your qubit. But next to that, we have some kind of classical device, which should be high speed and controlling this quantum computation, which might be next to a much larger, slower thing, doing some heavy classical compute on large data objects. Hamiltonians, these kind of simulations can be gigabytes in size already, so we're not doing this at real time. And then, of course, this stuff happens at compile time, which is stuff we know can do in advance. And so if we're writing quantum software, we have to deal with these different time regimes, we have to deal with these different capabilities and these different scopes. And so somehow the combination of compiler and human being must distribute this computational task among all these environments. So quantum computers, maybe I don't have to say this anymore, they do exist, right? And there are lots of different technologies which have been proposed. So superconductors are probably the leading technology, ion traps in close second place, and there's multiple companies making these things now. So a couple of weeks ago, I logged into my IBM Quantum account, and I had these 20 computers available to me to use. So they do exist, and they're real, and one evidence that they're real is that 2 of them are not working today. So these machines are what we call NISQ. So this is a lot different to what you learned about in Nielsen and Twang if you learned your quantum computing from a textbook. So what does it mean? The IS stands for intermediate scale, which means they're small. I'll just leave it at that. And the N means they're noisy, which means that we have to deal with the fact that these are really analog devices. And so every operation you want to do has some limited fidelity. Your qubits have a limited lifetime, The errors have no nice properties whatsoever and are extremely hard to model. But the upshot of that is that you don't even need to say intermediate scale. The noise will build up and kill you before you get to a large scale computation. So it means that we have to really take a different approach to programming these kind of devices than we would with a classical computer. So the key point to notice here is that things that we are computing are statistical estimates of properties we want to know, not exact computations. Right. But before I come on to that, I want to say briefly what quantum compilation is. Is that seconds? Ah, fuck. Okay. We've got a compiler. It's called Ticket. You can get it from pip. It's free, open source. It plugs into everything in the world. For anyone that doesn't know, quantum circuit for this audience is basically a prop with an interpretation functor and FG-hilb. So what the compiler is doing is computing functors between these different props, doing rewriting on them, and then translating them back into something the machine can actually eat. Yeah, lots of things like that. And we have other software for error mitigation, which is quite cool because this is all based on higher order combs. So you put in the program that you wanted into this comb, and then it rebuilds it into something which would be less susceptible to noise. It is also free, and I'll show you a picture. Oh no, I'll show you a picture of the kind of things it looks like. So it's all graphical and it's all combs. And we have, this is just my team, not even the team in Oxford or London. Lots of academic collaborations. If you want to work with us, get in touch. And if you want a job, get in touch. Thanks.
Right, so going to have one more in-person talk given by Brendan Fong from Topaz Institute. And then there might be an online talk after this. There's some suspense, depending on if the power comes back on where our speaker is. Okay.
Okay, thanks. So this is approximately perhaps the last talk of the day. And there have been already hours of talks by Topos sort of scientists. So I thought I'd try and keep it brief and non-technical, and say some words more about the community and the context of the work. So I have 2 slides. This is one of them. So I started my PhD 10 years ago under the supervision of Bob, who's just left, and John, who's not here, but leaders of the community and steering members of this sort of conference series. And at the time, I wouldn't have imagined that we would have, after 10 years, an annual conference that's well attended like this and dedicated to applications of category theory. I mean, 5 years ago, when we started planning for the first of what would become the conferences in this series, I also wouldn't have imagined that there would be an industry session packed with lightning fast talks from major companies around the world, the largest companies in quantum computing and systems engineering and electronics. Would have imagined that Bob, who's just left, would be chief scientist at one of these companies, but here we are. So many of the conversations I've been having, or some of the conversations, a theme over the past week has just been the growth of this community and the potential for the work we're doing, the power it might have or has to help us understand the world we live in and build technologies to shape it. And I think if this session is any indication of that, and if the quality of the talks that we've seen throughout this week across quantum computing, machine learning, scientific modeling, programming languages, if these are any indication, then category theory stands to sort of fulfill this potential. And I think it's well-grounded. I believe category theory is a science that takes relationships and compositionality to the heart, and this is very important for understanding systems, and it is a cornerstone of an emerging sort of new science of systems. So where does it go? So what does that have to do with this talk? Topos is a nonprofit research institute, a community institute, to sort of unlock this power of a new science of systems for public benefit. And when we look around the world and the systems that surround us, our aim is to ensure that they benefit us all. And when we talk about the power of technology over science, I think we should also ask some questions, right? When we talk about power, we should also ask, will this power be used? What will it be used for? Who will use it? Sort of whose problems we solved? What will the quality of those solutions be? And perhaps most importantly, how do we know what we're doing? How do we have confidence in what we're doing? And so part of what Topos does is not just the research in this, but I think it can help play a role as a community institution to help consider these broader questions of our work too. So I think this is important, right? Recent history, even very recent history shows that positive answers to these questions cannot be taken for granted. Whether it be the potential disadvantages of technologies like AI, or I'm speaking of things I wouldn't have imagined 10 years ago when I moved to the UK. I wouldn't have imagined that a London summer's day would be 40 degrees and disrupt attendance at an event like this. But again, here we are. So the point again of Topos is to participate in the project of building positive answers to these questions. And I'm very proud of the work we've presented across this week. And I think sort of gives some insight into the model we have that involves the importance of basic mathematics and science to really understand systems, because we believe partly that that's inherently important, but also because good technology is built upon good science. And so we also participate in the process of building that technology and then considering these broader social, practical social questions and questions of ethics and impact. So in particular, across this week, for example, we've seen talks, Topos work on just the nature of organizations or intelligence. We've seen technologies, tools we build from this theory to address problems like epidemiological modeling and make scientific modeling more transparent and accessible, more human. And then, a bit more under the radar, but Topos has helped support things like the adjoint score, which helps build this community and ensure or welcome sort of new researchers to apply category theory and facilitate travel funding, because finances shouldn't be a barrier to participation in this community. So I'm very excited about our work, so pushing deeper into all these aspects. Again, this is a big project, and it's the work not just of sort of Topos proper, but of an entire community. And so there are plenty of ways to get involved. We have our head sort of office based in Berkeley, California, and an emerging one here in the UK in Oxford. Please keep an eye out for if you're interested in job openings over the coming sort of months and years. Please, there's a lot of collaborative projects to be done, and we also, one way to be involved is just we do a lot of work online. We publish papers, there's blogs. You can comment on the blog. We have a lot of online seminars. Please participate in the seminars, and if anything's at all interesting, please also come speak to me or any of the scientists here at Topos. Would love to have a conversation today, across this week, or over email or Zoom. Cool. Thanks.
Thank you very much. Okay, let's see if we have one more talk or not. Kreshnik, did you manage to join? Yes, there you are. Excellent. You are muted though.
Hey guys, I apologize for the mess there, but we just got power, so it's amazing.
Okay, right. I need to make you a co-host. And now you also have the power to share your screen. And please take it away.
Thank you. So I'll try and make this short. I talked to Jules a little bit 2 weeks ago, and we went through something that has been an issue and a problem for us to solve in big organizations, which is the ability to compose teams, really. So there were a lot of, so I've done this presentation or part of it for bigger, for the business world. And I trimmed this presentation to be very specific to this type of group, and also to kind of show that in our world, one of the things that we struggle with is to abstract problems that have a lot of parameters, such as teams and all the variables that go on with having such big teams, and making them in such a way that they help the business get structured properly. So according to this year's Gartner report, companies that embrace composability will outpace the competition by 80%, and they have some, hype keywords, etc., in there. But the interesting part is a lot of the companies, especially in the remote world right now, are breaking into pieces. Like their way to deal with and big teams and organizing them is to break them into pieces, right? And then they say, okay, so now that we have these broken parts and pieces and teams and groups, how do we make them composable? And the reason why is because we need to make sure that the work that flows through these is combined properly, is composed properly. So one of the things, interesting to us in the industry world has been that if we form a category, then then things should be easy to compose, right? And when I talked to Jules, he brought up the fact that, look, just by forming a category is, it doesn't mean you solved your issues. Basically, it's beyond that. And I think he also talked a little bit about potentially almost like a general abstraction to these types of problems that we can apply a lot easier and simpler without the much more depth of the category theory world, which is way beyond what we kind of need. So this was an interesting. This is the patent of the original Lego patent from 1961. It was very interesting, and it's something that we talk a lot about in our world. And it's basically, how do you create the interface, the arrow per se, right? And what does it mean for problems that are not so easy to imagine and so easy to kind of think of in terms of categories. And in this one, you can clearly see that the interlocking of the pieces, it's almost like your arrow, right? Like your arrow interface is the interlocking, and it's literally just right in the patent. And so that's what we're looking for as well. Like, what is our patent? Where is our part of interlocking? And then obviously you can do so much more after that's figured out. And so one of the things that at Click, so Click is about 1,800 people now. When I joined, it was about 500 people, and so it's tripled in its way to quadruple right now. And through these changes and transformations, what we've seen is that growing the teams, we need to keep that those composability parts, right? And we need to keep the flow of things. And in our world, there's two things that actually that could form the arrows in a way. And those are communication flow and flow of artifacts. Those are the two most important parts in our world. And if we solve those two, then in a way, our teams as an abstraction, as an entity, are composable in a way. So communication flow matters a lot, obviously, because, and I'm not going to go through the actual presentation pieces in here, but it matters because, obviously the lines of communication grow, quite a bit if you grow the members of the teams, right? So you can imagine that a team that had, for example, or smaller groups that were 2 or 3 people in the past and now are 20 and 30, it's impossible for them to keep all these lines of communication. So naturally we break them down, but by just breaking them down doesn't really mean anything, right? The information still has to flow, and the artifacts and the information that goes with those artifacts has to flow as well. So we almost need like a general way, a general abstraction, or a general theory in a way that encapsulates what do we do with these communication flow and flow of artifacts in terms of a category, or potentially in terms of defining what the composition interface is. So I'll give an example of something that we've done, and things that we've tried in our world to make this work. So let's say we had groups of teams in the past that were like your pizza team, right? Like your pizza team being let's say your 2 designers, 2 devs, 2 QA, maybe even a BA, etc. Right? So those are small groups that naturally, because they're so small, the information and the artifacts flow easily. And in a way, you can compose the groups. You can go from let's say design to QA without really knowing the pieces in between, without caring about the details. Naturally, it just happens in a way, right? It kind of happens naturally. The moment that these grow, it doesn't anymore. So what is that general abstraction? Without getting into, so you guys could provide a lot more benefit to some sort of general theory of something that we can use, but without going into details, one of the things that one of the almost like solutions without having a framework that we have, seen that it works is, well, let's say this is front end and we're doing design, dev, QA, etc. Well, if we introduce, for example, a unified system, like a design system or an API layer or something that all the teams have almost like the same abstraction, the same interface, then all the work, all the artifacts flow naturally, and it, in a way, potentially forms a category. Because it forms a category, it doesn't really mean anything. It doesn't mean that it's still it's composable, but at the very least, there's a step forward. So I don't have a solution. I do think there's a need in our world to have a solution for this, and I think there's an opportunity to potentially get some bright minds to help us with this.
Right, thank you very much. Right, that's the end of the industry session on time, amazingly. And next, we're going to move on straight ahead to the community meeting that Dave is going to chair. Can you find the thing?
Yes.
Great. Oh, he might want to talk at some point, but I don't think it's not crucial.
Oh, I see. Okay.
Is Jade here? Okay, so this is the community session. I have an agenda on here. It's a half an hour long, and I'm going to keep to time. And then if there's things that people want to discuss that take longer, then we can stay after. Anyone who wants to can kind of stay after the half hour. But we'll just get through this thing. Great. So it's 30 now. So first of all, we're going to hear from Jade, or the PC chairs. I guess is Jade here? There she is. Okay. Right. Okay. You want a microphone? This one. So we're going to talk. Let me just say what we're going to talk about. We're going to talk about a report from this year about what happened. We're going to talk about very quickly. We're going to talk about what happened with last year's proceedings. It's already on there, so you can see. We're going to talk about next year's location. This one's pretty important. And we're going to talk about guidelines, and we're going to talk about feedback from you guys. We're going to talk about job announcements and any other business. So that's what's going to happen over the next half hour. Okay.
Yeah, so I'm not going to say all those things because I didn't look them up. But so 2 things is, one, that I'm really proud of everyone. There's like lots of really great submissions, and I'll be in touch about the proceedings. Next thing is that I wanted to thank all the grad students who have been working very hard. So like Ezra right there, and Ryu, and also Malin, and Bruno, and Eva, who's not here. And that's all the grad students I see in this room, but there are more, and they did all the snacks, and they did all the streaming, and they did a lot of hard work. So can we give a round of applause for all of them? And that's all I have to say.
Okay, so now if we can get Kohei on the line, I don't know how to do that, but if he's on the Zoom, we'll see. And if he's not, I already know what he's going to say, because he told me in case he can't be. Oh, he is great. And I should say before Kohei talks that in all of my time, I think he's 10 times literally more conscientious than any other PC chair I've ever seen. So this guy, okay, go ahead, Kohei.
Yeah, thank you. So first of all, my sincerest apologies for the delay in the publication of the proceedings. We envisaged that it would be out like much earlier this year, but well, so the TCS is currently working on publishing it. So everything, all the papers are in, preface is in, abstract is in. So yeah, it's under the process, but it's a summer out there. Like some of them are taking summer breaks, so it's a bit slow, but I expect it to come out later this month. So that's, but again, my apologies for the delay. I had a bit of a family issue and my own health issue last year. So anyway, so that's the report. About the papers, so we have 26 papers out of the 51 talks from last year's ACT. So it's very impressive selection of papers. I'm very happy with all the papers, but yeah, thank you so much.
Thanks, Kohei. Yeah, Kohei was literally, as an editor, like finding errors in my grammar, and like it was kind of incredible. Like not only like basic errors, but like because the math wasn't quite right. So it is incredible. Anyway, so probably the most important thing on here is next year's location. We haven't pinned that down yet. We also need a PC chair. And so in the future, we really should be thinking 2 years in advance. So if you're the kind of person who might want to be a PC chair, or you're the kind of person who might want to organize a conference, it's a good amount of work, but it is also the sort of thing that brings a ton of great people to your location and is like community building and is pretty valuable. So it's valuable to the community, and I think you'll find it's valuable to your own research group. So I'm looking for volunteers for next year's location. We have anyone or a PC chair? Okay, James in Florida. We've got Joe in Maryland. Where are you? Dalton, where are you? Here at Strathclyde?
No, Stony Brook.
And Stony Brook, New York. Great. Okay, cool. That would be to organize or to be PC chair? Help organize. Okay, cool. Others? Carlo for PC chair. Okay, great. And Bryce? Great for chair. Okay, cool. So I'll record those somehow. And then we'll be in touch, and I don't know, the steering committee will think about stuff, but basically anyone who's volunteered, I really appreciate it. And yes, please start thinking for next year, because basically you kind of have to start if you're organizing kind of in September of the year before. So that's actually thing number 4, is that Doretta and I and the steering committee are drafting guidelines for that. So you won't be so on your own next time. We have dates and what you need to do and how you get a budget. Currently, Topos Institute is the custodian for the finances of ACT, but we're trying to formalize it so that barrier is like clean, so that like other things could be the custodian, but that makes it easier for Topos to like do the things that it needs to do, and for like the steering committee to do the things it needs to do, and kind of separation of duties. So that's kind of why we're trying to formalize what it is that the organizers have to do, what it is that the financial custodian has to do, how they interface, how a budget works, and stuff like that. So so that's kind of thing. I guess I'm going way faster than I need to, but I guess that means we have plenty of time for the later things. So I think I should say maybe before we do feedback and other business, I'll just skip number to job announcements. So I have a list of things that I know of job announcements, but maybe each one could say a minute if they want to. Does anyone from Planting Space want to say any, like 30 seconds of what they're looking for? Just say it like kind of.
Sure. So I'm Peter from Planting Space.
Is that not a good idea? That's a terrible idea? Okay. This thing, does this thing work? Yeah. Okay.
Works? Hi, I'm Peter from Planting Space. We are a company. We use a bunch of category theory and other things. What we do is we build a system for knowledge representation. And in particular, what it's supposed to do is synthesize probabilistic models in order to answer people's questions about all kinds of things. The interface that we built looks a little bit like Wolfram Alpha, but you can see the steps that were followed in order to answer the question, and it's probabilistic. So check out our website is planting.space, and we are looking for anyone from programmers to researchers in all kinds of domains.
Great. Swansea, Pierre at Swansea.
I'm Capucci, so yeah, I'm a lecturer at Swansea. So I just wanted to advertise two fully funded PhD positions there. One's on real exact computation and dynamical systems by a colleague, and mine would be about rating automata and linear lambda calculi. In my case, like you can switch, you can put on some ACT stuff in there. I'm happy to talk to yourself, but I guess I should keep it brief. So feel free to reach out. The deadline is quite soon, or to spread around.
Great.
Thank you.
Okay, thank you. And then Jade. I know Neil's not here, but we're supposed to also. Will you say what you know of Neil's situation?
Yeah, so Neil is looking to hire people all the time. So if you want to work at StratFi with Neil as speaker, you should contact him. I think there's some full-time positions and lecturer positions. The Chancellor's Scholarship, I think it's a particular position he's looking for. And then my announcement is related to a grant about coalgebraic formal verification. So there's a postdoc position which is just opened up at University of Southampton. And it would mostly be working there at University of Southampton with Priyaa and Varshinee on basically finding a very general framework for formal verification on nice coalgebras. So if you're interested in that sort of thing and you want a postdoc, you want to apply for a postdoc and that sort of thing, then send me an email and I'll get you sorted.
Great. I wasn't sure if Topos is hiring for things. One thing we're hiring for is like operations stuff, which is probably not what everyone here would want to do. It's not really a research job, but maybe you know somebody. We are really needing an operations person. Brendan, is there anything else we should announce, Brendan? Details are on the website. Any other people who want to announce? Yeah.
Right, so I've been asked to relay two announcements, three with Neil, so I'll do Neil again. We are hiring and stuff like that. The other one is someone at Edinburgh and Napier University contacted me called Professor Peter Andras, and he has a fully funded PhD position available that is at the interaction between molecular interactions and category theory. So if you know any good students, he would like to know about them, so you can send them his way. Deadline end of July. And finally, Jamie Vickery contacted me to push that Cycle 9 is happening at Lake Como in September. Deadline 1st of August, if you want to submit something there.
Very cool.
Yeah.
And I think that's it. Oh,
I would.
Sure.
Hi, everyone. So Protocol Labs is always hiring, and Zavdad especially really would love to work with other category theorists in the house. And also they always do grants as well.
Cool. Thanks. Anyone else? James? Lost something.
Thanks. So I'm James Fairbanks. There have been a few talks from the Algebraic Julia team this conference. I'm hiring PhD students, postdocs, full-time research faculty. I have a job ad for the research faculty up. That should be like closing around the fall, like early fall. So if you know anybody for any of those to work on algebraic Julia, kind of any of the topics we've presented this semester. This at this conference, you know, the rewriting stuff, the simulators, the we have the computational physics talk tomorrow that Tim will give. So you might be excited about that too. So
cool. Great.
So this is an advertisement from Blake Pollard, who works at a startup called Cross Snowchain. They build DSLs for advanced control of industrial sectors, starting with cold storage. Base control system runs on an in-house extended finite state machine specification, over which we are deploying some cloud-based model predictive controls. We have paid internship positions as well as full-time opportunities. We are interested in using the algebraic Julia suite for applications. I think we can offer a great experience for those craving some real-world applied experience, especially current PhD students. So if you're interested in that opportunity, please contact Blake Pollard, or if you don't have an email, you can contact me and I'll send you one.
Great. Okay. And then there's any other business is number 7, and there's feedback from participants is number 5. And so what I suggest we do is start to just kind of start with things that are more business-like, something that feels like business. If you have anything like that, you're pretty sure it's business, like, you know, do like that. And if you're like, I'm not sure it's business, wait till that kind of peters out. Maybe it's already has. And then if you just have any feedback at all, do that. So just kind of however businessy it feels, be more quick to raise your hand. And as it bleeds into just feedback generally, be a little slower to raise your hand, and we'll do that. So anyone for business or of any sort that you think the community needs to know about? Yeah.
So it sounds like the steering committee is doing some really good work in formalizing what's going on with this conference. Is there is this work going to be, for example, guidelines going to be transparent public?
Right. Yeah, the guidelines are going to be public. So far we just kind of started on the guidelines. Thanks for that question. We sent it around to the other steering committee members. So it's Doretta and I working on it, and we got some feedback. Next, we're going to send it to like this year's organizers to see, like, you know, how does this match up with your experience, and like, would you do things differently? And then we're going to send it. Then we're going to kind of figure out how the budget's going to work. We're going to send that to Topos to see. I know I wear 2 different hats here. So we're going to send that to Topos to see if that looks right for how the budget negotiate. You know, like, we're going to send a budget by October. Oh, what do you need to know? You know, that sort of thing. Once that's done, and everyone's kind of, all the major stakeholders are kept in the loop, then we'll send it around to, well, we don't have a plan on how to make it public, but if any, I don't have a plan on how to make that public, but there's nothing keeping us from making it public, and it's something that probably should be public. So maybe Zulip, at worst case, if there's no other venue for it. What did you say? Conference, which conference? This year's conference? Next year's conference website? Yeah, okay, yeah, something like that. Yeah, we'll find some way to make it public, and if you don't hear from us, feel free to write. It'll be public at some point. Other business-y-ish things?
I have several things I want to say, and I can't find the raised hand button.
Go for it.
Hi, everyone. I'm feeling a lot more human today. The first thing I wanted to say, Brendan pointed out that ACT has grown. This comes with also some downsides, or some things to think about. Our acceptance rate, not including posters, was something like 57%, which is really low for kind of a community. I still think of this as a tiny community. We're 4 years old. I still want to think of us as a niche community, but 57% is a very low acceptance rate. I would like people to think about that. This conference is not big enough for the size of the community currently, I think. I would like people to think about creating smaller workshops for more specialized subfields. and especially having published proceedings. So, for example, I'm vaguely thinking about one on optics for next summer. I will take over the thanking of the sponsors because nobody else has done it. So our major sponsors were Huawei, Protocol Labs, and Cambridge Quantum, or Continuum, I guess. They provided a lot of money each. We also received funding from Connexus and funding from SIXA, which is a Scottish academic funder. It's not quite true that the conference wouldn't have happened without them. The reality is that we spent the vast majority of our budget on travel funding. So without most of them, a lot of people wouldn't have been able to come who did in fact come. So huge thank you to our sponsors. I mean, they basically what they're doing is they're making the community more inclusive. I would also like to thank my co-organizers for stepping up and filling in when I very unfortunately wasn't able to be there. I think that's everything that I was intending to say, other than also hi to everyone who I haven't been able to say hi to.
Hey, Jules, thank you. Great.
Oh, you mean there isn't really anything on there?
There's really nothing to say. Yeah, that's right. Yeah, I don't need to look at this thing. Yeah. Probably better to look at Jules. But okay. Any other like feedback or anything that anyone wants to say in the next little while? Of course, come find anyone who you think needs to know anything, or feedback to anyone who's an organizer.
We're doing applause for Jules for organizing.
Yeah, great idea. So thanks to Jules. Thanks to James. Also, thanks James Fairbanks for co-organizing, and yeah, thank you James. And who else? To Fred.
Yes, Fred did so much stuff on the ground.
Thanks, Fred. Go for it.
Yeah, I was just gonna say, if you want to be involved, like there's a lot of organizing for the conference that goes on throughout the year, like well ahead of the attending of the conference. So there's like that are relatively low stakes, like low effort commitments, like being a PC member, and then also submitting names for PC members. So we don't, like, it's good as a community, as conference organizers. Thinking. So it's good for the community and as like organizers to get a diverse group of participants, and that means a diverse group of speakers and a diverse group of PC members who are the people who decide who can give talks. So if you're like, you want to volunteer for that, or you want to volunteer other people to do that, I think, yeah, be proactive in that. Whoever gets to end up naming as the PC chair, I'm sure they're going to be welcome to get that list. So especially for people who you know who are not here now, those are the most important people to get that you know would be interested. That was all my
great. Thank you.
My plea for participation for next year.
Thanks, James.
I'm not sure what the right forum is for this sort of discussion, so perhaps the chair can advise. But in case this is the right forum, I want to follow up on Jules' comments about perhaps workshops and the way that this conference format might evolve. So I'm interested in whether we have a plan for things like parallel tracks, or there's certain things that one thing I'd like to see, Jules also mentioned inclusivity. I wouldn't mind more discussion of what we do as a community to promote that. I wouldn't mind more space for one-on-one meetings inside the sort of official structure of the conference. I certainly would love to. I haven't met a lot of people here. And I would love to at least make myself available to meet a lot of people.
Yeah.
the right form, but.
Yeah, I think so. So I think what we can do is, well, sorry, Fabrizio.
I mean, maybe one small, I think, pretty low effort thing that we can do that is also connected to what Jules was saying is, I mean, we have a lot of people here that are good with computers or, like programming, data visualization. I think that a kind of useful thing could be just collecting information that we have from, for instance, the submissions. So we can see, how many groups from different world regions have submitted something, acceptance rates, kind of arguments, like basically with data visualization, you can get aware of a lot of things. So maybe a field that you think is overrepresented ends up not being that overrepresented or stuff like that. So basically, I would like to encourage anyone that has fun with visualizing data to ask for this data. I don't know where we can pull it, but I guess from EasyShare or something like that, and play with it, because we could, have a basis to be more precise about all this. Thanks.
Mm-hmm.
Well, based on the data, I will say that it seems like the people with more reputation tend to get better reviews. It's sort of a rich get richer thing, which happens pretty much in every academic conference and every academic journal. And it seems pretty unavoidable, but just because. Yeah, so maybe there's things we could consider, like blind reviewing. There's disadvantages to that, but yeah.
So a few ideas are to have like physical one-on-one sign-up sheets. That's one idea. Another idea would be to pair up members of the graduate school with an established member of the community as like a buddy to like ask basic questions if you didn't understand something in the talk, or just have someone you can go to in a coffee break. You don't really know very many people aside from your graduate school friends. Another idea is to have like some breaks that are long enough that there can be tutorials that sort of emerge out of the interest that comes up during the conference. So if a bunch of people are coming together like, oh, we really like to talk about this, but the breaks aren't quite long enough, then there could be a tutorial session that can get filled up as the week goes on. So I think some of these things help with the inclusivity.
Cool.
Is anyone taking notes?
Yeah, that's what I was going to ask. Yeah, not yet. So yeah, maybe that'd be really nice. Yeah, if you can take notes, that'd be great.
We are still recording.
We are recording. Yes. I guess Andres has a comment up there. Nathan.
Thank you. Yeah, it's been great being here with all of you guys. And since you guys were commenting about diversity, I'm not really sure what everybody does here, but I got a sense that most people here come from inside category theory. And since this is an applied category theory conference, I mean, I was wondering if it would be possible to have a consideration of having a percentage of people that come completely from the outside. Or maybe, I don't know if you guys have considered maybe more of a workshop format where you have, say, people from science that are not category theorists, but that have, that have questions, and then these people can interact with mathematicians and category theorists to see if there's any possibility of applying category theory to answering questions that people have formulated from inside science. Yeah.
So just a comment that came to mind from a couple of comments ago. There was a mention about apparently joint school students with a member of society. Perhaps that could, for inclusivity for people outside category theory, you could perhaps make that as an option as well. Obviously, make sure you don't overload the people. So there's 10 people going to one big name and applied category theory after every talk to work out what the talk is about. But also with the tutorials, at a bunch of the physics conferences I've been at, they'll sometimes run a tutorial session the day before where they'll have one or a couple of tutorials that people can go to learn about something.
I think these comments are, a lot of them would be most useful to next year's like in-person or like organizing team. So people who are doing that, I'd encourage you to kind of re-watch this recording if that happens to you, or look at Eliana's notes. But who is next?
I think it's me. I thought I would just share an idea that came up in Park, a bunch of us the other day. Lots of us use and cherish NLab, and yet lots of the ACT stuff isn't on NLab. And there was this random thought about doing NLab hackathons where people write up all this applied category theory stuff. Like I do lenses all the time, but lens NLab is quite empty, and there's, I'm sure many of you will feel the same about your part. And it's hard doing it on your own. I have one or two things I did in NLab, but that took a while to understand what we need. And I think it's easier in a group and sort of having this push together. Maybe somebody who knows more how to do it, like Matteo, who's in the top 10 contributors.
Because apparently Matteo edited 3 pages and that put you in the top 10. Yeah. Yeah.
Yeah, that's all.
Okay, that's great, thanks.
This was just amplifying Brendan's comments about possible parallel sessions. I mean, this was came up in conversation with us earlier in the week. Yeah, I mean, if the contributions are getting larger and we need more talks, but at the same time need space in the gaps between the talks, and parallel sessions does suit more together. So.
Great. So why don't we have 2 more minutes in this session, then what we're going to do, what my plan is in 2 minutes, anyone who wants to leave can, and then if you don't leave, you're staying, but you can kind of peter out at any time. So it'll just kind of be a conversation that's organic after the 2 minutes from now. Nelson, did you have a comment?
This is actually cycling back to businessy things. The people who are officially organizing this aren't here, I don't believe, and so I'm not actually officially part of this, but a lot of us are going to be in Boston for the American Math Society's joint math meetings in, I think, January 4th through 7th, and there's going to be a special session on applied category theory there on Thursday, January 5th. So I think there will be more information out soon about how you can submit for that, but I think just keep an eye out for that.
The deadline will be around mid-September.
Yeah, the deadline's around mid-September. So presumably they'll release stuff in the next month or so.
Yeah, very soon.
Okay.
That's it. Thanks.
Great. Is there one more? Yes, there's one there. Owen has his hand up too, but let's make Owen, you'll be the second to last and Owen will be the last, and then we'll all empty out.
So this
or whatever.
is really quick.
Yeah.
It's feedback. I think there's lots of really good ideas for making this more accessible to outside category theory, but as someone who's come here from outside category theory, I just want to say thank you. You've all been really nice, and thank you for helping me figure out how I can apply this to chemistry. So loads of people here have helped me, so thank you all. You're always doing well.
Thanks.
So I think one thing that I like about applied category theory is that it's a little bit non-traditional, and we are we have the Topos Institute, and I think one of the things that's exciting to me about the Topos Institute is that we can prioritize things that are not traditionally valued in academia, such as value in terms of tenure track advancing, such as exposition and software development. And I think it would be great if we could somehow reflect that in our conference. I mean, we have a lot of software already, but yeah, I think I agree with what has been said, that it would be very cool to have a part of the conference that was dedicated to exposition.
Cool. Okay, well, thanks everyone. This has been great. Thanks to all the speakers and everyone else. So the community session is officially closed, and anyone who wants to stay, it's an organic discussion of the things we've talked about, especially if you thought it'd be a really great idea if that's not really, like, volunteering works way better for getting stuff actually done than saying it'd be cool if someone volunteered. So if you think something's important, it's really best to put your action where your mouth is, but to discuss it with others might be helpful. To join a group of people trying to do that thing, maybe we can have small discussions. If someone wants to stay around, they see somebody else who had an interesting idea that they want to talk to, we can either talk broadly or in smaller groups as things happen. So yeah, thanks everyone. Thanks for running around.
I'm not sure if we have like met.
Okay. Hi, I'm David.
Oh,
Nice to meet you.
You're doing opera things.
Opera,
Loads of
yeah.
opera competitions.
Yeah. You're doing opera? I'm doing opera. I'm doing opera?
You're doing opera.
I sometimes do opera. Yeah. And you?
Yeah, we like any kind of pleasure.
Oh, okay.
But yeah, opera.
Yeah. Like plain opera. Yeah.
Yeah, so basically do like
Yeah, non-symmetric. Yeah. Okay.
It's not all just connectivity, it's like more information than like
Okay, cool.
so yeah, and I'm doing like two different building categories of these things, but also like so doing like Category-Theoretic.
Oh, cool. You're here at Satellite or? Cool. Okay. Nice meeting you. Thanks again.